I'm ready to do it.
Okay,
Okay,
so
or yes,
should I present my screen, Pavitrata?
yes, yes, please.
Okay.
Whenever you will ask me, I'll start talking. Yeah.
Orinnam, are you ready?
I am
Yeah,
ready. Yeah.
we can start. So, welcome everyone. Today we have Professor Pavitra Barik. He will be the chair of this session. Yeah, over to you, Barik sir. Yeah.
Okay, good morning, everyone. We have first speaker of today, Professor Orinnam Banerjee from Ramakrishna Mission Vivekananda Educational and Research Institute, Belur Math. He will speak on age ideals and introduction to combinatorial commutative algebra. Orinnam, please.
Thanks a lot, organizers. This is an amazing opportunity. And okay, let me first start by apologizing. My computer has broken down a week or so ago, and so I am forced to kind of give a talk like this with handwritten slides and so on. And I am really, really sorry about this. And so, and if any book, ask stop me and ask me questions right away if you cannot read something and so on. And also, in this kind of virtual talk, I cannot see the audience, so I'm not sure about my speech. So for feel free to stop me either way you want. I mean, either you want and either
Dr.
send a message in the chat box and so on. Okay, let me start by
Orinnam.
yeah,
Yeah, your voice is breaking actually.
yeah. Or, can you hear me now?
It's still breaking. Yeah.
Can you hear me now?
Yeah, we can hear you, but the voice is breaking. Yeah.
Just 1 second. I can see what can I do here. Is it clearer now?
Yeah, it's better. It's better.
Yeah. Yeah. Okay. Okay.
Okay, so the topic of my talk is basically, I mean, I was requested to give a talk on my area. So I work on this area called algebra mostly, and my talk is basically an introduction to this area through one particular object called edge ideal. So that's what I'm going to talk. So next slide. Okay, so as I said, this is going to be an introduction to, or rather, I should say, invitation to combinatorial commutative algebra through edge ideals. So what are edge ideals? Before getting into that, I want to explain what really combinatorial commutative algebra is a bit. Um Combinatorial commutative algebra is essentially commutative algebra objects, and by objects we mostly mean rings and ideals, or more precisely, a polynomial ring. You have a polynomial ring, the ideal inside that polynomial ring, which comes with some combinatorial associated to it, and then you study the ideal per se or the polynomial ring quotiented by that ideal. So, but before telling what kind of things we study, I want to give you a little bit of a glimpse of this word commutative algebra in this context. I mean, what part of commutative algebra I'm talking about. So before that, all along is any field where whatever I'm talking today is almost completely characteristic free. But let me a priori warn that theory of real commutative algebra is not in general characteristic free. There are lots of character dependencies. But today I have chosen my topics so that it's characteristic free. For today's talk, I will take I to monomial ideal. Uh, so basically, I has a minimal monomial generator, and if a polynomial belongs to I, all its monomials will belong to I. So that's just for today's talk. I'm thinking I to be a monomial ideal. So let me first introduce the commutative algebra part that we'll discuss. Uh, then we'll get into the combinatorics later. Next slide, please. Okay, so I will essentially discuss two problems today. The first one is related to so-called associated primes. By the way, can people read what my slides? Is there anything
Yeah,
that
I
is
think I
Yes,
think
sir.
the slides are readable, but your voice is actually breaking. That's the problem. Your voice is still breaking. Yeah.
Is it still breaking?
It's now clear, but when
It's
you start to, yeah, it's
So,
slightly breaking.
so I think what's happening is the microphone is going from my
Okay.
face sometimes. So let me just try to make microphone is always close to my face. So any ideal can, as most know, can be written as intersection of ideals whose radicals are prime ideals. A particular class of some such description, when where the radical of these ideals are prime, and when you take the quotient, every element is either non-zero divisor or nilpotent. A particular such class we are interested in. Such Qs are called primary ideals, and you can write, and it's known that in a Noetherian ring you can always write an ideal as such intersection. If you can do that, do so. That's called a primary decomposition. There are many interesting uniqueness properties associated to primary decomposition, and this is the first thing that we are interested in. Given an idea, you want to write it as intersection of uh, primary ideals. This is a big problem in commutative algebra, and this is the first topic that we want to discuss. Now, one of the reasons people are interested in decomposition, you that is right. First of all, I mean, writing down something as section or product or whatever of simpler objects is runs across whole mathematics, and that
Arindam, you're not audible at all. No, now you're not audible at all.
Arindam.
I think he's having some serious problem with his audio. Yeah.
But it seems he is there. But yeah, no voice is coming yet.
So yeah, I think I should wait for some time. We should, yeah.
Okay, he has left. He may rejoin in a minute.
Right. Right.
Yeah, it could be possible due to network problem.
Hmm.
Yeah, I guess the network is gone.
what do you suggest? I mean,
Let's wait for something.
okay,
Some time.
okay. Yeah.
So Professor Arindam Banerjee got disconnected due to some network issues. So we are waiting. We hope that we can connect him in few minutes. Saurabh, can you call him once again?
Yeah, sure. I'm trying to call you. Yeah, okay.
Hello, Gaurav.
I think he's there, right?
Yes.
Yeah. Okay, great. Yeah.
Yes, Arindam, we can hear you.
So up to the primary decomposition part, you were audible, and after that, everything went off.
Hello.
Arindam, yes.
Yeah.
Arindam, please continue. Oh, he got disconnected again.
Hello.
Yeah. Yeah. Continue.
Yes, Arindam, please continue.
Hello.
Hello. We can hear you. You're audible. Can you hear us?
Arindam, there is some issue perhaps.
অরিন্দম দা, আমি তুমি শুনতে পাচ্ছ না, আমরাও তোমাকে বলছি যে, কিন্তু তুমি শুনতে পাচ্ছ না, মানে ইউ আর অডিবল টু আস। ওকে ওকে। ইয়া।
Hello. Okay.
Yes, Arindam, we can hear you.
Okay. So can you? Sorry
Please
for this
continue.
glitch. Yeah. So all I was saying that. So basically, I am interested in this kind of decomposition of an ideal in the primary decomposition, where an ideal can be into intersection of ideals whose radicals are prime, and also those ideals have one more property, that is you take quotient with those ideals, then every element either a zero divisor or a nilpotent. This kind of decomposition is called primary decomposition, and this is going to be one topic of our interest. Can you take a slide show?
Yes.
So there are many nice uniqueness results as to these intersections. Basically, one of the primary unique that I want to underscore, the prime ideals that are from this kind of intersection, namely the radicals of those UIs, those are unique. Whenever you take you have to basically remove the redundant element. So if you take the irredundant decomposition of an ideal in this form, then the prime ideals you will get unique, whatever kind of decomposition you take. And by redundant, I mean you just basically remove the elements already whose sub-ideals are appearing there. So now another interesting property of this kind of intersection is that the radical I to begin with is radical ideal, that is I is I radical. Then I can actually be written as intersection of prime ideals themselves. So I will be intersection of a few prime ideals, and this in turn will be primary decomposition. Can you go to the next slide, please? Okay, before that, sorry, I just want to do an example of primary decomposition. You take this ID AB, BC, CD, DE. You take this ideal, and its primary function is the ideal generated by A, C, and D, intersection B and BD and E, C, A, and E, D, A, B, E, B, and C. So can you see a pattern here? I mean, we'll keep coming back to this example repeatedly all over the talk. So it's probably worth stopping for a moment and is there a pattern? Well, there is a pattern, namely if you draw a pentagon for one at a time, then these ideals are essentially you're taking one vertex and taking the opposite line, opposite side. So that's this decomposition. By the way, is my voice too low?
No, it's okay. It's perfect.
Okay. So here, one important is what are the heights of this associated primes? Well, height in this context means what's the length of the prime that reaches the highest length of prime chain starting from zero ideal that reaches that ideal. We'll elaborate on these things in a moment. Our first topic of commutative algebra that we will discuss in this text of combinatorial commutative algebra. Next topic is resolution. I need to explain this picture a little more. So see this big picture in the top. At the rightmost part, there is this ideal I, and then there is a map from I to everything going to 0. And suppose alpha 1, alpha 2, alpha a, k minimal generators of I. Now, obviously, since k minimal generators, you can take k many copies, that is direct f, direct sum s, direct sum s, k many times, and use a surjection onto I. Namely, the vector ei goes to alpha I. This will definitely gives you a surjection. Now, take the kernel of this surjection. This is Noetherian setup. This direct sum module is a finitely generated module over Noetherian ring, which is the polynomial ring. So every submodule is finitely generated. So this kernel will also be span of finitely many elements. Take a minimal generator beta 1, beta 2, beta k. Now again, beta 1, beta 2, beta k. Sorry, it should be s power k instead of beta 1, beta l. It should be s power l. I think I wrote s power beta. That's a typo. So from s power l, you will have a surjection onto the kernel, namely again EIX vector goes to beta I, and this surjection followed by the inclusion of kernel into this s direction k. This composition will give you a map D1 from S beta to S power alpha. Now, for the sake of simplicity, we'll call the first module as F0 and the second module as F1. But what we really gave you a construction which gives you a map from F1 to F0. The map is D1, and also a surjection from F0 to I, and then a surjection from I to 0. But D1 may have a kernel, and that will also be a generated module. So you keep this process going. At each stage, the kernel take its finite generating set and then surject from a free module of an appropriate dimension. You keep going, and there's a theorem called Hilbert-Szilagyi theorem, which says that for ideal polynomial ring, this process stops at finite step. So if the step is p, that is, if we stop at f position, then p is called projective dimension of I. Now look at these maps, VIs, that is from I to Fi minus 1. This is a map between free. So if obviously they will have a basis, so they have a matrix representation. If all the DIs, if apart from D, of course, if all the DIs have linear entries, then we called I has linear resolution. I mean, this linearity, when everything is every in DI is linear, is a case we want to study, because resolution becomes very simple in that case. Deviation from linearity is called Castelnuovo-Mumford regularity. So we are defining it in a rather unconventional way. If you go to books, they define it in a slightly different way. And the definition goes as, so the understanding is following. I is generated by certain monomials. So when you go to the next step, the kernel is expected to be generated at every stage. Basically, the kernel is expected to be generated by linear elements. However, from linear is our question. So basically, you take the maximum degree of a generator in the kernel in that step, subtract the index of the step, namely I, from that, take max these numbers, and then add D to that, where D is the ideal, where we are starting with I to be ideal generating degree D, 6 degree D for the die. Is a measure of being away from linearity, how much away from linear it is. So basically, linear, then what will happen is this regularity will be D. That's roughly, that's the understanding. Any question? I mean, I just gave a very, what shall I say?
Okay, so I have actually one question.
Different notions of, yeah.
Yeah, so is this definition of Castelnuovo-Mumford regularity is a particular thing? I mean, is it a specific Castelnuovo-Mumford regularity, or there is a more general definition of Castelnuovo-Mumford regularity? I think there is a more general definition.
Yeah, there are. I mean, this is definitely a special case. I'm giving you for homogeneous, as I wrote, homogeneous degree D. I am restricting myself severely here, and I'm doing, because to give a general definition Mumford regularity, either you need local cohomology or you at least define the notion of shifts, namely shifted polynomial rings. And I think uh, for the time being, if you definition for granted and give me this, so basically assume Castelnuovo-Mumford regularity is a measure of how much non-linear this resolution is, and it's a measurement of being of non-linearity, where linear means essentially at every stage these matrices DIs are linear, and if matrix linear, then there is already a constraint among the degree of the generators of kernels. So basically, how much far it is from that. I mean, that's essentially the measure of Castelnuovo-Mumford regularity. Very highly used, variant in commutative algebra. It also can be defined using Schiff or every other things. But for the time being, this working definition, the important thing to remember for our context, if I is an homogeneous ideal generated in a fixed degree D, the best possible scenario is regularity of I is D. If it is D plus 1, it is little. If it is D plus 2, it's little further worse, and so on. So it has linear if and only if regularity is D. So that's where, for today's talk, it won't hurt if you start from that.
Okay.
Any further? Yeah, sure. Next slide. So as I was talking to Saurav, if I is a homogeneous, that is, for example, generated in degree D, then I has a linear resolution if and only if regularity I equal to D. So let me give you an example. Just the previous example itself, take where I use ABCD. Hello?
Hello, yeah, carry on.
Yeah. Here I'm using x1, x2. Suppose I is x1, x2, x2, x3, x3, x4, x4, x5, x1. If you write down the resolution, I mean, I have used all two, but this is even, I think, doable using your hand. You can see that resolution looks like following. I have 5 generators, so the first definitely need a free module of rank 5. And if you take the kernel and search into that kernel, you'd actually see the first matrix is indeed linear. It consists of entries, zeros and linear entries. However, the second matrix needs quantities. So this is not linear. The resolution here is not linear. You can cut projective dimension here is 2 and regularity is 3. So since I is quadratic, if it had to be linear, then regularity had to be 2, just 1 off. So question obviously is when regularity equal to D. I mean, that is when the resolution is linear. That's a very important thing to study. So here, basically what happens is the following. Now I will get combinatorial stuff. So generally speaking, explicit questions or doing explicit computations in general is hard in algebra. The purpose of introducing combinatorial structure is that you can somehow exploit the combinatorial structure and actually do some computation. For example, for a big group of ideals, can you say ideal indeed has linear resolution? Or if not, can you say exactly the regularity is? And the same goes for associated primes. I mean, for a given class of ideas, can you explicitly define associated primes? And for this explicit part, combinatorial come into picture. Can you go to the next slide, Saurav?
Yeah. Oh, wait. Yeah. Sorry.
Okay. Now I'm going to ideal part. Suppose S be the same polynomial ring, G be a finite, simple, undirected graph on x1, x2, xn. That is, s of G are x1, x2, xn. Now, a big thing is happening. variables x1, x2, xn are now they also have another interpretation, namely they're vertices of a graph. And finite simple undirected, what does that? Well, undirected means basically there is no arrow on the edges. There's source and sink. It's arrow, an edge is just a connection between two vertices. Also, no loop. No vertex can be connected to itself. By the way, loop is not a circle. Loop means a self-joining edge. No vertex, no edge has the property that both vertices are same. And also no multiple edge. That is between two vertices, there can be one edge or no edge, no other choice. An induced subgraph of G is a finite simple graph such that its set of vertices is a subset of set of G, and the edge set, that subset of vertices remains unchanged. That is, take a few vertices from vertices of G and keep the edges intact. I'm just explaining an example. If look at this picture, G, this triangle with two antennas. The bottom triangle is definitely an induced subgraph, but if you take, instead of the bottom, take the bottom triangle and erase the bottom edge, subgraph you get is a subgraph, but it's not an induced subgraph because you have erased the edge which was there in the original graph. So this induced structure keeps playing an important role. So I thought it will be easy to define it right away. Regarding resolution, even associated prime, edge ideal, induced subgraph, because I've already defined 4 important notions that I'm going to play with throughout the talk.
Acha, excuse me, I have one question. This is what is this in the slide? I mean, take some vertices, keep the edges intact. Can you please explain?
That's the definition of the induced subgraph.
Okay. Yeah, I got it. Yeah. Thank you.
Yeah, okay. You take some vertices and keep the edges intact. Yeah.
Okay. Yeah. Thank you.
So now we're in a position to define edge ideal. Edge ideal, IG of G, basically, now that the way we have defined, each edge is a monomial of the xj. So basically, it's the ideal generated by edges. And clearly, there is a 1-1 correspondence between finite simple graphs and square-free quadratic monomial ideals of S. And this 1-1 correspondence is something that is explored quite a lot. So just to give you an example, I'm just using the 5 cycle again. You have x1, x2, x3, x4, 5. Then the edge ideal is x1, x2, x2, x3, x3, x4, x5, and x5, x1. Can you move up a bit? Yeah. As we discussed, the associated primes of this, as we saw before, is something like x1, x3, x4, x2, x4, x5, x3, x5, x1, x4, x1, x2, and x2, x3. As I asked earlier also, is there a pattern? And if you close your eyes for a moment, and I'll just readily say that the pattern is essentially what you are taking is that you're taking x and taking the opposite edge. That's it. That's the pattern. That's 5 cycles. Does this say something about in general? For a general finite simple, can you say what are the associated primes? We'll see it in a moment. Can you go up? Edge ideal obvious monomial variables. So every square-free monomial ideal can be written as intersection of ideal generated by variables. One can trivially check that ideal generated by variables are prime ideals. That is, all associated primes are generated ideals. What can you say about associated primes of an edge ideal? Now you see, associated prime is a prime ideal contains IG. At the very least, it's a prime ideal. So if a quadratic monomial xi xj is there in that prime ideal, then the variable has to be there. So if xj is an edge and an associated prime, then either xi or xj is in P. The question is, that's a necessary condition. Anything else explicitly defines, describes edge ideal, associated primes of edge ideal. Associated prime of edge ideal is all satisfying that property such that no proper Q satisfies that. That's it. So associated prime basically ideals generated by variables such that for every edge one vertex is there in that, and if you take a CL of that ideal, there is at least one edge for which neither of the vertices are there. So that's the complete associated primes. But from graph theoretic point of view, this is basically what minimal vertex covers are. A minimal vertex cover in case of graph is just vertices. A vertex cover, in fact, in a graph is just a set of vertices such that for every edge there is one vertex in that set. And a minimal cover is a vertex cover such that no proper subcover or per subset is a vertex cover. Now, minimal vertex covers are extremely important in combinatorics and computer science. They actually play quite an interesting role in optimization theory, and they, on right, they're very much interesting because they have many interesting purely mathematical properties. But one important thing is computing these minimal vertex covers. These algorithms are generally NP hard. However, why people are interested? I mean, as I said, there are many interesting applications, and recently I actually came to know there are lots of applications of minimal vertex cover problems even in biological network theory. So I mean, I don't want to discuss too much application. If anybody is interested in application, I can do that after the talk. But I just want to talk about these things just to address the importance. But another thing I also want to say that if G doesn't have an induced graph of this form, which is bipartite graph, one side one vertex, another side three vertex, then these algorithms, the computing minimal vertex covers, they are actually polynomial time algorithm. Now, explicit computation of primary decomposition for ideals in polynomial ring, that's actually a problem in commutative algebra. I mean, people really want to know how to compute stated primes. But unfortunately, most of general algorithms forget about being polynomial or NP. They use Grobner basis, so they or I think they're double exponential. So these algorithms, in case of general commutative algebra, is very good. But for example, in case of combinatorics, just we saw that if as long as the graph doesn't have this k13, you can compute it in polynomial time. So this is one demonstration how combinatorics can possibly be exploited to give quicker and concrete answer to algebraic question. Maybe in a restricted set, one can exploit them to give some satisfactory answer. Uh, in case of associated primes, one important question is when is IG unmixed? Well, I mean, I'm just basically, in general, mixed means all associated primes have same height. In case of Arial, the definition simply translates into for what are the graph have this following property that all minimal vertex covers have same size. In general, that is in general for ideal polynomial ring, this obviously is a character dependent ideal, a characteristic dependent property. The characteristic of the field because the primary decomposition might change. However, in case of edge ideals, as you see, that really depends on the minimal vertex cover structure of the underlying graph is characteristic free. So once you prove it for one field, true for all fields. minimal vertex, all minimal vertex covers is same. It's generally difficult to give an exact description of unmixed graphs. Well, what I mean by unmixed will be clear in a moment. But for bipartite graphs, there is an explicit description. Uh, and this is a theorem proved by Villarreal. G is bipartite graph without isolated vertices, unmixed, if and only if there is a bipartition. By the way, all of you are familiar with the notion of bipartite, right? I can hopefully I don't have to define that. Anybody who's sure of any question regarding bigraph?
Yeah, no.
Okay, great. So G is a bipartite graph without isolated vertices. G is unmixed if and only if there exists a bipartition x1, x2, xg and y1, y2, yg have to be same size so that xi, yi is in eg. If xi, yj and xj, yk is in eg, then xi, yk to be in eg. As concrete as. Note that giving you some example. This graph is mixed, this bipartite graph, because there is a height 2 prime x1 y3. Note that if you have x1 y3, you cannot go far, go smaller than that, and for every edge it either contains x1 or y. That's a vertex cover, and also that's basically a minimal prime of that, so it has to be minimal primes associated. And also there is a height 3 prime x1, x2, x1, x2, x3. You cannot go smaller than that either. So this definitely is not unmixed. However, because of this previous, the next example will be unmixed, and that all we need is just to join one in that. This is unmixed. I mean, you can check this bipartition itself, like one x2, x3, are satisfying Wheeler. This is I thought about I some of my time got wasted this connectivity issue. I don't know how much I will be able to do, but I thought about give of Villarreal's theorem because this is fairly accessible and will give you an idea how a theorem like characterization for unmixedness can be proved. So let me quickly go through the proof. Yeah, the slide please show up. The whole slide. Yeah, if you can make it. So the first, this direction. One thing you should right away notice that each bipartition is actually a vertex cover. I mean, you cannot get rid of any of the xi's or yi's because there is no isolated vertices. So if you take all the xi, well, since it's bipartite, if you take all the xi's, that gives you a vertex cover. All the edges are have one x vertex and one y, and you cannot, once you take all the xi's, you cannot drop them because it's a no isolated vertex. So the vertex you're dropping, that's part of an edge, but then you're not any of the yi's. So if you drop that vertex, you're not taking any of the vertices of that edge. So basically all these, both the bipartition, they are minimal vertex covers. So definitely they must have same size. X's and y's have same cardinal. This I'm using one theorem by Koenig, which you can read from maybe Harare or GPUS basic graph theory book. The G is also maximum number of independent edges. By independent edge, I simply mean a bunch of which doesn't share a vertex. That's it. So maximum number of such things you can do. This is sometimes also called matching. So maximum matching basically. So since G is maximum number of independent edges or max size of maximum matching, that essentially get after permutation if needed, edges x1, y1, xg, yg. That set already satisfies the first variant. Now take x1, xi, and xj, yk, where ij, k are distinct. If xi, yk, this edge is not there. I mean, remember the third end of Villarreal. That's what I am trying to prove. That if xi, yj is an edge, xj, yk is an edge, xi, yk has to be an edge. That was precisely what was missing in that one example of non-un. And I'm trying to prove that if that's there, then it has to be un, basically. So suppose this is not there, this edge ayk is not there. Then if xi yk is not there, there exists a vertex cover without xi or yk. Call it C. And well, xi yk is not an edge. So take all the vertices other than xi and yk. That covers all the edges. So that gives you a vertex cover. And every vertex cover contains a vertex cover. Just like you take an ideal and take a prime ideal containing that ideal, then there exists a minimal prime of that ideal sitting inside that ideal. I mean, this is exactly the argument. So, but then by construction, xi and yk are not there, and xi and xj, yk are edges, both xj and yj be in C.
Arindam, sorry to interrupt. You have 10 more minutes.
Sure. Oh, okay. So, well, at all L not equal to J, at least one of XL or YL must be, then size of C is greater than or equal to G plus 1. Just gives a contradiction. Similarly, the other side, if suppose those conditions are satisfied, if C is a minimal vertex cover enough to show that C intersects with each xi yi exactly at x, assume both xi and yj belong to C. That is the neighbor xi of there is a neighbor of I, neighbor xi of yj, and there is a neighbor yk of xj, such that I not equal to j and k not equal to j, such that these both of these they do to C. Can you go to the next slide, please? If I equal to k, then xi yi do not is not covered by C. That's a contradiction. Otherwise, by second criterion, xi yj is an edge and xj yk is an edge. So we get xi yk is an edge. It's not covered by C, which is also a contradiction. So this is how this whole proof is achieved. I mean, this is as simple as this. So one more property in this topic. I mean, I'll rush through the next topic quickly, but just let me discuss this. So depth of S mod Ig is just number of vertices minus projective dimension of minus 1. Experienced commutative algebraists and algebraic geometer gave me for this definition. So I just saw a question. Can I take the questions afterwards since I just lost some time?
Yeah, yeah.
Or
Yes, yes. You can
So
address the
basically,
questions afterwards.
yeah. So basically, Ig is called coherent if Ig is unmixed and height of is associated primes. The common height is just vertex covered. Height of this associated primes, that is minimal vertex cover, is projective dimension of Ig plus 1. So this comes from something called Auslander-Buchbaum formula. Actually, depth is also a measure of size like Krull dimension. So what we are doing essentially something is Cohen-Macaulay if depth and Krull dimension same. In general, even for graphs, this is characteristic dependent. However, for bipartite graphs, it is characteristic independent. There are characterizations of this Cohen-Macaulay bipartite graphs. One, and the most by Herzog and Hebe, it's exactly like the unmixed, but you need one more condition. You have the same criterion. You have a bipartition of same size, such that xi yi is an edge, and also that condition xi yj yk edge implies xi yk an edge. Other than that, you also condition that edges go downward from x to y. Namely, if xj is an edge, then I has to be less than or equal to j. So once this fixed, it's bipartite, it's Cohen-Macaulay, and also other way around. So there is one more characterization of Cohen-Macaulayness I want to discuss. But before, I just have to give one quick please go. Please. Okay, so let me quickly define what colon ideal is. I colon A is just R, such that R A belongs to I. This is an ideal readily checked. So if Ig is an edge ideal, M is a minimal generator of Ig power S, then we have in characterization. Ig is a sub-ideal of Ig power S plus 1 colon M. Ig power S plus 1 colon M is actually a quadratic ideal. Further, if G is bipartite, then Ig power S colon M is actually bipartite edge ideal with same bipart. So we use this Vivek Mukundan to give this characterization of Cohen-Macaulay bipartite graph. G is bipartite. G is bipartite. G is Cohen-Macaulay if and only if G is equal size bipartition, and there exist exactly edges E1, E2, Eg, such that Ig square colon E is Ig. So you will have exactly G edges, a bipartition, and exactly G edges just such that the Ig square with that edge is itself. So that's the overall glimpse of associated primes and unmixedness Cohen-Macaulay problem, ideal, and how combinatorics plays a role. Can I get 5 more minutes? Shruta?
Yes, you have.
Okay. Next, I want to discuss regularity, and we already defined what regularity is. And let me quickly describe how, in case of edge ideal, regularity is dependent on combinatorics. A classical result by Froberg, and by the way, I heard that this by combinatorial topologists from earlier generation also. Ig has linear resolution, that is, regularity of Ig is 2, if and only no induced cycle in the complement graph other than triangle. That is, G complement we allow triangle, but we don't allow induced 5 cycle or 6 cycle or induced cycle. What's an induced cycle? Well, it's an induced subraptitious cycle. So Herzog-Hebbian proves a property that if Ig has linear resolution, then Ig power S has linear resolution for all greater than equal to 1. Now, this is an extremely strong property. General for ideals, I having linear resolution says nothing almost their powers. I mean, but for edge ideal, I having linear resolution determines that powers have linear resolution. Conversely, Francisco Ha et al. Also proves the following result, that if any power of Ig has linear, then G complement does not have an induced 4 cycle. It is, by the way, let me caution that it is not true that if all higher power linear resolution, then Ig must have linear resolution. For example, take this 5 cycle, it have linear resolution, but all its powers, second power onward, have linear resolution. So the converse, what will be the converse of Herzog-Hebbian's theorem is some, it's still people are trying to work on that direction. Next slide, please. A while, people actually believed that the converse of Francisco Ha-1 is true. That if there is no 4th cycle in G complement, then all second power onward has linear resolution. For a while, people believed true, but unfortunately, a counterexample came up. The counterexample is something like an graph with 20 vertices and 100 and something edges. This was dug up using computer programming. So there's no way one can randomly run into such a counterexample. And the triangulation of sphere, more construction are involved in that. So based on all these studies, there was a conjecture by Nevo and Piva that no induced 4 cycle complement and regularity Ig less than equal to 3 implies regularity of Ig power S equal to 2S for all S greater than equal to 1, 2. This conjecture is still open. Well, it's sort of open. I mean, progress has been made, but in its full generality, it's still open, this conjecture. So some theorems regard in this direction was done myself in my thesis that if G complement has no induced force cycle, regularity of Ig power s is less than equal to 2s plus regularity of Ig minus. If G is also induced this structure free, a triangle with two antenna, then for all s greater than or equal to 2, regularity power s has linear resolution. Also, fairly recent in another work by joint with Nevo, can you go up a little bit? Prove that if for all G, for all graph G, regularity of Ig square is less than or equal to regularity of Ig plus. And if G is bipartite, regularity of Ig power s is less than 2s plus regularity of Ig minus 2. Now look at the previous theorem. We have 2s plus regularity Ig minus 1, and here we have regularity of Ig 2. 2s plus regularity of Ig minus 2 is the best bound you can due to Froberg's formula, and generally people tend to prove that for as larger classes of graphs as possible. But Sophie's bipartite is something we got. Just quick definition. A set of edges in G is called matching if no two edges are vertex. At a vertex, at a matching is called induced matching. Amongst those vertices, only those edges belong there. There are no more edges amongst those vertices. Just an example to demonstrate what's an induced matching. Go up, Saurabh. Take this graph, AB and EF, where there is an CD and EF are edges and connected. If you take AB and EF, this is an induced matching. Because first of all, they don't share a these two edges don't share vertex. No edge amongst them. However, if you take AB, CD, and EF, that doesn't give you an induced because there is an edge AD. However, nevertheless. So size of the maximal size of a matching is string number, and maximum size of induced matching is called induced matching number. Yeah, next slide, please. I just have only 2 more slides. Yeah. So Jayantan and Selvaraja, A.V. Jayantan and Selvaraja, the following result. If height of Ig is exactly equal to of vertices divided by 2, then regularity of Ig power s, actually they can give an explicit formula. Formula is 2s plus induced matching number minus 1. The reason we define that this formula, this theorem by Jayantan and Selvaraja states that, can you go up a little bit, Saurabh?
Yeah.
This theorem demonstrates how matching numbers and induced matching numbers they play important role in case of regularity. And one final slide. So basically, there is this result by Bayerslan, Ha, and Chung that just like Jayantan and Selvaraja gave this using induced matching number, that formula in general is actually a lower bound for all graph. In case of all graph, that's a lower bound for regularity of Ig power s. And finally, instead of induced matching number, if you take matching number, me, Bayerslan, and how we get that gives you an upper bound. So essentially, 2s plus induced matching minus lower bound for regularity of Ig power s, and 2s plus matching number minus 1 gives you. So this is a conjecture. It has been observed by many of us. We believe that regularity of Ig power s is equal to 2s plus regularity of Ig minus 2 for all graph. So we have it for bipartite and several other classes. And due to Froberg and Herzog-Hibby-Jeng, this is basically the best possible bound one can get. Okay, I'll stop my talk right here and the technical glitch and this handwritten slides. Thank you.
Okay, thank you. Thank you, Arindam. Can you address one question that was raised by Orpon, I guess, over chat, very quickly?
Well, Hilbert-CCG theorem can be applied for Hilbert's CCG theorem is true for polynomial rings. So mostly we study ideals over polynomial rings and modules over polynomial rings. So for these cases, anyway, Hilbert's CCG theorem is true. If Hilbert's CCG theorem is not true, that namely if you take a module with infinite solution, you can define Castelnuovo-Mumford regularity for sure, but that may not be fine.
Okay, thank you. So anyway, it was raised by Oisik, but anyway, Arpon pointed out it. Thank you so much. So we organizers also reminded us that we have to go to the Zoom link for the next talks, and we can meet at 11:05. Saurabh.
We can. Yeah.
Yes.
Yeah.
So let us shift to the Zoom link given by our organizers.
Yeah, so the Zoom link is provided in the chat box. This is to inform everybody we are moving to the Zoom for the next session. So all the
Yes,
yes.
I think she's here.
She is trying to join here. Yes.
She's already here.
Preeti, are you here? Can you hear us?
She is trying to join here.
Yeah, please add her as a co-host. Otherwise, she
How
won't be
can
able
I?
to join.
Shomo will do that.
Okay.
You cannot unmute.
Soma, yeah. Kriti, now you can share your screen. You can unmute yourself and share your screen.
Yeah.
Okay.
Yep. Please mute yourselves.
Not the speaker and the chair, rest of us.
Yes, please go to the full screen. Yes.
Is this visible perfectly?
Yes, yes.
Yeah. Am I audible?
Yes, yes.
Okay, that's good.
So we'll start in few seconds.
Sure.
Yeah. So welcome again, everyone. Professor Barik will chair this session. Let's start this session again. Yeah.
Yes. Preeti, are you okay? Hello.
Yes.
Yes. So can you go to the first page of the slide?
Yes.
Okay. So next, welcome back. Next speaker
Yeah,
is Kriti Goel from Indian Institute of Technology, Bombay. She will speak on characterization of F-rational rings using tight Hilbert polynomial. Kriti, please.
Thank you. Hello, everyone. Thanks for joining in. I'm Kriti Goel from IIT Bombay. And firstly, I hope everyone is safe and sound. And I would like to thank the organizers for giving me this opportunity to talk, and also for organizing this conference in these difficult times so that we can learn more mathematics. I'll be talking about characterization of F-rational rings using the tight Hilbert polynomial. And it's a joint work with Vivek Mukundan and Jugal Verma. So let's begin with some notations and definitions. So for us, R will be an I will be an M-primary ideal. So given a sequence of ideals I sub n, we say it is an I filtration if it satisfies the following three properties. Firstly, it should be a descending sequence of ideals. Secondly, it should satisfy the grading property. And finally, it should satisfy the property that the nth power of the ideal I should be contained in I sub n. Moreover, if an I filtration satisfies this property that there exists a natural number k such that I sub n is contained in n minus kth power of the ideal, the filtration is said to be admissible filtration. So what is a very common example of an admissible filtration is looking at an I-adic filtration. This means given an ideal M primary ideal I, we look at the nth power, the sequence or the set of ideals which consist of nth power of the ideal I. Now the other interesting or most sought after filtration, which is admissible, is an integral closure filtration. Let me quickly define what it is. So an ideal I is said to be, given an ideal I, the integral closure of I, which we denote by I bar, is a set which consists of all those elements X in the ring, satisfying an equation of the particular form, where these coefficients come from the corresponding powers of the ideal I. So if we consider the collection of the integral closure of powers of the given ideal I, this forms an admissible filtration if the ring is analytically unramified. So this characterization was given by David Rees. Let me recall here, by analytically unramified, we mean that the M-adic completion of the ring is reduced. What he proved was the following. He said that a ring is analytically unramified local ring if and only if the collection IN bar is an I-admissible filtration, and this is true for any M primary ideal I. So what properties do admissible filtrations have that we can use? So associated to an I-admissible filtration F, let's say suppose the dimension of the ring is T, we associate a length function to this filtration, which we call as the Hilbert-Samuel function of the filtration F. This is precisely length of R over I sub n. And it is popularly known that this length function is actually a polynomial function. This means that there exists a polynomial with rational coefficients of degree d. We call this polynomial as the Hilbert-Samuel polynomial of the filtration, and this means that the function and the polynomial coincide for large enough values. So this was a general introduction. But then we want to target a specific closure operation in characteristic P, which we call as the tight closure operation, and further study it. So let me recall the definition of tight closure. So as I mentioned, we'll be dealing in characteristic P. The ring is a Noetherian ring. By Q, we mean the prime power. So Q is P to the E, where E is a natural number. So if we have an R ideal I, by I bracket Q, we mean the eth Frobenius power of I, and it is the ideal generated by A to the Q, where A varies over all the elements of the ideal I. One more notation. By RO, we mean the complement of union of all minimal prime ideals of the ring R. And in this setup, the tight closure of the ideal I is defined as a collection of all those elements in the ring, such that there exists a C in RO, such that C times x to the Q is in the eth Frobenius power of the ideal, and this should hold for all large Q. Moreover, if I is equal to I star, then the ideal I is said to be tightly closed. Next is a very interesting containment relation. So we started the tight closure. We looked at the tight closure. We looked at the integral closure of the ideal. And this is an interesting containment relation, which is true for these closure operations. I is always contained in its tight closure, which is further contained in its integral closure. So a very quick example of tightly closed ideals is integrally closed ideals. This means if an ideal I is equal to its integral closure, then it's also equal to its tight closure. Other trivial examples or quick examples using this observation is when the ring is a regular local ring. In this case, if you pick any ideal, it's tightly closed. This requires flatness of Frobenius functors and various other things. The other example is a consequence of Price-Kongsberger theorem. And it says that if we have a principal ideal, then the tight closure and the integral closure of the ideal coincide. So now once we have defined the closure operation, what we want to do next is the following. We want to look at the tight closure of the power of the M primary ideal I, and then see under what conditions it is an admissible filtration, and then proceed further. So we actually figured out that under certain circumstances, it is indeed an admissible filtration. So what are the assumptions under which this happens is the following. So the ring is a d-dimensional, analytically unramified local ring with prime characteristic P. I is an M-primary ideal, and T is a collection of tight closures of the powers of ideal I. Then in this case, we prove that T is an admissible filtration. This means when we look at the Teichel-Hilbert function, which is length of R over I n star, it is a polynomial function of degree D with rational coefficients. We call it as the Teichel-Hilbert polynomial. We call it as the Teichel-Hilbert polynomial. And if the expression of the Teichel-Hilbert polynomial is written in this particular form as a linear combination of the binomials, then the leading coefficient is called the multiplicity of the ideal. And of course, all the other coefficients are called the Teichel-Hilbert coefficients of the ideal I. And the coefficient we'll be interested in looking at the stock is even star of I, which I'll explain later. But the next thing I would like to define and shift focus to are F rational rings, because these are the rings we want to characterize using these coefficients. So let me quickly define what F rational rings are. So again, a ring is Noetherian. It has prime characteristic P. We say an ideal I is of principal class if it is generated by height I number of elements. And in this particular setup, the ring is said to be F rational if ideals of principal class are tightly closed. Now, these F rational rings also have certain interesting properties. These properties help in characterization of F rational rings, and also, of course, they help in building up more examples and in checking various examples. I'll just mention a few properties here to give you a feel of F rational rings. So we assume R is either a locally excellent ring or it is a homomorphic image of a Cohen-Macaulay ring. In this case, the ring is F rational if and only if it is equidimensional and there exists a parameter ideal which is tightly closed. What is interesting to observe here that we only need to check for one particular parameter ideal. As a quick corollary, one can also see that if R is a Cohen-Macaulay ring to begin with, then it is F rational if and only if there exists one parameter ideal which is tightly closed. This means it's enough to check just one to see if it is F rational or not. The other characterization is when its localization at every maximal ideal is F rational. So let me mention here, we have not assumed Cohen-Macaulay localness over here, but let's say if we have a local ring and we have a non-zero divisor X in the maximal ideal, such that the quotient ring is an F rational ring, then the ring will be F rational. Unfortunately, the converse of this statement is not true. This means that R being F rational will not say that the quotient R mod XR for a non-zero divisor X is F rational. This and a few more examples I'll illustrate next. So the first one is quotient of the polynomial ring Kxyz by the element x square minus y cube minus z to the 7. K is a field and it has a prime characteristic P. We pick an ideal I, which is ideal generated by y comma z. Now observe here that this ring is a Cohen-Macaulay ring. The ideal I is a parameter ideal. And of course, small y and z are images of capital Y and z in the ring R. So in order to check this ring is F rational or not, it's enough to check that the ideal I is tightly closed or not. And one can easily check that the element X, which is not an element of I, is in the tight closure of the ideal. And since it's a parameter ideal, we get I is not tightly closed, and hence the ring is not F rational. So while it might seem easy to check whether a ring is F rational or not, this might be an example in disguise, because even a same ring with different characteristic might behave differently. And this is what the next example illustrates. So we have a quotient of a polynomial ring Kxyz by x square minus y cube minus z5. K is a field, and again I is the ideal generated by y comma z. Small y and z denote the images of capital Y and z in the ring Again, in order to check the ring is F rational or not, we just need to check if I is tightly closed or not. So these two examples I've picked up from Brunson-Herzog, chapter 10. If you're interested in looking at the details, please, you can go back to the book and see the details. Example 2 requires some work, and this is what it's proved over there. They prove that X is not in tight closure if and only if the characteristic of the base field K is strictly bigger than 7. So this computation is characteristic dependent. In particular, it is proved that the ring is F rational if and only if the characteristic is at least 7. Okay, so this was the background details of it. Let's come to the main topic. We want to characterize F rational rings using even star of I. But why even star of I? So this coefficient is what is called as the Chern number of filtration, and this is not the first time that people have looked at the coefficient and used it to characterize rings. This has happened in the past. Of course, there's a good amount of literature and history of results where people use vanishing or bounds on these coefficients to study or to characterize rings. So I'll quickly recall here. If we have an admissible filtration and we have Hilbert-Samuel polynomial P sub f of x, and we have the following expression, then the coefficient E sub 1 of f is called the Chern number of the filtration. And as I mentioned, there are some results in the history which I would like to quote here. The first one is by Giese and few more people in 2010. They characterize Kuhn-Macaulinus of a ring using the vanishing of even Q for some parameter ideal Q provided that the ring is unmixed. In the same year, Goto and Ozeki proved that the ring is Buchsbaum local ring if and only if it is unmixed and even Q is constant, and also it is independent of choice of parameter ideal Q and R. So before I proceed to the main theorem, there are small results and lemmas which we'll use in the main theorem, and of course they are interesting their own individual respect as well. I'll quickly quote them and then proceed towards the main theorem. So this is what is called as the intersection theorem for tight closure. So a version of this theorem for integral closure, and of course a motivation for this theorem comes from a result of independent result of Huneke and Ito, where they proved this result for integral closure filtration. Prime characteristic P, I is ideal generated by regular sequence. We proved that for all n bigger than or equal to 1, the following intersection condition holds. And as a consequence, we have this theorem by Watanabe, suggested to us by Watanabe. And it says that, of course, under the above restrictions that we have an Noetherian ring, prime characteristic P, ideal I generated by regular sequence, then the ideal I being tightly closed implies that all its powers are also tightly closed. So we use these two results and prove the main theorem, which is as follows. So we assume that Rm is analytically unramified Cohen-Macaulay local ring, prime characteristic P. Then the ring is F rational if and only if even star of I vanishes for some parameter ideal I. I would like to emphasize here that we only need to check it for one particular parameter ideal I. Since it's a very short proof, I'll quickly give the proof. So let's look at, yes, sir.
So we have very 1 minute, I think you can take at most.
Yes, sir. It's about a minute. Yeah, thanks. So let's look at the forward part. Let R be F rational and we pick a parameter ideal I. We need to show that even star of I vanishes. But by definition, I being parameter ideal and R being F rational will imply that the ideal I is tightly closed. And by the previous slide, the result of Watanabe, we get not just I, but all the powers of I are also tightly closed. This means when we look at the tight Hilbert polynomial of the ideal, it coincides with its Hilbert-Samuel polynomial. And this will say further that the coefficient E1 of I, which in this case is even star of I, vanishes. So this is the forward part. For the backward part, let's say we have a parameter ideal I such that even star of I is 0. We need to prove that the ring is F rational. So in order to prove this part, you look at what is called as the Northcott inequality. This was proved for filtration by Hakama and Marley, and this is the following inequality. In our case, even star of I is 0. E0 star of I is the multiplicity of the ideal. Since the ring is Cohen-Macaulay and I is a parameter ideal, E0 star of I is precisely length of R over I, which gives us the left side inequality. Since I is contained in I star, we have the right side inequality. These two combined say that length of R over I is same as length of R over I star, and hence these two ideals are equal. So now we have a ring which is Cohen-Macaulay. We have a parameter ideal which is tightly closed. This will say that the ring is F-rational. So this completes the proof of characterization. These are references, and thank you. Yeah,
Okay,
I'm
thank you
open for questions.
Thank you so much. And we don't take any questions because we have to wrap it up for the next talk. Thank you.
Okay,
Thank
yeah,
you,
sure.
Kriti. So,
Thanks. Should I
Saurabh,
stop?
yes,
Thank you.
please.
Yes.
So next speaker, I think Sudeshna, can you
Sudeshna Roy.
share? Yes, Sudeshna Roy, can you share your slide, please?
I think she is here.
Okay, okay.
She was here, but now I don't see her.
Can see.
She's here.
Yeah, she is here.
So just please unmute yourself and start sharing your screen. Sudeshna,
Go to the full
just
screen.
unmute yourself and start
Yes.
sharing your screen.
Is it visible?
Yeah.
Yes.
Okay. And my voice is also clear, no? I mean, there is no issue.
A little louder would be better, perhaps.
Okay, okay.
So we'll start in few seconds, Sudeshna.
Okay, okay, thanks.
Okay, welcome back. The next speaker, Sudeshna Roy from Chennai Mathematical Institute. She will speak on graded components of local cohomology modules. Sudeshna, please.
Thank you. And also, I would like to thank all the organizers for giving me the opportunity to speak here. So today, I'd like to talk about the behavior of graded components of local cohomology modules. This is a joint work with Professor Tony Joshi-Pradhan-Purakkar. And let me start by defining the main object, that is the local cohomology module, which was introduced by Grothendieck in 1960s, and it is a fundamental tool in commutative algebra and algebraic geometry. So let C be a commutative Noetherian ring, I be an ideal in C, and let L be a C module. Then by gamma I of L, we are denoting the collection of all elements in L which are annihilated by some power of I. So this gamma I is known as the I torsion functor. One can check that it is left exact. The ith right derived functor of gamma L is called the ith local cohomology module of L with respect to I, and it is denoted by HII of L. Now let T be a standard graded Noetherian ring. T plus denotes its irrelevant maximal ideal, and let L be a finitely generated graded T module. then a large number of work has been done in dealing with the behavior of the local cohomology module of L supported on T+. Particularly, they are well behaved, and for instance, I mean, its every graded components are finitely generated T0 module, and for large positive values of U, its graded component vanishes. So vanishing of this local cohomology module is used to define one fundamental invariant, the Castelnuovo-Mumford regularity. There are some other applications in the study of Hilbert coefficients, Ries algebras, associated graded rings, and many more. So in consideration of this, it is quite natural to expect that such behavior carried out by local cohomology modules supported on arbitrary homogeneous ideals. But it is known that it is not true in general. So let's look into this example. Let T be a polynomial ring over any commutative Noetherian ring A in two variables, and let I be the homogeneous ideal generated by the single element X. Then every graded component of the first local cohomology module of T supported on this ideal X generated by X, they are free but not finitely generated for all U(J). So this example also says that for large positive values of U, this local cohomology module does not, these components of this local cohomology modules does not vanish. Now let's change our setup. So let R be a polynomial ring in n variables with degree of xi is 1, and the degree 0 component is a regular ring containing a field of characteristic 0. Puthenporagal studied the local cohomology module of R with respect to this arbitrary homogeneous ideal I, and surprisingly, he found that they are notably well behaved. So he mainly studied the numerical invariance of the components of these local cohomology modules as U tends to infinity and as U tends to minus infinity. So here I would like to highlight that these local cohomology modules are really finitely generated, but still there are some finiteness properties of this local cohomology module which were obtained by Huneke and Sarf, and later by Lubezny in prime characteristic and in characteristic 0. When the base ring is regular, so it's quite natural to start with a regular base ring. But then we tried to extend some of his results to a relatively wider framework when R0 is any commutative Noetherian ring containing a field of characteristic 0. We further showed that, we further gave some examples which shows that these results other results are not true if we don't consider R0 to be regular. So now for the next part, I will be assuming, I will be denoting this local cohomology module of R by M. So here another more thing is that since I is homogeneous ideal, so there is an induced reading on this local cohomology module. So it is graded. Now I want to summarize our results. So let C be a commutative Noetherian ring, J be an ideal in C, and L be a C module. Then it is well known that the jth local cohomology module of L with respect to J that vanishes for all J strictly greater than its dimension and for all J strictly less than its grade. But if J lies in between the grade and the dimension, it is difficult to tell whether this local cohomology module vanishes. Our result says that if almost all graded components of local module vanish, this local cohomology module vanishes. It further says that if the local cohomology module is non-zero, then either its weight graded component is non-zero for infinitely many small negative values of U, or its weight graded component is non-zero for infinitely many large positive values of U. So Brodmann and Hellas, they raised the most challenging problem regarding the asymptotic behavior of the local cohomology module, which is known as the tameness problem. So we say a module L is tame if there exists some integer U0 such that its weight graded component is 0 for all U less than equals to U0, or else its U8 graded component is non-zero for all u less than equals to u0. Now, similarly as earlier, if we take T to be a standard graded Noetherian ring and L a finitely generated graded T module, then they asked whether this ith local cohomology module of L with respect to this irrelevant ideal, whether it is stem. This question was answered affirmatively in many cases, particularly when dimension of T0, that is the base ring, if that is less than equals to 2, and when this I is the cohomological dimension of L with respect to T plus. So cohomological dimension means that I is the largest I such that this local cohomology module is non-zero. Later, Kartkowski and Harjov, they constructed an example to show that this question has negative answer if the dimension of T0 is 3. So what we obtain that if U8 graded component is non-zero for infinitely many small negative values of u, that happens if and only if its U8 graded component is non-zero for all u less than equals to -n. Again, U8 graded component of m is non-zero for infinitely many large positive values of u if and only if its U8 graded component is non-zero for all u greater than equals to 0. So here, I mean, as we have seen in the previous slide, that if m is non-zero, then one of these two situations will occur. And we also need to consider the second case, because we have seen that if instead of t plus, we are considering so instead of t plus, if we are considering any arbitrary homogeneous ideal, then for large values of u, its graded component may not vanish. So we need to consider this second situation to check temness. Now, Karti and Harjov gave another example of a standard graded Noetherian ring T, where T0 is normal, three-dimensional, non-polar with a ideal n, such that 12 volt for the local cohomology module of T with respect to the extension of the maximal ideal n. So here notice that if instead of polynomial ring, I mean under our assumption, if we take arbitrary standard graded Noetherian ring, then this example says that this does not hold. Now I will talk about the rigidity of the cohomology module. Let me put it in graph. So what it says that if some arbitrary of the cohomology module is non-zero, or some r less than equals to -n, then its all u graded component is non-zero for all u equals to -n. So if some graded component of the local cohomology module is non-zero, for some is greater than equals to 0, then it is all graded internal 0 for all u greater than equals to 0. And if TF graded component non-zero, for T lies in between -n and 0, then its all graded components are non-zero. So what this result says that to say whether a local cohomology module is 0, it is enough to check only these two graded components, and only the 0th graded component and the -nth graded component. If both of them are 0, then the local cohomology module vanishes. So now I want to briefly discuss the techniques we have used to prove our result. So let K be a field and S be a polynomial ring in n variable over the field. It is standard. We are considering it as standard graded. So let D denote the K linear differential operator on S, and A and K denote the nth Weyl algebra over K, where dou y denotes the partial derivative with respect to xi. So since xi dou y, they don't commute with each other, clearly this ring is non-commutative. And if there is and equals to small dimension of it is of local so crucial point
Is it audible? Hello.
We can hear you. We can hear you.
Pavitra, you are audible.
Yes.
Yeah,
Yes, fine.
but I think there is some issues with the internet connection of Dr. Sudeshna Roy.
Yes, yes. Have we lost her in the?
I think I don't see her in the participant
Yeah, I think
list.
we have lost
Yeah.
her. Yeah.
Now she is here, I guess.
Sudeshna, are you here? Sudeshna, can you hear us?
No, she is not here now.
He has not joined.
I think
Yes.
she left. Yes.
So we can wait for a few seconds if she can manage to come back. Yes, she has come, I think.
Yeah, she's just joined. Yeah.
Yes.
Somo, add her as a co-host again.
Yes, Sudeshna.
Hello.
Yeah, can you hear us?
Yes, I mean, sorry for the inconvenience caused. Actually, I
It's
lost.
okay. It's okay. Please continue and put your slides.
Okay, thank you.
Please continue and go fast.
Okay, I will take, I mean, by 5 minutes I will try. I have one more slide actually, on 2 more slides, but I will just give the gist and I will finish.
Yes, you can take 2 minutes, please.
Oh, okay, thank you. The slides are visible?
Yeah, go to the full screen.
Yes, it's perfect. Yeah.
Okay, thank you.
Please continue. Yeah.
Okay. So here the main thing is that these local cohomology modules, they are not finitely generated over the B-string S, but they are finitely generated over the Weil algebra. So this makes the things easy to deal with this module. And to deal with the graded case, Lincoln Ma and William Zhang, they introduced a class of graded D modules, which is called Eulerian D modules in both characteristics. So in characteristic 0, we say a graded left ANK module L is Eulerian if they satisfies these properties, where this denotes the Euler operator, and by mod of y we are denoting the degree of y. So by classical Euler formula, the polynomial ring S is Eulerian. Again, the local cohomology module is Eulerian. But they gave example to show that these Eulerian modules need not be holonomic. And the issue with this class of module is that they are not closed under extension. So to rectify this problem, Puth and Purakkal introduced a new class of graded ANK modules that is called generalized Eulerian. So we say L is generalized Eulerian if for each homogeneous element y of A, there exists some positive integer A such that this holds. So here this A may depends on y. And notice that if A is 1, then it is actually the criteria for Euler, a module to be Eulerian. Now, one example is that any quotient ring is generalized Eulerian if eta in power A lies inside A for some A strictly greater than 0. Here notice that if A is 1, only then this quotient ring will be Eulerian. Otherwise, it is generalized Eulerian but not Eulerian. So Puth and Puragal proved that this local cohomology module, under our setup, this is generalized Eulerian ANC module. So the techniques we have used, that is the Dirham cohomology and the Koszul cohomology of the generalized Eulerian modules. And to prove the vanishing and the tameness property, we have used the fact that local cohomology modules are countably generated over R when C contains an uncountable field. And this, we can always consider by base change. So all our techniques, what we have used, it was developed earlier by several authors, including Professor Tony. But the main issue we have faced is that we don't have the notion of holonomic modules in our general setup, but we do have the notion of generalized Eulerian modules. And only using the technique of generalized Eulerian modules, we reproduced all those results and get our, prove our results. So this ends our talk. This ends my talk, and thank you for your attention. And these are some references, and this is the paper based on which my talk was.
Okay. Thank you, Sudeshna. Any quick question? Okay.
There is a question in the chat.
There is a question in the chat. Can you see, please, Sudeshna?
Chat is not visible.
Actually, she just logged in. Actually,
So
she
what
just
is
logged in.
the
You can just.
what is the definition of rigidity in this case? I guess this one or any other question.
Okay, here I am saying that only one single graded component is, the effect of single graded component is quite, just let me go to that slide. Sorry. So here one single graded effect of the single graded component on this local cohomology module is huge. Only one graded component is saying giving the whole region, giving a big region where this module is non-zero. So for that we are saying it rigidity, that only one graded component has this much effect here.
Oh, okay. So thanks again, and we have to wrap it for the next talk.
Okay, thank you.
Thank you,
Thank you
Sudeshna. Yes.
again.
So I think next speaker is Rimpa Nandi. She is here.
Yes, I'm here. Is it
Okay.
audible for
Can
everyone?
you share your slide, please?
Yeah, sure. Silent. Yeah. Is it visible to everyone?
Yes. Yes. Fine. So let's start. Next speaker, Rimpa Nandi from Indian Institute of Technology, Kharagpur. She will speak on regularity bounds and linear resolution of toric algebra of graphs. Rimpa, please.
Thank you. So I want to thanks to the organizer of Virtual Math Fest for giving me the opportunity to present here. So the title of my presentation is Regularity Bounds and Linear Resolutions of Toric Algebras of Graphs. And this is a joint work with my supervisor, Dr. Ramakrishna Nanduri. So as the title suggests, this is a connection between the graph theory and the commutative algebra. So for that, I will first define some terminologies I have used throughout my presentation. I assume that everyone knows the definition of a finite graph, so I am skipping this part. Now I will define the edge ideal. So if I have a finite graph G with the vertex set V of G and the edge set E of G, then we can associate a monomial ideal with this graph in this way, that this Ig is generated by the edges coming from the graph itself, and this is an ideal in this polynomial ring. So now, as we have an ideal, we can associate the algebra so suppose generated by these monomials, then we can associate the Riesz algebra in this way, and we can associate the fiber cone to this ideal, which is known as toric algebra in the graphical sense, and this is nothing but an algebra over K which is spanned by these generators of the edge ideal. So I have already defined these generators in this way, that ME is equals to xi xj if E is the edge xi comma xj. Now, as we have an algebra, so we will try to find a defining ideal for this algebra by defining a map from a polynomial ring to this algebra. So here we are taking the polynomial ring R equals to this polynomial ring, where this y1, y2 and yq are the variables, and they are basically denoting the edges e1, e2, eq of the graph, and we are defining the map in this way. Then the kernel of this map, this is known as the toric ideal of the graph G. This ideal was first introduced by Villarreal in 1995, and so I'll give you an example so that you can understand, so all of you can understand what is a toric ideal. So here I have a 4 cycle x1, x2, x3, x4. I'm sorry, I have done something wrong here. Okay, so suppose these are the ages x1, x2, x1, x4, x3, x4, and x2, x3. Then if we take the even closed work x1, which is going to x2, going to x3, going to x4, and coming back to x1, then the generator of Ig is defined in this way: y1, y3 minus y2, y4. So this y1 is denoting this e1, and y3 is denoting e3, and y2 is denoting this e2, and y4 is denoting this e4. So this is toric ideal coming from this graph. Now, as we have an ideal, our next target will be to find the generators and the Grobner basis for this toric ideal. So to find the generators, we'll define a even closed work, and we'll associate a binomial to that even closed work. So suppose we have an even closed work W in G of this form, then we associate the binomial in this way. In 1995, Villarreal again proved that the generators of the toric ideal, they are nothing but the set of these even closed work in the graph G. And in fact, if the graph G is bipartite, then we have to take only the even cycles in the graph G. So now we have a set of generators for the toric ideal. Next target will be to find the Grobner basis of the toric ideal. For that, we need to define primitive works. So if W is an even closed work, then it is called a primitive work if it satisfies this property here. And then in 2012, Inna and Herzog, they proved that this toric ideal, for this toric ideal, the Grobner basis is actually the set of the primitive works in G. And this is with respect to any monomial order. So next I'll define some homological invariants with respect to for any graded module M. Suppose that M is a graded module and it is finally generated, and over the Noetherian local ring R, and then obviously M has a minimal free graded resolution. Then we'll say that M admits a p-linear resolution if the minimal free resolution is of this form, where this beta ij, they are the ijth graded Betti numbers of M. And I'll next define the Kashul-Nobel-Mumford regularity. This regularity was first defined by Mumford in algebraic geometry, and after that Oishi, he defined this regularity in commutative algebra for graded modules. This actually measures the complexity of a module, and so we define this regularity here in terms of the graded Betti numbers, but this can be defined in terms of the local cohomology modules also. Next, I'll describe some results which are done in the direction of finding the bounds and linear resolution of toric ideal and Riesz algebra. So in 2017, Bearman, O'Keefe, and Toole, they first provided a lower bound for the regularity, the Castelnuovo-Mumford regularity of toric algebra for a graph G, and he provided this in terms of the presence of complete bipartite subgraphs in G. And they also provided some upper bounds for the regularity of toric algebra for caudal bipartite graph in terms of the bipartition of that graph. After that, in 2018, Weisheit-Rose, he proved that regularity of Rie's algebra of a bipartite graph that is actually equals to the matching number of the graph G. And after that, in 2019, Herzog and Hebe, they showed that if the Rie's algebra is normal, then the regularity of the toric algebra is actually lesser equals to regularity of the Rie's algebra. And they also they also provided a very nice bound for the regularity of Rie's algebra if the Rie's algebra is normal. So they showed that the regularity of Rie's algebra lies between these two numbers, matching number of G and matching number of G plus 1. After that, they asked a question that when this regularity of Rie's algebra can be equals to the matching number of G. So here we provide a completely new bound for the regularity of Rie's algebra for any graph G, and we provide some conditions such that this equality is satisfied there. So we first prove that if G is a connected graph and suppose that Rie's algebra is normal, then the regularity of Rie's algebra is bounded above by the minimal vertex cover number of the graph G. And as a corollary, we have shown that if G is conic, so G is conic means the matching number is equals to the vertex cover number. In that case, regularity of Rie's algebra equals to matching number and equals to the vertex cover number. And this actually answers the question asked by Herzog and Hebe. So this actually provided a class of graphs such that this equality holds. And also as a immediate corollary, we can show that if G is a bipartite graph, then obviously G is conic, then these two numbers are equal, which also recovers the result of Weisheit-Rose. Next, we provide some bounds for the regularity of Rie's algebra for a gap-free graph. So what is a gap-free graph? Suppose we have a graph G and we have two edges, they are not connected by a vertex. Then they should be connected by at least one edge in order to be a gap-free graph. So to provide some bounds for the regularity of Rie's algebra for gap-free graph, we recall a family which was introduced by D. Meister in 2006. So this suppose that G is a graph, then a subset U of the vertex set, this belongs to this family UG if it satisfies these three conditions. And this family actually plays a vital role in providing our bound for this regularity. So our next result, that is that if G is a gap-free graph such that it has at least one edges, then this regularity of the Rie's algebra can be bounded above by this number where U belongs to the family UG, which we have already described. And further, if we have that U is a maximal independent set there, such that this Vg minus U is a maximal clique, then this regularity is lesser equals to this number. And here HU is the minimal triangulation of G. By minimal triangulation, we mean that if we have a graph, then we can make it caudal graph or triangulated graph. And the minimal graph we are taking, caudal graph we are taking in order to get the minimal triangulation there. After that, if we achieve or if we provide a new bound, the next target will be to show that this bound is obviously a sharp bound. So here we provide an example to show that this bound we have provided here, this is in fact a sharp bound. And after this theorem, we have some immediate corollaries. This one corollary is this one, and the next corollary, here we have a gap-free graph such that the edge set is greater or equals to 1. Then if G satisfies this condition, then regularity of Rie's algebra is equals to matching number of G. So this again provides a new family where the regularity is equals to the matching number, which again provides a class of graphs that question asked by Herzog and Hebe. now I will discuss about the linear resolution of toric algebra of graphs. In this direction, in 1999, Osugi and Hibi, they gave a characterization for the toric algebra such that the toric algebra has two linear resolution. After that, in 2019, Hibi, Masood and Shuchiya, they proved that suppose we have a graph G and the toric algebra has a 3 linear resolution, then K of G has to be hypersurface. That means the toric ideal IG should be generated by a single element. And after this result, they actually conjectured this thing for a general Q linear resolution. So they conjectured that if K of G has a Q linear resolution, then K of G has to be hypersurface for a connected sample graph G. This conjecture was proved by Shuchiya in 2019, and this was proved affirmatively for bipartite graphs. So the proof for the general graphs is still unknown, and here we prove this conjecture affirmatively for caudal graphs. So what is a caudal graph? A graph is called caudal if every induced cycle in G is of length at most 3. So to prove that the caudal graph, the KG has a Q linear resolution and it is a hypersurface, we need to find the number of generators in the toric ideal. And the number of generators, this is connected to the Grobner basis because Grobner basis itself is a generator. And we know that the Grobner basis is nothing but the primitive works in the graph G. So we need to know the nature of the primitive works in a graph. And here we have the result from Diali. He showed that an even closed work of length 2q is primitive in a graph G if this is either of these three forms. One is an even cycle. Next, it can be two odd cycles connected at a common vertex, or it can be sequence of odd cycles connected by sequence of paths. So we have proved that if G is a caudal graph and IG has a Q linear resolution, then all the primitive works in G are of type 3 only. So we have cut down the type of primitive works in just one type. And next, in the next lemma, we have shown that if G is a caudal graph and IG has a Q linear resolution, then all the primitive works is of particularly this form only. That means two odd cycles and connected by only one path. So now when we have the type of the primitive works, our next target will be to find the number of the primitive works. So in the next theorem, we have shown that if G is a connected caudal graph, then IG has Q linear resolution, and then G has exactly one primitive work of the type C1 PC2. So that means if G has only one primitive work, which means that IG is generated by only one element, and so combining these three results, we get our main result, that is if G is a caudal graph and IG has a Q linear resolution, then KG is a hypersurface, because we have already shown that IG is generated by only one element. And this ends my talk. Thank you.
Okay. Thank you so much. Any question? Okay. If there is no question, we thank again the speaker. And our next talk, I think at 12:10. Saurabh?
Yes. So it would be a remembrance talk on C.S. Seshadri.
Okay, so thank you, Professor Barik, for chairing this session. Today we had a lot of technical glitch. Sorry you had to face it. Thanks a lot for joining us.
Visible?
Yeah, but on the right-hand side of your screen, there's
No, I'll remove that. That's
yes.
okay?
No, that's okay, yeah.
Yeah, and I suppose if I move it, it moves fine.
Yeah, it moves
okay,
fine.
because I will be writing on the margins or on the sides as I'm giving the talk.
Okay.
So this looks fine, right?
Yeah, it looks fine, yeah.
Okay, good, thanks, yeah. You can give me a start call and then I can start.
Yes, sure. So I think I should start now. The talk is supposed to start on 12:10. So I'm Saurabh Sen, one of the co-organizer of this conference. And it's very sad that Professor Shias Sheshadri left us forever on last Friday in Chennai. He was a magician in the field of algebraic geometry. His work, especially on unitary vector bundles, geometric invariant theory, and Schubert varieties, revolutionized the field. And among many awards and honors that he received, if I want to mention a few, then I have to mention the Padma Bhushan, Shanti Sharu Bhatnagar Award, and I also want to mention that he was also a fellow of IAS, INSA, American Mathematical Society, and Royal Society. I had the privilege to meet with this very humble mathematical giant directly during my multiple visits to CMI. Now, I would request Professor Vikraman Balaji, who was a student of Professor Seshadri, to say on the life and works of C.S. Seshadri. Now, yeah,
Yeah,
Professor Balaji.
thank you very much. It's a pleasure to be able to share my views on Seshadri's life and work. I thank the organizers of the conference for giving me this opportunity. Yeah. So I begin with my first slide here. This is my first talk of this kind. So Seshadri was a mathematical luminary of post-independent India. He passed away on the 17th of July after ailing from deteriorating Parkinson's disease. He passed away in his home in Mandaveli, Chennai. He was with his family when this happened. That was last Friday. I dedicate this talk to his family, his son Giridhar, daughter-in-law Padma, grandsons Rangasai and Anant, and Seshadri Sundari's daughter helper over the years, Vadivu was her name, whose devotion to both of them was exemplary. So this talk is dedicated to them. So I begin with a little bit of his life and then quickly go into his mathematics. Seshadri was born on the 29th of February, 1932. He joined the Tata Institute School of Mathematics in 1953 after completing his bachelor's honors degree at Loyola College in Chennai. He did his PhD, finished his PhD thesis in 1957. Seshadri's doctoral thesis was entitled Generalized Multiplicative Meromorphic Functions on a Complex Analytic Manifold. And this thesis, apart from a few other things, gave an independent proof of the so-called Birkhoff-Grothendieck theorem on vector bundles on the projective line. Just to recall what this theorem was, historically, this was the result which looked at considered holomorphic vector bundles, at least that's what Birkhoff did, holomorphic vector bundles on the projective line, and it was proved that it was a direct sum of line bundles up to some canonical equivalences, identifications. So this was the main theorem, but the theorem historically, Grothendieck proved this not just for vector bundles, but for arbitrary principal bundles. Well, the result on vector bundles actually goes back to Dedekind and Weber in their famous paper of 1882. And there is a very nice historical outline in this. I've given this link here to Charlot's article, which tells you exactly the various people who worked on this and how one can actually go back to Dedekind and Weber for the vector bundle case. So this was Seshadri's start of his journey. Seshadri came to Paris in 1957, and there is some sort of apocryphal story about how he is supposed to have met Serre in his office. Serre had actually posed the following problem: over n-dimensional affine space, are there non-trivial vector bundles? In other words, is the following statement true? Is any projective Noetherian module over the polynomial ring K(T1, T2, Tn), where K is the field, free? Is a projective module, finitely generated projective module, free? That was the question. For n equal to 1, the ring Kt is an integral principal ideal ring. Therefore, any Noetherian torsion-free Kt module, in particular any projective Noetherian module, is free. One could see, for example, Lang's algebra for all these things. For n equal to 2, it was already a very difficult question, and it was a conjecture of Serre's that, in fact, it must be true, or at least this was a question. I would call it a problem. It was not a conjecture. So, and here, for n equal to 2, the fact is that there are no non-trivial bundles either. And this is the theorem due to Seshadri. This was very early in his entry into the Paris School of Algebraic Geometry in 1957-58. And it kind of shot Seshadri immediately to stardom because, I mean, it was a kind of a unique argument. It was a beautiful argument there. The final affirmative answer in all dimensions, that is, any projective Noetherian K2 T2Tn module is free, is the theorem due to André Suslin and Quillen, which was done independently by them sometime in the 1970s. So one of Seshadri's, I think Seshadri's first PhD student, Bauman Murthy, carried on from Seshadri on this and proved the theorem for n equal to 3 first, and then did a lot of work in collaboration with Hyman Bass in those days, which was the foundation for this whole theory. It just grown into a huge, structure in commutative algebra and algebraic geometry. Okay, so when Seshadri reached, or when he landed in Paris at that time, and there is the time that he finished his doctoral work, algebraic geometry itself was undergoing a unique revolution in the hands of Alexander Grothendieck. The previous generation of Zariski and André Wei's work, I mean, was there as a huge body of work, and many people had worked in it, but Grothendieck was revolutionizing the whole subject. Seshadri went to Paris in 1957 and very quickly entered the sanctum of this new temple of algebraic geometry. And the very fact that he could enter the temple into its sanctum provided him a very distinctively unifying perspective. I mean, whoever entered the temple in those days got this perspective, which connected it to all branches of mathematics at some level. This kind of universal perspective was Grothendieck's view in some sense. André Weil had published striking conjectures linking number theory to topology, two very distinct branches of mathematics. And this was one of the driving forces behind the Renaissance in algebraic geometry in the hands of Serre, Grothendieck, and several others in Paris. And it was a heady time, I believe. Seshadri has told me several times that it was one of the most exciting times. I mean, developments were taking place almost on a daily basis, and there were these big seminars going on. There was a Cartan seminar, there was a Chevalier seminar, and talks given in these seminars were on recent, very, very new developments in those days. And Seshadri gave 3 talks in the Chevalier seminar, one on Picard varieties and their compactifications, and one on Cartier operations, both of which are very well known. The one on Picard varieties was later written as a paper by him. And this work on Picard varieties was in some sense kind of a precursor to many of his later works on vector bundles, on smooth varieties and singular varieties. And much of his later work had some sort of you can trace it back to his early ideas. In fact, his thesis itself was on vector bundles. So I guess all his later works were somehow connected to this. I directly go to the Narasimhan-Seshadri theorem. I mean, in between this period, I think in early 60s, Seshadri also gave a different proof of the so-called Weizenbach theorem. Very distinctively original proof of the Weizenbach theorem, which interestingly, I mean, he didn't pursue that kind of the whole theory there, but it was taken up and developed a lot by Gross-Hans, I believe. And there's a whole concept called Seshadri's sections, which comes out of this work of Seshadri's. I don't want to get too much into the details there because it's a general talk, but Seshadri had I mean, whatever he touched was non-trivial, and that was his style, and that was perhaps his keenness of his intellect. So the Narasimhan-Seshadri theorem, it came in 2 papers. One was in Math Annalen, and the second one was in the Annals of Mathematics. So this work had its roots in the work of André Weil on generalization of abelian functions, which was written sometime in 1938. I think that was. And its foundations were very closely linked to the work of Poincaré on the so-called uniformization theorem. I mean, this perspective of connecting it to the uniformization theorem, I'll indicate a little soon enough now, but this perspective comes from today's vantage position. I don't think either Seshadri or Narasimhan had any such perspective at that time, but it was Narasimhan who told me about this links or sort of mysterious unconscious links to a certain approach to the uniformization theorem. I'll come back to that later. But the roots of this work really were in Wales' paper on the generalization of abelian functions. So what is the Narasimhan-Seshadri theorem? So this theorem is a prototype of some sort of a theorem on correspondence, the equivalence of categories kind of question, which is so they were looking at two classes of objects: the irreducible unitary representations of fundamental groups of Riemann surfaces and stable vector bundles. So let me just indicate a little bit what do I mean by that. So let pi1 of x be denote the fundamental group or the homotopy classes of paths or loops on a Riemann surface X. This group was known to be what is called a Fuchsian group because of it's a Fuchsian group. I'm assuming that the genus of my Riemann surface is at least 2. If it's 1 or 0, then we'll have to state the result differently. So in these cases, this fundamental group was acting on the upper half space, and it's seen as a Fuchsian group, and since it's a subgroup of PSL2R, the automorphisms of the upper half space. And they were interested in irreducible unitary representations of this fundamental group into this unitary group like this. And they were interested in equivalence classes modulo what is called conjugacy, or the action of the projective unitary group. So this was the one class of objects they were looking at. And this class of objects had been studied earlier on, as I said, in the paper of Andre Weil. And to each such representation, they could associate. So to rho, they could associate a geometric object, a vector bundle, V rho, on the Riemann surface X. So we are viewing the Riemann surface X as a quotient of the upper half space by the action of the fundamental group. So this is the fundamental group acts freely on the upper half space, and this is the quotient. So you can think of this H as a principal pi1 bundle on the Riemann surface X, and this associated vector bundle is to this rho. You can look at the representation rho. So this group pi1x will be acting on the complex Cn through a unitary representation, and you can look at the vector bundle, which is defined to be H cross rho Cn, which is basically upper half space H cross Cn modulo an equivalence relation, which is through this diagonal action of the representation rho on the upper half space, and on Cn through the representation pi rho of the fundamental group. So this associated vector bundle, this is really can be seen as a vector bundle on the Riemann surface X. Vector bundle means that something which is that you can cover the Riemann surface with small disks, and this vector bundle will be locally trivial on each of those things, and there's a gluing datum. So their idea was these vector bundles belonged. I mean, you can look at the space or the set of vector bundles, but the hard part was to say that the space of vector bundles had some geometric structure. So it was in those days that the notion of stable vector bundles had already been defined by David Mumford in 1960-61. This was Mumford's Geometric Invariant Theory, a book which was, I would say, it started off as a paper and became a book, I believe. Mumford had constructed the so-called moduli space of stable bundles, which means that he could give the set of stable bundles, isomorphism classes of stable bundles, Stability is a notion which I don't want to define because it's a general talk, but there's a kind of a slightly smaller class. I mean, you don't want to go into all vector bundles. You are going to restrict your attention to vector bundles of some rank and degree. And stable bundles was a kind of a natural subset there. And Mumford could give it a geometric structure. And this was the moduli space of stable bundles. And as I said, the unitary representations of the fundamental group had been looked at very closely by Andre Weil. And what Narasimhan and Seshadri proved was that this association to every row to give this vector bundle V. So you restrict your attention to so-called irreducible unitary representation. Irreducible can be defined as in the classical Schur lemma kind of thing, that, I mean, the image of this acts as a, I mean, the image of this group is a irreducible subgroup of the unitary group here. So it doesn't leave any proper subspaces of CN invariant. That's what it means. So if you put the condition of irreducibility, then the associated vector bundle V rho, which comes out of this association, in fact is stable. And the hard part was that this, which looks like a set theoretic correspondence, had to be proven. I mean, so that it has to be proven that it's an equivalence of categories. And Narasimhan Seshadri brings in geometry. And they look at the manifold of this space of irreducible representations. They study the deformations of representations in the earlier paper. Then they look at the space of stable bundles that Mumford had constructed and show that this association has the properties of continuity. They show that this is injective in some sense. The image is open. For this, they use the, I mean, these spaces have the same dimension that can be computed. And then they showed that the image, in fact, is open by using Brewer's theorem on invariance of dimensions. And then they are able to extend this. I mean, some sort of compactness is required, some sort of properness is required. So you want to prove that these two spaces are homeomorphic, which is what they did. Topological homeomorphism is what they established, and thereby the sort of bijection of the isomorphism classes, and hence some sort of an equivalence of categories. So this, I mean, using this fact that this map is continuous, this is open, this is injective, and this is, you can extend it to sort of not just the irreducible representations, to the space of all representations. And the space of all representations, in some sense, is a compactification because the unitary group is compact. And that would, in some sense, force this associated dysmorphism rho to V rho to be actually proper, which was one of the crucial parts of this work. And bringing in all these ingredients together, they could set up this bijection. So that was the Narasimhan Seshadri theorem, which became very important in many ways. So there is an analogy, this Rosetta Stone analogy, which I'd like to share with you. This is something which comes up in Andre Weil's lecture to his sister, Simone Weil. So setting up such correspondences were somewhat like the process of building a Rosetta Stone for the deciphering of hieroglyphics. The two classes in the Narasimhan Seshadri theorem, the two of the languages on the Rosetta Stone. People should know that the Rosetta Stone was the one which had statements written in 3 different languages, and you have to decipher the third one. The third language came up much later from the work of Simon Donaldson during the mid-80s. Once provided, I mean, Donaldson gave what is called a purely differential geometric proof of this Narasimhan Seshadri theorem. Once all the 3 came together, once provided, many subtle and beautiful aspects of differential geometry, topology, mathematical physics, and number theory got miraculously unraveled. And this was in the 90s. Several things happened. I mean, I don't want to get into that. There's a huge body of work, which is, I mean, talking about Donaldson's work on 4 manifolds and Witten's work on Seiberg-Witten invariance, and so on. I mean, all of them in some sense had their roots in the Narasimhan Seshadri theorem. So I just wanted to say that, I mean, this one could kind of see this Narasimhan Seshadri theorem from the so-called, I will just say that there is a method of continuity. This is a method of proof, which an attempted method by Felix Klein and Poincaré for the uniformization theorem. The uniformization theorem said that, I mean, classifies the simply connected covers of Riemann surfaces. I don't want to go too much into it, but the beautiful thing about this Narasimhan-Seshadri theorem is that unconsciously, I mean, or rather at a very subconscious level, they kind of linked themselves to a method which was kind of discarded by Klein and Poincaré. This was looking at representations of Fuchsian groups in SL2R, discrete and faithful representations, and to each representation they could identify some sort of you could look at the space of metrics on oriented, closed, connected surfaces of genus bigger than or equal to 2. And you could look at the space of metrics modulo isotopy equivalence, and that is the Teichmuller space. I mean, all this is a modern perspective. And then to each representation of the Fuchsian group into SL2R up to conjugacy, you can associate a metric in this class. And they were attempting to prove the uniformization theorem by showing that this association is in fact a homeomorphism, which is eventually true. And I mean, it can be proven now, but the ideas were very interesting. And finally, it was the work of Breuer. I mean, there's a correspondence of Breuer with Poincaré where he's suggesting that his ideas are essential towards completion of the argument, which was never done then. But recently there was a volume on Poincaré where this method is there, and Narasimhan, in fact, told us about this connection sometime about 10-15 years ago. So now I'll go to Seshadri's other deep contribution, which was in the subject of geometric invariant theory. And this was a classical area, and the invariant theory questions were, studied a lot by Hilbert and several other people. And there was Mumford raised it to some sort of a monument status in his work because he connected it to constructions of spaces. I mean, where invariant theory could be used to construct geometric objects. Mumford's Seshadri approach provided the framework for most moduli space constructions, which came up then, and even to this date, the construction of the so-called core spaces for stacks has its roots in these kind of ideas. There were 3 papers of Seshadri's. The first one was the unitary bundle paper, which was just after the Narasimhan-Seshadri paper. This, in the Narasimhan-Seshadri paper, I was trying to point out that there was this properness business of proving the association. They didn't have a good space of compactifying of the stable moduli space. And so Seshadri then used Mumford's geometric invariant theory to construct a natural compactification of the moduli space of stable bundles, isomorphism class of stable bundles. And for this, he introduced the notion of S equivalence. So terminology S equivalence comes from a nomenclature given by Narasimhan and Raman, S standing for Seshadri, and also could be for semistable equivalence. So this was an equivalence which was some sort of an orbit closure equivalence. I mean, the orbit equivalence in some sense is like isomorphism classes, but orbit closure equivalence is a more complicated equivalence. And Seshadri's contribution here was to show that that is the natural equivalence which comes when you do geometric invariant theory. So this business of introducing orbit closure equivalences and making, constructing compactifications of stable objects became the prototype for constructing compactifications by GIT. So this was, so in some sense, a foundational paper, Seshadri's paper in the Annals of Maths in 1967. The second one was on Mumford's conjecture. Mumford had, I'll come to it soon enough, but just a little later now. Mumford had made conjectures, and Seshadri proved this conjecture as this was Mumford's theory originally was in characteristic 0, and Mumford was setting up the right foundations for doing things in the positive characteristics, because for arithmetic applications and things like that. And Mumford's conjecture was proved by Seshadri for the GL2 case, which itself was quite a beautiful argument. And but the paper had many other things. This was in the so-called 1968 TIFR volume on algebraic geometry, which was I said so-called because it was famous for several very beautiful articles in that. And Seshadri's paper had, although he proved the conjecture for GL2, he he could show that, you could, in some sense, construct these moduli spaces by circumventing many of these ideas, and even in positive characteristics. So this is the main contribution of his paper there. And then in the third paper, which came in 1970 in the Annals of Maths, which was on quotient spaces modulo reductive groups, he set up the foundation of studying quotients as algebraic spaces. I mean, this is a work of Kolar and Kiel and Mori, which comes later in 1990s. And Seshadri's several ideas there. He introduced the foundational technique of elimination of finite isotropies, which Kolar uses very non-trivially in his work. And the so-called Seshadri ampleness criterion and Seshadri constants, which became very famous afterwards, they come up in this paper of Seshadri's. So I'll remark a little bit on this below as we go ahead. So this was Seshadri. In fact, I think this paper came up because Seshadri wanted to give a geometric proof of Mumford's conjecture. And so his philosophy, or at least the original idea of Mumford's conjecture, was the following. So let me just say that, Mumford's conjecture is the following. So Mumford's conjecture. So the notion of some G being a reductive group is classical. I mean, you could think of it as, I don't want to get into a technical definition of what a reductive group is, but most groups that we know of, the classical groups and the exceptional groups, they're all reductive groups. And there was a property that Mumford wanted, which he called geometric reductivity, which said that if G is a group which acts linearly on a vector space, finite dimensional vector space V, and if V is a vector, non-zero vector, which is G invariant vector, then the property of what he called geometric reductivity was to say that for every such non-zero invariant G invariant vector, there exists a G invariant homogeneous polynomial, homogeneous F, a polynomial on the vector space V of positive degree, invariant polynomial, such that F of V is non-zero. So this was the property of geometric reductivity. And if people know what is linear reductivity or complete reducibility, which would tell you that if V is an invariant vector, then you can look at these one-dimensional subspace of generated by V, and the property of linear reductivity means that you can get a G invariant complement, a supplement of this one-dimensional vector space V, so that V is a direct sum of these two. And such a supplement would, in some sense, be equivalent to getting hold of a linear function F, which has this property. But for geometric purposes, Mumford wanted a homogeneous polynomial of positive degrees so that this happens, and he called this property geometric reductivity. And in some sense, the philosophy there, as I said, the Mumford-Seshadri theory was that if the group was geometrically reductive, then this quotient, you could start with the projective variety X on which G is acting, and you can transfer the property of the action of the group on the projective variety into some sort of a linear action on the cone. And if you the quotient, which is equivalence classes of semi-stable points for a linear action of G on a projective variety, the set, if this could be given a structure of a projective scheme, then Mumford's conjecture holds. That means you can prove that reductive is geometrically reductive. So this was some sort of a geometric translation of a very purely algebraic property from reductive equal to geometric reductive into some property of the quotient space having some projective scheme structure. So the basic conjecture was proved by Habush in 1974, but Seshadri's characteristics were such that he just could not let go of his original thought process and his argument. So I think somewhere around early 2000, he saw that there was a new work of Sean Keel. This was the kind of missing ingredient which he needed to complete this picture. And Seshadri and Pramod Shastri completed Seshadri's old argument. And the new ingredient of Sean Keel was, under some conditions, line bundles, which are so-called numerically effective, and F bundles and big are semi-ample. These are technical terms. I don't want to get into that. So there is a recursive property for Neff-line bundles to become semi-ample, a Nakai-Mosajon criterion for semi-ampleness, which is the work of Sean Keel, and Seshadri's original thought process, where he was trying to prove Mumford's conjecture using the geometric arguments, gave rise to Seshadri's ampleness criterion in the same spirit. And that's the reason why he was looking for the key ingredient which was missing at that time. And in the Seshadri ampleness criterion, it was a kind of an extension of the Nakai-Mosajon criterion, and a certain constant comes there. And an effective notion of this constant was later on given by Demai, and he gave it the name Seshadri constant. So this is the origin of Seshadri ampleness and Seshadri constants, which came up in this paper on quotient spaces. So the next piece of work that I'd go to is the analog of the Narasimhan-Seshadri theorem for a very general class of Fuchsian groups. Fuchsian groups, the fundamental group, as I said, was an example of a Fuchsian group. You could look at more general discrete subgroups of PSL2R, and if you restrict your attention to Fuchsian groups which act with the so-called parabolic or elliptic fixed points on the upper half space, to irreducible or unitary representations of such spaces, you can associate geometric objects exactly like the Narasimhan-Seshadri theorem, but these geometric objects will be vector bundles on the Riemann surface with added structures, which are called parabolic structures. So they introduced so-called parabolic bundles, which is a very flourishing industry now. Many scores of papers have been written on it. And much later, sometime as late as 2015, Seshadri and I wrote completed this theory to homomorphisms of Fuchsian groups into semi-simple algebraic groups, which Seshadri always felt, could be done, but when the equipment and the theory was not fully grasped at that time. And so as late as 2015, Seshadri was still active, very keen and with sharp intellect and perfectly comfortable with the most abstract of notions. So now, so I don't know whether I should give a little bit more about. So I just wanted to say that maybe I don't know whether I should give. So the theory was that, as I said, to representations rho, for young people who are looking at this talk. So this rho is, as I said, the representation of a Fuchsian group into the unitary group, and this is, I'm talking about the Mehta-Seshadri theorem. So this gamma is going to act on the upper half space with a finite set of points which we can assume to be so-called elliptic fixed points or parabolic fixed points. It just depends on what sort of stabilizer subgroups gamma has at these points. And if you look at this gamma will not act freely now. It will act with isotropies. So you can look at the quotient map from H to H mod gamma, which is your Riemann surface X. And you can, in some sense, make this association V to V rho by a process using this map P. And to rho, we can associate this vector bundle V rho now, again on X. But this V rho is not just a vector bundle. It's a holomorphic vector bundle with, if you look at the image of these points, A1, A2, AM, and this some X1, X2, XM here, and this is orbits here. They're not just points. So if you look at these corresponding images of these points here, this vector bundle V rho, depending on this representation, will have flags at these points, and they come with some weights. So the idea of Mehta and Seshadri was to have a notion of a new notion of stability for these objects, which was the parabolic stability. Many of these, some of these ideas, at least in the case of elliptic fixed points, goes back to an early paper of Seshadri in a Verona conference in the late 1960s. He was already looking at these questions, but he always told me that he just could not push the whole idea because he didn't have a full proof of the properness of the moduli space of what he called pi bundles. He had a proof there, and but he wanted a proof which was avoiding some sort of coverings which was being used by Seshadri then. And it was the joint paper of Mehta and Seshadri that some sort of evaluative criterion was used to prove the properness, and that's how the paper got completed. This was almost, I think it was in 1980, and this is a famous paper of Mehta and Seshadri. So this was, I didn't spare, this was Seshadri had done several other pieces of work. I mean, there's a volume in the Asterisk series called the Fibre Vectorial. It's in French. And the notes were taken by Jean-Marc Drezé. And this collection has lots of, there are several results of Seshadri on desingularization, and Seshadri's, one of his favorite themes was understanding degeneration of moduli of vector bundles when the curve degenerates to a nodal curve. So he was interested in vector bundles on singular curves also, and these questions were coming from compactifications of Picard variety. There was a famous paper of Seshadri's, which I have not mentioned here, which is the so-called Oda Seshadri paper, which studies the compactifications of the modulus of the Picard variety. And here I can tell you that Seshadri kept telling me that he was in Harvard in those days. Oda was also there, and David Mumford was looking at these questions. There was a paper of Meyer and Mumford which was looking at the question of compactifications of Picard. And when Seshadri was there, Mumford asked Seshadri whether Seshadri told him that maybe one could use GIT. He was telling Mumford this, and Mumford asked Seshadri whether Seshadri could solve the question using GIT for the dollar curve, a singular curve like this. And I believe that, Seshadri told me that basically Seshadri made the computation for this case, which showed that even for the rank 1 case, that is the Picard case, the notion of semistability plays an important role, and which was a kind of new thing, because in the rank 1 case, semistability was not visible in the usual construction of Jacobian and things like that. So Seshadri's view, a point of view was that if you look at something like a reducible stable curve, this is an example of what is called a stable curve. And Seshadri then gave numerical criteria as to what should be the objects in the boundary of the Picard, which gave the idea of a compactification. And then this was developed in a very big way by Oda and Seshadri in a 90-page paper in the Transactions. So this is the construction of the compactification. So Seshadri was always fond of singular objects, singular curves. And then there is towards the end of 90s, Seshadri, Nagaraj and Seshadri, they did highly non-trivial work on degenerations of moduli space of vector bundles when the limiting bundle curve was a stable curve, which is an irreducible nodal curve, and this is highly referred to work now, which has developed a lot. So this was Seshadri's theory of using torsion-free sheaves, and those ideas were used here. So I don't want to go too much into this. I just wanted to say that there's a whole body of work which Seshadri did. Then he also studied the desingularization, where subsequently I was also involved in a little bit. So I just want to quickly come to his second half of the other half of his. He broadly worked on two different areas: the moduli theory, algebraic geometry, and in the invariant theory. On the other side, he worked on representations of algebraic groups, and this was from early 70s. So Seshadri wrote a paper in the mid 70s. I think his student Lakshmibai had joined him in the late 60s. Musli had joined him in the late 60s, and then Lakshmibai. And Seshadri, Lakshmibai, and Musli, they got together, and Seshadri had this idea of generalization, a vast generalization of the classical theory of Hodge for Grassmannians. And the idea was construction of bases for the space of sections of line bundles on Grassmannians, which was done by Hodge, but later Seshadri wanted to generalize it for more general Schubert varieties. Schubert varieties had the added Weil group element. So So the aim was to construct such natural basis which reflects the intrinsic geometry of the Schubert variety. And also intricate combinatorics of the Weil group comes into the picture here. And Seshadri and Mussoli, Seshadri and Lakshmibai wrote several papers which all appeared in the Indian journal, but they were foundational papers referred to by several people. And this was the so-called geometry of G mod P. This was the series of papers. Geometry of G mod P. I mean, this was the title. It starts with 1, and I think it goes all the way to 9, I think. Sometimes Seshadri with Lakshmibai, sometimes all three of them together. But it was a huge piece of work. And this theory has led to fundamental developments in the field of representation theory, geometry, and combinatorics. So there's a lot of technicality here, and it's not going to be easy to talk about that. So following this series of this, at this time when Lakshmibai and Seshadri were working, they were making very careful analysis of these issues and on the basis, especially when they're looking at Schubert varieties for exceptional groups. And Lakshmibai and Seshadri formulated the so-called LS conjectures. They didn't give this name. It was given much later by Peter Littleman. So this is the Lakshmibai-Seshadri conjectures. They were very beautiful combinatorial conjectures. And the key point of these conjectures was that it gave some sort of an indexing to this standard monomial theoretic basis, which this is not just giving some indexing. This indexing which implied a remarkable character formula, which is now called the LS character formula. And these were some sort of conjectures, and the character formula was natural consequence of those conjectures. And sometime in the mid-90s, there was this. So these spaces that we're looking at, the space of sections of line models, they got connected to the so-called de Mazur modules of the Schubert varieties, and Littleman proved these conjectures by bringing fresh inputs and new ideas from the theory of quantum groups. And I must mention that there's some very nice paper by Raghavan and Parmeshwaran, which carried on this combinatorics and this thing to give a new kind of basis for these objects. I don't want to talk too much about the technicalities here. So Peter Littleman solved this conjectures, and it was again very fundamental breakthrough in this whole thing. So this is a very brief story about Seshadri's work. I didn't want to go. Seshadri's other passion was the creation of Chennai Mathematical Institute, and the Chennai Mathematical Institute was founded in 1989 in times of crisis. Chennai Mathematical Institute came up. Seshadri had joined math science in 1984, and in the 5 years of Seshadri's stay at math science, there were several issues there, and then Seshadri was asked to start the SPIC Mathematical Institute by A.C. Mutaya in 1989. Seshadri took the plunge, and then later on this institute was called the Chennai Mathematical Institute. In the first 9 years, it was a research institute. And around 1998, because of funding crisis, Seshadri had a brilliant idea of making this into a different kind of an undergraduate institution, which was run by researchers. He was modeling it after what he thought was the École Normale Supérieure model, or the model of some of the top American universities. That was his vision for the place. But I remember much before this crisis, in the early 90s, in one of his moments when he was reminiscing about things, he pulled out a letter from his drawer and showed it to me, a letter written to A.C. Mutaya. This was even in the early 90s, where he had said that eventually that the institute should become a top-class undergraduate institution run by people who are doing frontline research. This was his guiding principle there. And so in some sense, the financial crisis gave him the opportunity to give shape to his dream. So he used it immediately and started this undergraduate CMI undergraduate program, which has, as everybody knows, and it has been mentioned a lot now, has come a long way from those days through several periods of crises. Anyway, so I just wanted to, so CMI was Seshadri's, apart from algebraic geometry and Schubert varieties, CMI was his something which engaged him very intensely for the last 30 years of his life. So a few words about Seshadri's personality. So Seshadri as a person. So I have known Seshadri as his doctoral student since 1984. I joined Seshadri 3 months after he joined the Math Science in November 1984. And I've then later on I became his collaborator and colleague at the Chennai Mathematical Institute. And I've had the pleasure and privilege of witnessing his personality, mathematical personality, the manner in which he thinks, which is rather unique. In fact, a mention of the manner in which he does algebraic geometry, it comes up in Caroline Parekh's biography of Zariski. Zariski saw Seshadri's non-canonical way of thinking, and I was fortunate to have some sort of I could get into the wavelength of Seshadri's hidden statements, and they made my own career. So as a mathematical personality, I saw someone unique in his vision and insight, an uncanny ability to consistently strike gold in a vast world of mathematics. That means in some sense, if Seshadri felt that something was interesting, then one could be sure that there was something very deep hidden there. In a volume of tribute volume of when Seshadri turned 70, Arun Ram has something very nice to say. I don't remember now. He said that, you know, if Seshadri found something interesting, you can be sure that, I mean, it's worthwhile pursuing. So this is Seshadri's uncanny ability to strike gold. I mean, just thinking of wherever he saw something, it meant that there must be something deep there. He was extraordinarily generous with his ideas, and he shared his insights with one and all. And this extreme generosity was his human side as well. So both in personal life, both he and his wife Sundari, they were extraordinarily generous people. And Seshadri was like an open book. Always, of course, the caveat was that the listener go back and pursue the ideas to the best of their abilities. And there used to be this constant pressure. You know, there was this famous, I mean, whenever Seshadri, after Seshadri has shared some of his ideas with anybody, then the subsequent meetings will always be a phrase which says anything, which means he will ask this question in a very anything, and that meant has anything come out of those ideas? Has there been work on it? As a person who's been listening, has he been just sitting idle, or has he been doing something about it? I mean, this was one single word which carried everything in it. And it was simultaneously an enthusiastic anything, but it was a huge pressure on the person who was listening to it. So this is Seshadri's subtle way of applying pressure on the people who are recipients of his ideas. And so this was his way of sort of continuing his, the work has to be continued. So that's the way he looked at it. And it was very challenging. And there was and Seshadri he was completely aware of his own stature. And because he was so completely aware of his own stature, he was naturally absolutely modest. I mean, he didn't have any insecurities at all. He knew about what he was. And at the same time, he was absolutely humble, very simple, almost bordering on naivety. I mean, he was a simple, naive person who didn't know many things about normal human things. So it was a very unique combination of a rather special mathematical brain, which was high in stature, and a very modest and humble personality, which was visible for all other interactions. He was also in leadership. I mean, nobody would have, if people had seen his personality earlier in math science, leadership in the sense of directing an institute and things like that would not have been easy to attribute to somebody like Seshadri, but Seshadri proved everybody wrong. I mean, he had insights, and he was very confident of his insights. What he felt was his intuitions about how things should be developed, and this confidence made him very calm. He was unperturbed during several moments of crisis that the institute faced, even during the math science times or later on at CMI, when CMI perpetually faced financial crisis. Seshadri was always unperturbed, and he was always dynamic as to find out what is the next thing to be done to carry on the activity. The work must go on. And Seshadri had a unique sense of humor and sympathy. He could meet anybody on the corridor and he would ask them about their welfare and things like that. And his sense of humor was infectious. His smile was remarkably infectious. I mean, anybody could joke with him and they will be having a very good time. And this was the hallmark of his personality. His interests were ranging widely from mathematics, philosophy, politics, and music. And music was a passion of Seshadri, which started very early in his life. I think he learned his basic music from his grandmother. That's what he told me. And this was, in some sense, his style of singing was somewhere close to, I mean, I would be rash in saying this, but something like Brinda Mukta's brand of Carnatic music. I think, interacted with Rangaramanuja Iyengar in Bombay. That's what he told me. Most of the compositions that he used to sing were self-taught. And this was again a remarkable trait of Seshadri's. And Seshadri was, I would call him a real expert in Dikshidhar and Shyama Shastri Kritis. He used to be a regular singer on the Saraswati Puja days at CMI. And it was the memorable moments of CMI was his singing in the library. And this was a tradition that he followed for 30 years. I mean, from 1989. And Seshadri's grasp of the nuances of Carnatic music, he could have been, he kept to himself. He was never a performer. And he kept to himself as a singer, never really went too much into it. But people who have heard him in private and know that he was top ranking. I think he ranked very well in music, as high as he ranked in mathematics, in my opinion. That's my opinion. Anyway, I'll finally quote Professor K. Chandrasekharan, who in a letter to Seshadri on the 10th of February 2013, he wrote, "I cherish the values that inspired the creation of CMI and your unswerving commitment to those values." So I would say that Seshadri will be remembered for these values that he brought in, and in his mathematics, impeccable high standards, quality, and also integrity, and mathematics in the institute building of CMI. All these things came in as foundational things, and one just hopes that CMI will develop and live up to the standards that he expected it to live up. So I close with lines from Auden. This is the hymn to the United Nations. This is so, like music, when begotten notes, new notes beget, making the flowing of time a growing. It is what it could be when even sadness is a form of gladness. So with that, I'll close this talk. Thank you.
Thank you, Professor Balaji, for this extraordinary talk. And we have basically some questions.
Sure.
Yeah, so these questions came from YouTube. You can also see those in your chat box, but I'll read it out for you.
That'll be better, yeah.
So I heard that Donaldson gave another proof of Narasimhan-Seshadri theorem. Was it
Yeah.
completely new or inspired by their work?
It was completely new. It was completely new. This was a differential geometric approach. One of the important things about in the old proof of Narasimhan-Seshadri, as I said, is a kind of a strange density argument. You set up this map and you prove that the image is open and closed, and then you prove that it is the whole space. There was not a, whereas in Donaldson's argument, there was some sort of a constructing, I mean, it was not the representation that he constructed, but there was some sort of an Einstein-Hermitian connection that he could construct on the bundles, which gave a grasp on some sort of a, it was a very different in spirit and flavor. Yeah.
Okay. Yeah, and the next question is, how does Riemann-Roch theorem come into action of the Narasimhan-Seshadri theorem, and how was the great influence of Grothendieck on Seshadri and other generation of mathematicians who entered the temple of algebraic geometry in 1960s? Yeah.
So the Riemann-Roch theorem really is too basic. I mean, it had influence in everything that happened in algebraic geometry. It was almost like a large philosophy of, I mean, which linked topology of and algebraic geometry in a big equality, which is the Riemann-Roch statement. So it didn't have any specific impact on the Narasimhan-Seshadri, except that everything was, I mean, Riemann-Roch theorem was like almost alphabets in if you want to do algebraic geometry. But Grothendieck's influence, I must say that I have to say that Seshadri was the first person who brought scheme theory to India. I mean, algebraic geometry of language of schemes. It was a bold thing. I mean, he came back in the 60 and I think started giving courses and introduced scheme theory in a very big way. I think even Narasimhan and Seshadri both were there during those times. Narasimhan's slant in those days was more analytic, but I think he was also very much influenced by Grothendieck's point of view. So both Narasimhan and Seshadri, when they came to TIFR, they brought modern algebraic geometry in this big way. It was taken up immediately by several people at that time. Seshadri had a galaxy of people who were, I mean, Seshadri's students were Pauman Murthy, I don't know, C.P. Ramanujam, whether he was, I can't be called Seshadri's student, but he was also one of the people who was highly influenced by Seshadri's thought process. And I mean, at that time, Raghunathan was there, and Ramanan was, these people were with Narasimhan, and they were also top graded algebraic, I mean, they knew algebraic geometry, the scheme theory at the front level, and then Raghavan Narasimhan was there who was doing analytic geometry. So it was algebraic geometry was, it was infectious in some sense and influenced everybody. And in late 1960s, TIFR was one of the world centers of algebraic geometry, and they had this huge conference where Grothendieck came and spoke about his so-called standard conjectures in 1968. And so I guess the influence of algebraic geometry was viewing this kind of Rosetta Stone kind of picture. You know, I mean, although this statement is from Andre Weil, trying to see analogies, trying to see symmetries, looking at groups. I mean, trying to understand whether objects generate groups in some sort of what I call Tanaka categories. I mean, all these things were a kind of almost natural thought process that people imbibed. And it became so natural that people now cannot even think without all that. That's the kind of influence that Grothendieck had, and Seshadri imbibed it completely and brought it into India. I would say he introduced Grothendieck's algebraic geometry to India, and today it flourishes because of him.
Okay, and one more question came from Snehojit Misra, who said that, is there any contribution of Seshadri in Falting's approach in moduli of bundles without using GIT?
Yes, the paper of Falting's was written. This is a technical question because somewhere in Falting's construction, where theta functions are being used, it is without GIT, but GIT does play a role. I mean, it is influencing the thought. It is telling you what to choose to construct as your invariants. I mean, looking at theta functions was the way in which Jacobian was constructed. So Falting's idea was to look at the same sort of theta function idea for construction of vector models. But what he could construct was some space whose normalization was the actual moduli space. And some ideas were required there. I think I remember that when the paper was written, we ran a seminar at CMI, and Seshadri wrote to Faltings about, slightly different approaches. And Seshadri kind of rewrote parts of Faltings by trying to see it from the standpoint of GIT. So although GIT doesn't directly come in, it is somewhere there as a background. I won't say it is, you can, it's not prominently there, but it is there.
Thank you, sir. And I would like to wrap up this session by saying that one of our faculty of our advisory committee, Professor Krishnendu Ganguly from Aider Mohali, have advised us so that senior professors present here, so they can share some fond memories with Professor Seshadri. So would like to conclude our session by that memory sharing.
Sure.
Yeah.
If they are there, I don't know what to do. I just stand by and watch, I guess, right?
Yeah.
Okay. I don't know whether people are equipped to join in. I don't know who all are there.
Yeah.
I have no idea.
Okay, that is the problem. Yeah, I guess. So, yeah. So Shomo, can you do something about it?
Yeah. So anyone can unmute themselves and speak. Yeah.
So maybe I can unmute myself now.
Yeah, as you wish. Yeah,
no, I don't know what to do. Yeah. So let me just see.
Yeah. So if anyone has to say anything about their interaction with Professor Seshadri. Yeah.
So.
No, I don't think there are people who will.
Yeah. So we'd like to conclude this session and thank you, Professor.
Hello.
Balaji.
Saurav Sen. Saurav Sen, this is Jugal Verma.
Wonderful. Jugal.
Yeah. So I would like to read what I wrote to the faculty of IIT Bombay. Just one
Please.
As soon as I got the news, next day I wrote something for the IIT Bombay faculty. So I would like to simply read that.
Sure.
Yeah, just one moment. So this I posted on 19 July. Yeah, this is a copy of my post to faculty of IIT Bombay. So I'll just read this. I think there is some noise coming.
Maybe I should.
Yeah, hello. So can you hear me?
Yes, we can hear you, sir.
Okay. We have lost a mathematician who had many other talents, such as accomplished classical music singer and a top administrator. His mathematics was of highest quality. It combined geometric insight with mastery over whatever mathematical tools were needed to solve the problems of contemporary interest. He could connect very easily to people of all ages. He was eager to discuss mathematics anytime with anyone. He remained active in research and music until the end. He built an institute in a PPP model that was unheard of in those days. His aim was to attract the best undergraduate students to take up careers in academics. For many decades, education at CMI was almost free. Although it was in PPP model, it attracted top mathematicians from around the world. This was due to the stature of Professor Seshadri. Whenever I met Professor Seshadri, at first at the SPIC Science Foundation in T Nagar, and later at the Chennai Math Institute, he would welcome me with a big smile and talk about whatever mathematics I was pursuing. And whenever I met him, I found him surrounded by many people who were eager to talk to him. And when I first saw the Chennai Math Institute and the statue of Lord Buddha, I could feel the sentiments that he had while building this institute. It's a unique experiment. It is extremely successful, and I'm sure that this will be his lasting legacy besides his beautiful mathematics. His philosophy in running the institute was very simple. This is what I could perceive: attract the best faculty, best students, and offer very demanding courses. Students of BSc at CMI usually know whatever we teach at MSc and even PhD level in universities. And it was no wonder that so many of them have gone on to the best graduate school, and some of them are faculty in the best places in the world. Seshadri solved Serre's conjecture in dimension 2, which was a major problem in commutative algebra. He was still a graduate student at that time. This work inspired several generations of mathematicians, as Balaji mentioned, that Pauman Murthy took this problem and it started a whole generation of research work by students, and it continues. But Seshadri's real love was algebraic geometry, a subject which is much more demanding, but well connected with all fields of mathematics. While he was at TIFR, the School of Mathematics at TIFR became a leading center of research in the world in algebraic geometry, and it was due to his courses, his inspiration, and his training at TIFR. Seshadri constants are now active areas of research in algebraic geometry, and as Balaji mentioned, there are many other areas which Seshadri has more or less created from scratch, which have enriched algebraic geometry. He was of course, the awards were mentioned that he was a recipient of Bhatnagar Award and FRS and Padma Bhushan. And for a man of that stature, these awards did not mean anything. He remained humble human being throughout his life, and we will miss him greatly. Thank you.
Thank you, sir, for your excellent words. Now I think we'll wrap up this session, and after this we'll have a lunch, and the next session will start from 2 p.m.
Thank you very much. Thank you.
Thank you.
So I'll stop. Thank
sure,
you. Thank
sure.
you.
Thank you, Professor Balaji.
Thank you, Balaji. It was a lovely talk. This is Vidhi, and I'm very happy to hear your talk. Thank you.
Yeah, Balaji is still there.
Yeah, he's here. Yes. Professor Balaji, are you here?
I think he must have left.
Yeah, maybe.
All right. All right. Okay.
Okay, sir. Yeah. Okay.
Yeah, I think we can start now. So let's start this session of analysis and PD, and we have Dr. Anisha Chorwarwala as chair. Okay.
Okay, so it's my pleasure.
Dr. Anisha?
Yeah. It's my pleasure to start this afternoon session of today's virtual math fest. And the first invited talk for this afternoon is by Dr. Anup Biswas, who is a colleague, my colleague here at IISER Pune, and a very established mathematician at a very young age. He is already on the editorial board of two very reputed journals, one of them being the Annals of Applied Probability and Pure and Applied Functional Analysis journals. So, the title of his talk today is Recent Developments in the Theory of Generalized Principal Eigenvalues in RL. So over to you, Anup, and thanks for accepting. At this
Thank you, Anisha. I guess you can hear me, right?
Yes, we can hear you.
Okay. Thanks, Anisha, again. And thank you, for taking this initiative for this virtual math fest. I'm sure many people are making use of it. A bit of apology because I already presented the same thing last week. So those who have attended, there is nothing new unless I say something in addition to which I have said in the last week. So what I would like to discuss is about, of course, what is a generalized principal eigenvalue. Of course, we probably do understand what we mean by eigenvalues, at least in the context of matrices. Now we have a principal eigenvalue, which we can also think of in terms of operators, and there is a way to define principal eigenvalue. But now we have another notion which is called generalized principal eigenvalue. And in what sense this is generalized, and what are the developments? So this is something many of us might have seen, and for classical course in PD or any the first course in PD, we might have seen this. So if you take a smooth bounded domain and you look at this, all these eigenvalues of this operator solving this Dirichlet boundary condition, right? And it's known that there exists a sequence of infinitely many eigenvalues and going to infinity, the first one being positive, solving this eigenvalue problem. Okay, and this eigenpair lambda and phi n's are known as eigenpairs, and the first one is referred to as principal eigenpair. Okay. Now, if you look at it, it should remind you compact operators, but the compact operator has a relation that eigenvalue should decrease to 0. But here, we are seeing it's going to infinity. The reason being the inverse of this operator, the Laplacian operator, is compact. So therefore, the Laplacian has eigenvalue going to infinity because the inverse operator is compact. Okay. Now, let me tell you a couple of properties that this first. So in this talk, I'm interested mainly this particular eigenpair, lambda 1 phi 1. Okay. So this first thing is this phi 1 has a fixed sign, whether you take positive or negative. Okay, it has a fixed sign, and lambda 1 is simple. So that means if you look at the eigenspace corresponding to this eigenvalue lambda 1, that is one dimensional. And you also have Rayleigh formula, Rayleigh's quotient formula, that lambda 1 can be represented as a ratio of two functionals. So that you can figure out from here. If you just multiply with the function phi n and take integration by parts, you get to this kind of representation. And when you look at the CC infinity functions, so this is infimum over CC infinity functions, but if you extend the space by h10, then it becomes minimum because the minimum is attained in this space. Okay. So this is another way to characterize lambda 1. So if you want to define lambda 1. Now, suppose I want to move beyond this Laplacian settings and want to understand what happens if I want to replace it with a more general form of elliptic operators. Okay, so this is an operator which is called in divergence form. So this operator is has a specific structure. So you take a positive definite matrix, so Aij, of course, depending on x, and then you look at this vector and then differentiate it, and yeah, that's how it's written. And then C is generally referred to as potential or zeroth order term. So I'll probably stick to the term potential because it comes from a probability theory. Okay, so this is the structure of the divergence operator, and this is the assumption I'm going to impose that it's called non-degeneracy assumption, that this Aij matrix, it's positive definite and its eigenvalue is never zero. Okay, in fact it's uniformly bounded from below. So C0 is the lower bound of the smallest eigenvalue, as you can see. Okay, so this is the next level of generalization of Laplacian, because if I take this to be identity, this fellow becomes Laplacian here. Okay, now what happens? So for this kind of operator, there is a way to define bilinear form. How do you define bilinear form? You just multiply this guy with a v and throw this derivative on v. So you actually get to this bilinear form, and it is somewhat analogous to Laplacian. So whatever you can develop for Laplacian is the same fashion you can develop for an operator of divergence form, so particularly operator of this form. Okay, so what helps us here is this bilinear structure. Okay, that plays a crucial role to apply. So this makes this operator symmetric, and there are other properties which is analogous to Laplacian. So you just follow the step of Laplacian to get to the results that corresponds to this divergence form operator. Okay, so there is nothing fancy here. So now let's move to a more general form of operator, which is known as non-divergence form operator. So this is the more general elliptic operator where I have Aijx. Okay, now this guy is outside the derivative. So derivative is double derivative is totally acting on u. That's a matrix, and then you multiply the matrix and take the trace. So you get this summation. That's a vector valued functions, and that's a dot product with gradient of u, and then there's the potential and u. So this is the most general form of linear elliptic operators in non-divergence form. Now, the question, of course, if we want to understand how to define eigenvalue, because we don't have any bilinear operator here, so Rayleigh's coefficient doesn't make sense here. So we cannot go to define a quotient formula or Rayleigh's quotient type and then take the infimum over some class to get to the eigenvalue. So that characterization doesn't work. So another way to see this is can one deal with a compact operator? So can one prove the inverse of L is a compact operator? Yes, that's possible. But the challenges with this is, so okay, let me just say it, what I want to say. So mostly we are interested in, if you recall, mostly we are interested in the principal eigenvalue. So that is the eigenvalue λ1 having a positive eigenfunction. Okay, so let's say if you're interested in eigenvalues here as well, with eigenvalues having positive eigenfunctions. Okay, now I mentioned that one can apply theory of compact operators and find an eigenvalue. So the extension of that theory is known as the Crane-Ruthman theory. So the Crane-Ruthman theory, what it does is it looks for the eigenvalues with positive or positive eigenfunction. In particular, it looks for eigenvalues with eigenfunctions in a cone. So when you apply a Crane-Ruthman theory, there is a cone that comes into a play. That cone sort of use ordering to that operator. So for example, if I take all the functions, all the non-negative functions, that forms a cone, and we can use that cone to give a ordering of that operator, and then we can apply Crane-Ruthman theory to find an eigenvalue with positive eigenfunctions. Okay, now that's a pretty powerful tool, and it requires a lot of estimate. Okay, and sometimes it's not easy to get those estimates. But this particular operator actually one can get. But on the other hand, so this is another one, and which is more powerful in some sense. So this a notion introduced by Berestytsky, Nirenberg, and Varadhan in 1996. Okay, so they used a maximum principal technique to define what we call, principal eigenvalue and eigenfunctions. So now remember, we are interested in eigenfunctions or eigenvalues having positive eigenfunctions. Okay, so this is our interest. For rest of the talk, I'm mostly interested in eigenvalues having positive eigenfunctions. Okay, and then I want to see how many eigenvalues having positive eigenfunctions. Remember, in case of Laplacian, we have only one eigenvalue with positive eigenfunctions. Okay, only one. There is no other eigenvalues apart from the first one having positive eigenfunctions. Okay, so now something that should come to your mind, because we are looking for eigenvalues with positive eigenfunctions. So in the setting of matrices, this should remind you positive eigenvectors, and that should remind you Perrin-Frobenius theorem, right? So Perrin-Frobenius theorem, what it says that if you take a matrix D, entries Dij, and all of them being positive, so then this lambda 1D, which is known as the principal eigenvalue, is the supremum of this mod lambda. This has this particular properties that this eigenvalues has an eigenvector with positive entries, and lambda 1D has a characterization, so infimum over all this lambda such that dv is less than or equal to this. And if you take the supremum, so this sign gets reversed. So here it is less than or equal to, now you get a greater than or equal to. So you remember this characterizations of lambda 1. So this is actually going to be useful in the later part of the talk. In fact, this is something we are going to make use of it. So you see, I can also define the principal eigenvalue with any of these characterizations that we have, the last two lines. Okay. Now, let me, okay, so this is actually the theory of Perrin. So the generalization of Frobenius was you can take, entries that is non-negative, okay? It could be zero somewhere, but the matrix has to be irreducible, okay? So that was the extension of Frobenius, and the same thing holds, okay? Okay, so now we come back to our operator. So this is our operator, and we want to define eigenvalue. So this is what Berestytsky, Nirenberg, and Varadhan did. So they used, so this is the characterizations if you see. So this is the supremum one. So it's kind of analogous to the one we are looking at. So you take the supremum over all lambda in R, okay? So those who are not comfortable with what W2N is, they can just take it as C2 functions, okay? This is much weaker than C2, but I mean, you can as well stick to C2, okay? Okay, so there exists a function, let's say C2, and continuous up to the boundary, satisfying this inequality and positive in D. Okay, so both this relation should hold in D. Okay, so this should remind you somewhat a Perrin-Frobenius type of definition. But also I had another one. If you go back, see, I had infimum and supremum and they coincide, right? Okay, so this is how they defined what they call generalized. So this is where the name came, the generalized Dirichlet principal eigenvalue. Okay. Now, so it has a couple of interesting properties. So one can show that this lambda 1, this fellow here, is attained by a positive eigenfunction. So there exists a positive eigenfunctions phi. You can have a C2 here, which is continuous up to the boundary. Okay, so that is attained. So that means if I put a lambda 1 here, so there would be equality with respect to the phi. Okay, this will be equal. And this is simple. That means if you look at the eigenspace corresponding to lambda 1, that's one dimensional. Okay, so what happens if I change the domain? So if I increase the domain, the lambda 1 decreases strictly. Okay, so this is a monotonically decreasing property with respect to the domain. So this is also it has. And you see this Perrin-Frobenius type characterization holds. Whether you take infimum, so then you have to look for sub-solutions. So if you go back here, I had super solutions, which is less than equal to sign. So if I take infimum, the sign flips, and I take, here, and I take sub-solutions, okay? And same class of functions, it has to be just positive, somewhere positive inside. you can take, in fact, positive total inside D. And another supremum, but here I want my psi to have infimum positive. So in previous definitions, I had psi positive inside D. It can vanish at the boundary, but here I want, I mean, it's also positive at the boundary. Okay, so even if you take supremum over that class, it all agrees with lambda 1. Okay, so these are, so you can say that these are other possible definitions of lambda 1. Okay, and all three definitions coincide. Okay, now what is the relation with C? So you see the C is the potential term that I have in my operator C. Okay, how it behaves with respect to C. So if I increase my C, okay, so then my lambda 1 decreases again. So if I have another one, C1, which is, let's say, bigger than C in a set of positive measure, then lambda 1 will be strictly smaller than lambda 1C. Okay, so this also, it has another property which is quite crucial and fundamental in PD, which is called extended or refined maximum principle. It says, suppose that my eigenvalue or the principal eigenvalue is positive. Okay, so I take an L for which this is true, then it has a maximum principle. What it means is that if I take any function u, which is a sub-solution in D, and u is non-positive on the boundary, then u has to be non-positive inside. Okay, so this is called a maximum principle. For obvious reason, you can relate it to the complex analysis. And now, okay, so this is called refined maximum principle. Why it is called refined maximum principle? See, in general, in PD, you see maximum principle where it is assumed that C is less than or equal to 0. Okay, so this term is assumed to be less than or equal to 0, then you get a maximum principle. Now you see, if I take C to be less than or equal to 0, my psi equal to 1 is an admissible function, and then you can prove that this guy is strictly positive. So it sort of takes that C less than or equal to 0 as a sub case, and this lambda 1 being positive is necessary and sufficient conditions to have maximum principle. So for example, if I have lambda 1 less than or equal to 0, you can prove that your principal eigenfunction has this two property, but not, it's not negative. So therefore, this is an if and only if conditions to have a maximum principle. And that's what makes it interesting to characterize when you can have a maximum principles, when you cannot. Okay, yeah. Now I would like to understand that what happens if I want to extend the domain D. So far we have been dealing with domains. There's a smooth and bounded, and you can of course relax the assumption of smoothness. In fact, the work of Beresitsky, Nirenberg, and Varadhan, they did it for what they call rough domain. So you can take any arbitrary domain, of course bounded, and the boundary should have a certain property. So in particular, Lipschitz domain is fine, but you can go even worse, and it should have a certain property, and that can be explained through a probabilistic phenomena called exit time. But anyway, I'm not getting into that. But they did it for bounded non-smooth domain. Okay. Now, of course, the next extension is I want to go for, let's say, unbounded domain. Okay, let's say smooth or all of Rn. So one possible extension is, let's do it for all of Rn. Okay, it's possible to do it for any unbounded smooth domains or non-smooth domains. It's not very difficult. It's kind of routine in some, there are certain tools one has to use, but I'm not going to discuss the possibility for any general unbounded domain. Rather than I'm sticking myself in D equal to Rn. So you take the unbounded domain and try to understand what is the notion of a generalized Dirichlet principal eigenvalue. Now Dirichlet won't make sense, there is no boundary, but yeah, so you can talk about generalized principal eigenvalue, eigenfunctions, and yeah, and so this 5 property that I listed for bounded domains, how much of them holds true when you have unbounded domain. So the thing that I would like to remember is, let me go back a bit. So that here, yeah, so this P1, see this lambda 1 is attained by a positive eigenfunctions, and this is the only eigenvalue with positive eigenfunctions. So that is also true. There is no other eigenvalue with positive eigenfunctions. Okay, so lambda 1 is the only one. Okay, so this is what you all is also holds in bounded domain. Now go back to Rn. So in Rn, so you see, I had characterizations of eigenvalues in bounded domains, and I showed there are 3 different representations for eigenvalues, and all of them agree. So these representations were like this. So first one is supremum when I take super solutions, positive super solutions in Rn. And here lambda 1 double prime, here I want my infimum to be positive. So this is one of the characterizations I had. And here I'm taking subsolutions, but then I'm taking infimum of subsolutions. Okay. And why I need it to be bounded, that will be clear in a moment. Okay, there is a reason you have to impose these conditions, that you take the bounded, positive bounded subsolutions. This will be probably in the next slide, why I have to restrict. But yeah, there are 3 different ways to define principal eigenvalue. Now the question is, which one should I pick? And yeah, and what is the relation between these 3 different eigenvalues I just defined here? Are they equal? What if not? Is there a possible ordering? And yeah, all these questions becomes relevant. I mean, to begin with, if you want to go further with this theory. Now, what happened is that, so this lambda 1, when I write lambda 1, I'm always looking at the supremum over all positive super solutions. Okay, so that's my definition. And why this is my definition is this, that if you take any lambda that lies below lambda 1, there exists a positive phi, okay, p bigger than n, satisfying this relation. That means any lambda below lambda 1 is an eigenfunction, is an eigenvalue. Okay, there exists a positive phi for that. So you see that therefore, unless I impose this particular condition, this infimum becomes minus infinity. Okay, and which makes this quantity sort of trivial. So therefore, I have to impose these conditions that I want only bounded. Okay. Yeah. And you see that there is an uncountable. In fact, there is a continuum of eigenvalues with positive eigenfunction. Okay, which is quite, I mean, different. In fact, very, very different for the case from bounded domains when you had only one eigenvalue with positive eigenfunctions. Now you see there is a continuum. Right? So that's the first difference. Now, second difference is if I assume that some sort of growth conditions on this matrix A. So if A grows at most quadratically and B grows at most linear and C is bounded, then I get an ordering between the eigenvalues. So the lambda 1 is bigger than lambda 1 prime and lambda 1 prime is bigger than lambda 1 double prime. So this quantity, these 3 eigenvalues that I've defined, they have an ordering. Of course, it doesn't exclude the situation that they cannot be equal. In fact, this is what happens. There is an example. This inequality, the last inequality here, can be strict. So therefore, they need not be equal. So unlike bounded domains, when all these 3 quantities are equal, this need not be equal. So why I chose, or why it is defined that I should pick lambda 1 is the principal eigenvalue, because this is the largest eigenvalue with positive eigenfunction. That is the reason for unbounded domains, we define lambda 1 is the principal eigenvalue. Okay. Okay. So now, as I said, that this lambda 1 prime, the green one, is less than, it could be strictly less than lambda 1. So I cannot expect equality for this. But how about the purple one and the green one? So that means lambda 1 double prime and lambda 1 prime. And in fact, it is left as a conjecture that, I mean, of course, there is a large family for which they are equal, but it's a conjecture of Beresitsky and Rossi that if you take A, B, C are bounded, then one must have these 2 equal. But the conjecture is still open and we don't know what happens. I mean, we don't know any counterexamples, and neither one has been able to prove that for all ABC bounded, they are equal. Okay, so this is a conjecture. They believe it's equal. Okay, now So now coming back to maximum principle, you see that for bounded domains, I have said the principal eigenvalue plays a crucial role in characterizing the maximum principle. But now, what would be the maximum principle in unbounded domain, or in particular in Rn? So you take a subsolution. So since the boundary is infinity, you impose the condition that at infinity it is less than or equal to 0. So if the maximum principle holds, then we should have u is less than or equal to 0 in Rn. Okay, so this is something extension maximum principle in unbounded domains, right? You start with the subsolution that is non-negative at the boundary. So boundary is infinity. So then it has to be non-positive at the boundary. So then it has to be non-positive inside. Okay. And the question, of course, we're interested in that just by looking at the eigenvalue or the principal eigenvalues of L, can I say that it has a maximum principle? And in fact, it is not the lambda 1 that characterize the eigenvalue, but the other one. So the lambda 1 prime and lambda 1 double prime. So these two quantity determines the maximum principle. So L satisfy maximum principle if only if lambda 1 prime is greater than or equal to 0. So it's a necessary conditions to have maximum principle. On the other hand, under the same growth conditions that I have stated before, lambda 1 double prime, if you take positive, then L has a maximum principle. Okay. So now you see that if these two guys becomes equal, which they have believed as a conjecture, so then this quantity lambda 1 prime characterizes the maximum principle. Okay, it sort of becomes if and only if, apart from the 0 case, of course. Okay, so that's the extension of maximum principle in unbounded domain. Okay. Now there is another property which I mentioned, that the monotonicity with respect to C in bounded domain. If you increase C, then the eigenvalue decreases strictly, but it doesn't hold true in unbounded domain. So what happened is that if you look at this map, okay, it did not be strictly monotone with respect to C. In other words, one can find two bounded continuous functions, C and C1, so that C lies below C1 and not equal. That means there is a ball on which C1 is strictly bigger than C, but the eigenvalues are same. Okay, so therefore the strict monotonicity property does not hold. Now, so the question can be that when can I say, it has a strict monotonicity? Okay. Looking at L or from some properties of the eigenfunctions, can you characterize this property of monotonicity with respect to potential? And why it is important, I'll try to say one line on this, why one is interested in monotonicity. But if you look at it as a fundamental property, so this is what we could be interested in. And then there are two different kind of monotonicity we could think of. Okay, so let's take, so this was introduced in the joint work with Arapostathis and Subhamay Saha. So this is, you take, let's say, C0 plus. So this is a collection of all functions which are non-zero and non-negative, okay, and vanishing at infinity. So you take all the continuous functions which are non-zero somewhere, and they're non-negative, cannot change sign, but vanish at infinity. Okay. Now we call it, this is monotone on the right at C. That means you add a H from this class, okay, and then eigenvalue, principal eigenvalue decreases, strictly decreases on the right, okay, because I'm adding H, so I'm sort of moving to the right. So we call it a monotone on the right at C. Now if I subtract H, okay, and it increase, we call it strictly monotone at C. Now what happened is that the strictly monotone implies monotone on the right. The reason being, one can show that this lambda 1 is a concave function with respect to C. Since lambda 1 is a concave function with respect to C, and if this guy increase, later on the function has to decrease, it cannot go flat. So strictly monotonicity implies monotonicity on the right, but not the converse. There are examples where the eigenvalue is strictly monotone on the right, but not strictly monotone. Okay. Okay. So now when such kind of So when this property holds, so this is a question. What's happening? Yeah, when such thing holds. So this is a probabilistic characterization, and just let me try to tell you briefly what it means. Is that so? You start with psi star, let's say the principal eigenfunction. Okay, so you take the operator L and psi star being the principal eigenfunction. You take the log because that's a positive function, so log makes sense. So I get psi star, small psi star. Okay, and so this is a diffusion process. If you don't understand, it's still fine. So this is the diffusion process having this as a generator, whatever it means, but that's a stochastic process. And there is a stability property of the stochastic process that determines the monotonicity property of lambda 1c. What happened is that lambda 1c becomes monotone on the right at C if and only if y star is recurrent, and this becomes strictly monotone if and only if y star is exponentially ergodic. Okay, so this exponentially ergodicity is stronger than recurrent. Okay, that's why the one below implies the one above. But it also has a very nice implication in criticality theory. What happens is there is a criteria known as Agmann's minimal growth criteria at infinity. It's pretty popular in criticality theory, and in fact it is used to prove that your principal eigenvalue is simple. That means the principal eigenspace is one-dimensional. Okay, now what we proved that this, Agmann's minimal growth criteria at infinity is equivalent to the operator is monotone on the right. Okay, so there it's equivalent. Okay, so this is this used a probabilistic argument at criticality theory. So this is done jointly with Rapostathis and Devdeep Ganguly. Okay, now let me point out a very interesting conjecture. Okay, it's called Landis conjecture. It was posed in 1960s. Okay, and still open. So what the conjecture is says that you take a solution U, okay, need not be positive. In fact, it has to be sign changing. I'll tell you why. So it just says that take a solution U of this equation, Laplacian of U plus V times U equal to 0. And V is bounded above by Q square. Okay, you can take 1. That means Q is 1. No problem with that. Now suppose that for some epsilon, we have U x is less than equal to e to the power minus q plus epsilon mod x. So that is the decay. So you impose the decay of u sort of an exponential fashion, but q plus epsilon. So this is important. So if I take epsilon equal to 0, okay, so let me state the conjecture first. So if I impose this decay, then q has to be identically 0. So that, okay. So now if I take u equal to, epsilon equal to 0, you can take in particular the exponential function e to the power minus q mod x type function to check that there is a non-zero function for which there is this equation has a solution. Okay, so here this epsilon important. Okay, and this is the conjecture of Landis from 1960s. Now, what has happened on this conjecture? Let me give you some cases. The conjecture is still open. Okay, as of now, so there is a little stronger version of this conjecture by Carlos Koenig. You can go to his paper and find out. So, okay, there is a modification of this conjecture. He proposed another stronger conjecture, but neither of them got solved. For n equal to 1, this was settled because this becomes an ODE, and then you can do a lot of things with ODE, and that was settled by Rossi in 2019. For n equal to 2, if we impose this u of mod x is equal to c epsilon times, here it is minus c mod x log to the power half mod x. So it's much worse than this bound, and also that for a large c, if it happens, then u is equal to 0. So this decay is quite stronger than the what given by Landis. And this paper was archived last week and by Logunov, Malenikova, Nadirazvili, and Nazarov, where they use some harmonic analysis tool to prove that this actually happens. And of course, a estimate on the nodal sets, nodal domains. Okay, now I said that this conjecture holds true for positive eigenfunctions. So we actually this work with Araposis and Ganguly, we gave a sharp lower bound, sort of matching this bound for positive eigenfunctions. Okay, in fact, for the operator L, which is more general than this. So if you take a positive eigenfunction, then this holds true. Not only that, if we assume your lambda1 of this Laplacian plus V, this operator is greater than or equal to 0, then Landry's conjecture holds true. So these are the two cases we could prove that the Landry's conjecture holds true. Another case is if your V has a compact support, which is also included in this paper, then the Landry's conjecture holds true. The way I see it, the only place where the Landry's conjecture becomes quite difficult, in fact, I think every other cases can be reduced to this particular case if you assume your V to be positive. Okay, so or positive of outside a compact set. So that is the place where it appears to be more challenging, because constructing green function at that level becomes very difficult. Okay, so this is on the operator. I started with L. I still have like 10 minutes or so, or maybe, yeah. Let me get into some other kind of question. Now, so far I just spoke about a lot on principal eigenvalue of linear degenerate elliptic operators, whatever the L thing I had. So of course the question can be, can we define the principal eigenvalue for other operators following the same technique coming from Berestovsky, Nierenberg, and Vardan, using super solution or parent-Frobenius type of representation, and look for positive eigenfunctions. Okay, because then you don't have to go for this Rayleigh's type of coefficients, or you don't have to look at the variational forms. And yes, and so for example, one can look for Pucci type operators, which is called nonlinear Pucci operator, which is of great importance because of its applications in homogenizations and control theory. So there is a lot of work done for that. Second is called the P-Laplacian operator, which is degenerate type operator but having a variational structure. For those kind of operator also has people have looked at it and worked on those kind of operators to study the eigenvalues. Okay, now this is another kind of operator which is known as infinity Laplacian operator. Okay, it's called the limiting operator of P-Laplacian operators. So now you see this operator has a very crazy form. It looks like the second derivative, or the second derivative part, or second order part, looks like gradient of u. Is there a question? Hello?
No, I don't think there is any.
Okay. So you look at the gradient of u, and then the d to u, that's a matrix, and then another gradient of u, and then you take the second product. Okay. So this is called the infinity Laplacian operator. Now, of course, the question is why it's called infinity Laplacian operator. Why the name infinity? It cannot be just the notation I used here, lambda infinity, sorry, delta infinity. There should be a reason. Okay, let me point out that part, why it is called infinity Laplacian. Okay, so first of question is how this operator came in business. I mean, why it became an interesting operator after all. Okay, so this is what happened. So in 60, I think G. Aronson, this guy, okay, he wrote, I think, 3 papers back to back, 65, 66, 67. And I think I have only read this 2, so I have listed this 2. So what he was trying to do, so it's called the absolute minimizer in a domain. So you take a domain, let's say you take a nice smooth domain in Rn, and you give a Lipschitz function on the boundary. Okay, suppose I've taken a domain and prescribed a Lipschitz function on the boundary, and I want to extend the function inside or outside without changing the Lipschitz constant. Okay, so this is the question I'm interested in, and one can easily give at least 2 functions. It's not very hard. That there are with that property that it matches with the function at the boundary having the same Lipschitz constant. Okay, I think it's called Maxian extension or something. So definitely it's not unique. At least two you can find. So what question Aronson was interested in, what extra condition I can impose on this extension so that it will make it unique. Okay, so the extra condition that he imposed on this, it should have this what he called as absolutely minimizing property. That means if I look at that extension and consider a small subdomain, okay, I cannot find a better extension inside the subdomain. So it's a very vaguely, but that's what it means. And when he sort of fixed this extra property on this extension, it sort of made this thing unique. Okay. Now this extension or absolutely minimizing functions is actually infinity harmonic function. So it solves a function, this guy is equal to 0. Okay. Now, of course, it doesn't justify why it is infinity harmonic. To see this is infinity harmonic, you look at the last line here. So if you look at the P Laplacian operator and you let P tends to infinity, the limiting operator is that infinity harmonic operator, and that's how it named this. It got this name, infinity harmonic operator. So this is the extreme operator as P tends to infinity. Okay. Okay. Now from the structure, it has a lot of degeneracy. Okay. And of course it's nonlinear because if you add two solutions, it does not, solve the same equation. You cannot superimpose two solutions. And there is a famous conjecture which is again still open, that if you take an infinity harmonic function, it has regularity C1 1/3. Okay. So in general, this is the best regularity you can expect. In fact, there is an example that has regularity C1 1/3. Okay. So therefore you cannot expect better than this. Okay. In fact, the function is x to the power 4/3 minus y to the power 4/3. And you can show that that solves this equation in whatever viscosity sense. And till that, the best known work is by Sabin in 2005 in dimension 2. He could prove that it is C1 alpha for some small alpha. And then later on, Evans and Smart, they could prove that it's everywhere differentiable. So this is, but the conjecture as a whole is still open. And I think probably one of the most challenging conjectures so far. Okay, so that's how this infinity Laplacian came in business. And one can consider an operator in a quite general form. So you add infinity Laplacian, then you have gradient nonlinearity. And then this is C is the potential, and then you look at u to the power cube. Okay, so that's the equation. Now here, why I want u to the power cube? Because this is 3 homogeneous. If you look at, so this guy is 3 homogeneous. In fact, I multiply u by tu, so t to the power cube would come out. So this is a 3 homogeneous or positively 3 homogeneous. Okay, and this is some conditions one would need on H. Okay, let me go a little fast. Now, as I said that, okay, there exists a solution which is not C2. So as I said in the slide before, that you cannot expect your solutions to have a C2 solution. So therefore, what is the best notion of solutions? Because of course I cannot make, give a meaning to this equation point-wise sense. So what would be the best way? And this is done by what is called the viscosity solutions introduced by fields metallist Lyons. And I'm not getting into this, but this is the definitions and how to arrive at this definition. It's possible. So you take functions that touches you from above and below and look at certain equations or inequations to hold. Okay. So you can prove that if you use the classical solutions, it should hold this kind of inequality. And from there you define viscosity solution. Okay. But let's not get into what do I mean by viscosity solution. The point to be kept in mind is, when I say a solutions, I mean viscosity solutions, because classical solution does not make sense. So here, as a similar fashion, I define my principal eigenvalue, but the point to be noted here is I want my function psi to be positive in all of d bar. Okay, it's not only inside, up to the boundary. So that's difference from the Varadhan, Beresitsky, Nirenberg, okay, whatever they had done, and d is a smooth bounded domain. And it's not only done by us, it's actually started from this, several work. So there is a work of Bhattacharya, Muhammad in 2012, Jutinian 2007, and later on by Berezovsky and others in 2015. So they all imposed this condition that it has to be positive all the way up to the boundary. Of course, the question is that if I allow it to be positive inside and can vanish at the boundary, whether this fellow would increase or not. Okay, I get a different value because I'm increasing my class of admissible functions, and that part remained open so far. And we settled this question by a joint work with Huang Hung Vo. So this is a function continuous up to the boundary, but positive only inside D. I don't want it on the way to D bar. And this is the characterization for the infimum, because I said there are 3 characterizations or 3 different kind of admissible functions. Okay, so this is the story for the bounded domains. The next challenge is if I want to increase it. Okay, there is an open problem here as well. We do not yet know whether this eigenspace corresponding to the principal eigenfunction, eigenvalue, is one-dimensional or not. Okay, so this problem is still unsettled. Okay, in fact, in the simplest setting where you have A is equal to 0, okay, and that setting also this problem is not settled. Okay, now the question is, if this work to unbounded domains, let's say Rn, what are the challenges? So the first thing was the Harnack inequality, which we are able to prove. So there are 2 works. The one is archived, you can find in my homepage. The other one we haven't archived. We're planning to do so. But yes, so there we prove that it has a Harnack inequality. And then you can talk about things in unbounded domain. And all these properties of eigenvalues in Rn, we could establish, and then we could look at a semi-linear equation like this, talk about existence, uniqueness, bounded positive solution, stuff like that. Yeah, so these are the recent extensions to the setting of infinity Laplacian, and I think that's it. Yeah. Thank you.
Thank you, Anup, for such a lovely talk. And I would open the floor for the audience in case there are any questions, comments, remarks. No questions? Let me check the chat window.
Are there any?
Okay. Yeah. So if there are no questions, we will take a 10 minutes break and we'll meet again at 3 for Sarika's talk. So
Okay.
short contributory.
Okay. Now it's stopped, right? Yeah. Okay, so 3 o'clock.
Thanks. Yeah, thank you, Anup, once again.
Okay.
Dr. Sharika, are you here?
I saw her online on Zoom.
Yes, I am here.
Okay, okay.
I am here.
You can try to share your screen. You can check
Yeah,
that.
sure.
Yeah.
Oh, so kindly allow me to share my screen.
Yes, yes. Now you can. Now you can do it.
Okay.
Wait. Soma, could you make? Yeah.
Hi, Sarika.
Hi, how are you?
Not bad. How are you?
Huh.
After a long time.
Yeah.
So yeah, you can make it full screen. Yeah.
Am I audible?
Yes.
Yes. Yeah. Okay. So we start at 3.
Sure.
Okay.
So Sarika, this is pronounced at Chocquard, right? Chocquard exponential nonlinearity.
Foucault. Foucault.
Foucault, I see. Okay.
Yeah, Foucault.
Mhm.
So right now, are you in ISER or
I
you
am
are
at ISER. I am at ISER. You are at Bennett University in Noida, right?
Right.
Okay. When did you have joined there as a faculty? Is it?
Yes.
Okay. When did you join?
4 years back.
Acha, acha. I see.
2016.
How is life there?
It's good.
I see. So your talk is for 20 minutes.
Yes. My
Yeah, I think we should start now. Is that okay with the advisors, with the organizers?
Yes, we can start.
Okay, so it's my pleasure to invite Dr. Sarika Goel for the second talk of this evening. So Sarika is a faculty member at Bennett University, Greater Noida. She is PhD from IIT Delhi. She completed her PhD in the year 2015, and she will be talking about existence results for fractional Kirchhoff equations with Coquard exponential nonlinearity. Over to you, Sarika.
We cannot hear you, Sarika.
Sarika, we can't hear you.
No. Are you muted?
Yeah. No, she isn't muted. So could you check your sound settings? We could hear her a while ago. I don't know what happened.
Sure, yeah.
No, we can't hear you, Sarika. Is something wrong from our side?
Shouldn't be. I mean, it shows that she is not muted.
Yeah.
Let's see.
No, Sarika, it's not audible. Can you hear us, Sarika?
I think she can hear us.
Ask her to join again. Probably that would help.
Yeah, Sarika, maybe you can leave and join again. Sarika, leave the meeting and join again.
Yeah, she just did it.
Oh, I could still see her, so that's why.
Yeah.
Hello.
Hi.
Yes,
yeah,
now we can
hear
hear
you
Now
now.
it's fine.
Yes,
Okay.
yes.
Yeah.
Yeah.
So yes, you are invited again to start your talk.
Oh, thank you.
Now you can share screen.
Yes, perfect.
Now am I audible?
Yes, you are audible.
Yes.
Okay. Thank you.
All good now.
So may I start now?
Yes, please do.
Yeah. Thank you for your nice introduction. So the title of my talk is Existence Results for Fractional Kirchhoff Equation with Coquard Exponential Nonlinearity. So this is the joint work with Dr. Tuhina Mukherjee. So these are the outline of my talk: introduction, applications, main result and idea of its scope, and then references. So in the introduction, first I will give brief introduction about the fractional Soholo spaces. Then I will come to the fractional PDE and its variational setup. Then I will discuss the work which I have done with my calibrator and the main result and brief idea about its scope. So first of all, I define what is fractional Soholo spaces. Basically, it is For S belonging to 0 and 1, P from 1 to infinity, we define WSP for Solar spaces of order S and P is exponent P of omega, where omega is any open set, as U is in LP such that this quantity belongs to LP of omega cross omega, and it is a Banach space Indo with this norm, and for P is equal to 2, it becomes Hilbert space. And these are the embeddings, which is known as the fractional solar spaces embedding. So for omega open and bounded with smooth boundary, for S belonging to 0, 1 and P lying between 1 to infinity, in case if n is greater than Ps, WSP can be embedded into LQ for every Q belonging to 1 to NP upon n minus SP, and it is compact when it is when Q is not equal to NP upon n minus SP. In case n is equal to SP, WSP can be embedded into LQ for every Q belonging to P to infinity, and this embedding is compact. And if SP is greater than S, then WSP omega can be embedded into C0 alpha, with alpha is equal to SP minus n upon P. So the exponent NP upon n minus P is known as fractional critical exponent. So basically these fractional solar spaces, these are useful when we study the fractional PDE. So first, let me introduce, suppose the problem PF is given. So this is a P fractional Laplacian of U is equal to f of x comma u in omega, and u is 0 on Rn minus omega. So the variational setup for this fractional Laplacian in case of P is equal to 2, that is given by Sarvadei and Valdinosi in 2012, and for journal P, that is studied by me and Srinath in 2015. So for n greater than equal to Ps, omega, which is open and bounded domain with smooth boundary. So we want to study, so we are looking here for the variational setup for this type of equation. In general, this fractional Laplacian operator can be defined in many ways, but the way which we are defining, that has the variational setup. So for n strictly greater than Ps, the nonlinearity f of xu will be behaving like a polynomial kind of thing. And when n is equal to Ps case, then nonlinearity is become exponential type of u. So basically what is the idea? As we can see this exponent in the solo embedding, what is the critical exponent? The critical exponent is np upon n minus Ps. So when n approaches to Ps, this quantity become infinity. So it means that the nonlinearity will behave like exponential kind of thing. So that is why whenever we study any PDE, in case of n is equal to Ps, so the nonlinearity will always behave like exponential kind of thing. And whenever we are studying n is greater than Ps, in that case nonlinearity will behave like polynomial kind of thing. And one more thing, as s approaches to 1, it the fractional Laplacian thing will reduces to the usual Laplacian. So if I am taking in journal P, that reduces to P Laplacian. So the P fractional Laplacian that is defined in this form, this is defined in the integral form, and this is a P fractional Laplacian operator is also known as non-local, because if we calculate the value of fractional P Laplacian at any point, we need to know the function and in whole of the domain. But that is not the case with the usual Laplacian. So one can study this type of equation for general non-local operator. So I am giving you this minus LKU is equal to f of x comma u in omega, and u is equal to 0 on Rn minus omega. So here the non-local operator which is defined as given by this integral. So one can note that if I take kx to be particularly 1 upon x to the power n plus ps, this non-local operator, general non-local operator reduces to the p fractional Laplace operator. And if k satisfying these 1, 2, and 3 properties. So one can study this, one can also study this general operator rather than the p fractional Laplacian operator, because that covers the p fractional Laplace operator. So one more thing, due to this non-local operator, we consider the function space as x naught. We don't work with WSP, because as you have seen in WSP, in the norm we have integration over omega cross omega, but the space that we are defining here, that has an interaction between omega and its omega complement. So we consider x as all those g which are measurable function. G restricted to omega is in LP, and this quantity is in LPQ. Basically, LPQ is nothing but R2n minus omega complement cross omega complement. So the space x, if I endow with this norm, that becomes the Banach space. So if I am working with this problem, so here u is 0 on Rn minus omega. So for that, what I am defining x naught as all those g in x naught, x, such that g is 0 almost everywhere in Rn minus omega. And I am considering z with this norm. In that case, x naught become Banach space, and in general for p is equal to 2, it becomes the Hilbert space. And moreover, this knob, this involves the interaction between omega and Rn minus omega. And one can easily see that x naught and the space x, whatever we have defined, these are the subset of WSP omega. And the embedding, the same embedding, so embedding works with this space x naught itself also. So as we know that if we want to find the existence multiplicity of given PDE, basically what we do, we identify the solution, we talk about the weak solution, and we identify those solution as a critical point of some energy functional. So the same here, we are defining a function u in x naught is a weak solution of the problem PF if you satisfy this equation, and we are identify this weak solution as a critical point of the functional j, which is given by this. And one can easily see that j is pressure differentiable, and j prime of u at phi is given by this equation. And with this variational setup, one can find the solution as usual critical point here. So basically, recently this non-local operator or the fractional operator, many author has a lot of interest to study this non-local operator because of many applications in engineering. So one can see like quasi-geostrophic equations, Fractal-Burger equation, stochastic differential equation. So as I have written some equation, and one can note that this fractional thing is appearing here. So similarly, in the fractal conservation law, it's also appearing minus Laplacian to the power, to the power alpha. Similarly, in the Fractal-Burger equation. So now I come to the problem which I have done with Dr. Sohina. So here minus m of u I have taken. So this is basically n by s I have taken. So it means n is equal to, I am in the case of n is equal to PSK. So here the nonlinearity will behave like exponential kind of thing. So this m is Kirchhoff operator, and this is fractional Laplace operator. And in the right hand side, you are saying here one integral term is also there. So here I am assuming this is Coccard type nonlinearities. And u is 0 in Rn minus omega. So omega is bounded domain with Lipschitz boundary, n is greater than equal to 1, s lying between 0 to 1, and g behave like exponential, and this quantity is known as n by s. Like earlier I am saying it's p fractional Laplace operator. So if I am taking p to be n by s, so it is known as n by s fractional Laplace operator, which is defined as same as I have defined earlier. So basically such type of problems, these are motivated by the Hardy-Littlewood-Sokolov inequality and the Moser-Thüringer inequality. So this is the Hardy-Littlewood-Sokolov inequality for T and R greater than 1 and mu lying between 0 to 1 with this condition. G is in LTRN and H is LR of Rn. We can find there exists a constant C such that this equation 2.1 hold. In particular, if T is equal to R is equal to 2n upon 2n minus mu, then this constant is explicitly defined. And when G is multiple of H, then in that case, inequality is becomes the equality, and these are and one can find these minimizers. Hx is in this form. So now before defining the Moser-Thüringer inequality, I denote W. I define W as n by s node tilde. That is the Solar spaces as a completion of CC infinity with respect to this norm. So basically in 2015, Martinezzi proved this Moser-Thüringer inequality. So for omega is bounded open domain, then there exists a constant alpha ns such that this supremum of this quantity finite for alpha belonging to 0 to alpha ns. And they also prove that this supremum is finite for alpha is strictly greater than alpha ns star. Means there is another alpha ns star such that the supremum is finite. But what is still open, that whether alpha ns is same as alpha ns star or not. So as moreover there exists, I told you, alpha ns star greater than equal to alpha ns such that the supremum become infinity. And in 2018, even the Ruff and et al. Prove the explicit value of this alpha ns star, but this is still open whether alpha ns star is equal to alpha ns or not. And this M is Kirchhoff operator with satisfying the following condition, like M is continuous function. We satisfy the assumptions M1, M2, and M3. So I'm considering one example. One can consider in journal MT is of this form, M0 plus AT of gamma minus 1, where M0 or A0, A is greater than equal to 0 and gamma is strictly greater than 1 such that M0 plus A is strictly positive. So one can easily see that this M is satisfying the condition M1 to M3. So here the Kirchhoff operator, we can talk about degenerate Kirchhoff operator or non-degenerate, which depends, like if M0 is 0, then it becomes the degenerate case. When if M0 is non-zero, then we call it non-degenerate. Similarly, the nonlinearity G is satisfying some assumptions which are given by Z1, G2, G3, and G4. And then G5. Basically, and one of the example of this G is as hxt to the power mod t upon n minus s. Hxt is 0 if t is less than equal to 0, and t it is like t to the power alpha plus gamma n by 2s minus 1 exponential of dt beta if t is positive. For some alpha and d lying between 0 to alpha ns and beta lying between 1 to n upon n minus. So one can easily see that this G verifies all the conditions. So the main result, we obtain the existence of non-negative and non-trivial solution in this case. So if the condition M1 to M3 and G1 to G5, these are whole, then we show that the problem M admits a non-negative, non-trivial solution. So the function space, we consider X0 as all those u in W s comma n by s of Rn such that u is 0 and Rn minus omega with respect to this norm. And weak solution of function u belongs to X0 is the weak solution of this problem M if for every phi in x0 it satisfied this relation, and the energy function associated to that problem is given by this. So the integral, the each term is well defined. So the second term is well defined because of the Hardy-Littlewood-Sokolov inequalities. And one can easily see that it's fractional differentiable, and we identify critical point as the weak solution of this problem. So what are the key steps? First, we show that this function satisfied the mountain pass geometry. So it means that mountain pass geometry, we need to show j of 0 is 0, and out in the sum ball, inside that ball, it is taking positive value, and outside that, it is going to be negative. So in that case, we have like mountain type structure. So it means that it's satisfying mountain pass geometry. Then we define the min-max level, and we identify this critical level. The crucial thing is to prove this min-max level, the critical level. So, and we show that below this critical level, it satisfied the Fleischmann condition. And this we prove with the help of Moser functions. So these are the sequence of Moser function like in the local case. And we show that the so mountain pass geometry give you the existence of Fleischmann sequence. So once we have the Fleischmann sequence, we show that the energy function is bounded, and then we show that if it is a Fleischmann sequence, then we can find u such that uk converges to u weakly, and we can easily pass the limit. And then we show that it satisfied the Fleischmann condition at C star, and we show that yeah, there are many mathematical technical involved in this proving all these details, so that I have not added it here. So after that, we show that it's a non-zero solution of the weak solution of the problem, such that j of e is equal to C star. And these are the references. And thank you so much.
Sarika, are there any questions from the audience?
Hi. Can I ask a question?
Yeah, sure, Anu, please go ahead.
Yeah, Sarika. Okay, interesting operator. I just want to ask one question. So in one of your conditions, you required alpha ns equal to alpha ns star, right?
That condition is not required basically. Like as you know, in the local case, like in the N-Laplacian or Laplacian case, there it is alpha ns is same as alpha ns star.
Okay.
But here,
yeah.
So, but here this is open.
No, but yeah, you go back to your, I think G5 or something.
Yeah.
So, yeah,
so
G5.
that is why we assume this condition here. So if alpha is not equal to that alpha ns star, we show this level. We show this level, but if, because we know that whether alpha ns is alpha ns star or not.
Yes,
So
if this happens, so
we assume this condition, otherwise we are able to show the existence of the psi function.
Okay, otherwise, okay, so if alpha is alpha ns star, so then this should hold, and otherwise
we are able to show this condition.
Okay. Yeah, got it. Okay, thank you.
Any other question or? No questions? I'm just checking the chat window. Okay. Yeah, thank you, Sarika.
Welcome.
So we'll meet in 3 minutes for Ratan Kumar Giri's talk. Okay. Yeah, see you there.
Thank you, Anisha.
Yeah, thanks, Sarika. Bye.
Yeah, welcome. Bye.
You have to unpresent your presentation.
Yeah, that I'm doing it.
Okay. Yeah. So I hope Ratan Kumar Giri is online.
Yeah, hi.
Yeah, please share your slide.
Yes.
Yeah, we'll meet in a couple of minutes. We'll start in a couple of minutes. Yeah, maybe we can start now. So it's my pleasure to invite Dr. Ratan Kumar Giri, who is from Technion Israel Institute of Technology. He has completed his PhD from NIT Rourkela in the year 2018. And the title of his talk for this evening is Superchloric Functions for the Parabolic P-Laplace Equation in the Fast Diffusion Case. So yeah, welcome, Dr. Ratan Kumar Giri.
Hello everyone. I am going
Hi.
to speak. Am I audible to everyone?
Your volume is a bit low, Ratan.
Could you speak a bit louder?
Yeah, a bit louder.
Okay.
Yeah.
Now it's fine, right?
Yes, yes.
Yes, yes.
So I am going to speak about a generalized class of super solution, so-called supercaloric function related to.
So, Ratan, sorry to interrupt. Your voice is, I think, not a constant volume. It is fluctuating. So maybe your mic is not stable. Maybe it is moving or because a while ago it was fine and then it was like a bit fluctuating.
Now it's okay.
Yeah, but it should remain this way. It shouldn't fluctuate.
Okay, I'll try.
Yes, please.
Yeah. So I'm going to speak about a generalized class of super solution, so-called supercaloric function related to parabolic T-Laplace equation, and it is a joint work with Professor Joachim and his PhD student at my previous workplace, Aalto University, Finland. This is the outline of my talk. Here is the PDE, parabolic T-Laplace equation. I will speak about in the singular case, which means the parameter P lies between 1 and 2. We will discuss here super solution related to this PDE. Although there are several ways to define a super solution, here we will consider the notion of weak super solution, which is defined through weak formulation of the problem under integral sign. Then I will speak about P supercaloric function, which is defined through, for example, by using a weak comparison, by using a comparison principle. The main goal of this talk is to discuss the possible collection between these two classes of functions. More precisely, what I mean to say is that take a P supercaloric function. Now the question is that does it belongs to a certain Sobolev space? If it does, what do you have to assume? What is the nonlinear theory of P supercaloric function in this condition? Related to all these questions, I will discuss here. Okay. When we have a PD, it's always a good question. What is the domain of definition here? In principle, here we are in Rn plus 1, where the last dimension is related to the time. Actually, we could speak about solution, super solution to the PD in an arbitrary domain of Rn plus 1, but we will consider here the space-time cylinder, which is given by omega t, and we have parabolic boundary, which is defined like this. Similarly, space-time box and its parabolic boundary is defined. Well, when we talk about weak solution or super solution to a PD, we need to somehow assume a certain Sobolev space as a solution space. Here we consider our solution space is the parabolic Sobolev space. It is denoted by this, and it consists of all functions u, all measurable functions u, such that for a fixed moment of time, it is in the Sobolev space, and if we fix x as a function of t, it is in h. One observation here is that no regularity in time is assumed. There are some certain articles where the regularity in time is assumed. Thus, we say that a function u is a weak solution to our problem if u belongs to this parabolic Sobolev space locally, and it satisfies this integral equality for every completely supported Newton's function in our domain. If this integral is non-negative for every non-negative x function, then we call it as super solution. Similarly, sub-solution is defined. And if the weak solutions are continuous, we call it as p-caloric function. We divide our problem into two cases, basically depending on the value of p. One is subcritical type if p lies between this range, and another one is supercritical type if p lies between this range. Now the question is, what about regularity? The weak solutions are in fact locally Holder continuous, and for the supercritical case, the weak solutions are in fact locally bounded. However, in the subcritical case, there exists some unbounded weak solutions. Due to the non-local nature of the problem, we cannot add constant to a solution. Solution cannot be scaled, and sum of two solutions need not be a solution in general. But there are something which works. We can truncate. So take a solution and truncate it. Then you do not have a solution anymore, but you do have a super solution, which is a good thing here. And also, the super solution for the case when p is bigger than 2 are lower semicolon. One important observation here is that when we talk about solution, then PD tells us some regularity in time. But when we talk about super solution, PD does not tell us anything about it, anything about regularity in time. For example, if you take this step function, it is a nice function and constant locally. It is not a solution, but it is a super solution. Okay. When we have a PD, we always wanted to know what is the worst possible solution that we may have. Here is the Baron-Blood type solution for the supercritical case. The Baron-Blood type solution is not defined for the subcritical case. It looks a bit complicated. However, it is in explicit form, and it is a solution to the problem, our problem, in the upper half space. But thing is that, but it is not a super solution in any domain containing origin because it fails to belong to correct Sobolev space due to the gradient term. Because the gradient fails to integrable to the root power like over here. So this example tells us that if you take the truncation, then it belongs to the certain Sobolev space and they are weak super solutions. So this example tells us that increasing limit of super solution may not be a super solution. Now the question is that what is the class of function which is closed under this increasing convergence? The answer is P supercaloric function. A function G is said to be a P supercaloric if it is lower semi-continuous against in a subset, and it obeys the parabolic comparison principle in each S-time boxes. If you think about the elliptic case, this class of functions are known as superharmonic functions, and as we know that any straight line is harmonic, so the comparison principle tells us that this superharmonic class of functions looks like convex functions. And one important observation here is that this P supercaloric function does not actually belongs to a parabolic Sobolev space. But the only connection with the PD is through this comparison principle. Here I listed some examples of these supercaloric functions. For example, the zero extension of Baron-Blood type solution, it is not a super solution, but it is a P supercaloric function. Similarly, the this step function, it is not a solution, but it is a P supercaloric function. Now let me show you what is known to us. So for P bigger than equal to 2, every bounded P supercaloric function is a weak super solution. And for the unbounded case, P supercaloric functions are divided into two mutually exclusive spaces depending on it belongs to L log P, LP minus 2 flow or not. If it belongs to LP minus 2 locally, then it is in fact in L1 and it is a super solution to our problem. And if it does not belong to LP minus 2 locally, then there is just time slice in which the function is precisely infinity. One such example of this class of function, which is I called as a complementary class of, this is called Baron-Blood type solution, Baron-Blood type class of function, and this is complementary to this. So one example to this class of function is basically friendly giant. And this function, you take this function where U is a solution to this PD, and it can be obtained from by separable of variations. So now the question is, what about the similar case? And that is precisely our goal to discuss here. I will first consider the bounded case, then I will speak about the unbounded case. For the bounded case, we have shown that every bounded P supercaloric function is also a super solution for the full range of P, which means I will to say that P is between 1 and infinity. There will not be any problem. To see this, we mainly use three results. The first one is the obstacle problem. It says that there is a weak super solution, which is in fact unique, such that U is greater than equal to psi inside the domain, where psi is the continuous obstacle, and U coincides with psi on the parabolic boundary of metal. And in this open set, U is in fact be continuous weak solution. And moreover, it is the smallest weak super solution above psi. The next result what we have used is basically Cacciopoli type energy estimate. It says that if you have a bounded weak super solution, then the LP norm of gradient is locally bounded. Okay. We have obtained this estimate by basically treating this test function in our time modified equation. Next result what we have used is basically the point-wise limit of sequence of super solution. It says that if you have a uniformly bounded sequence of super solution, then the limit is also a weak super solution. That's the result says basically. So here is the main result for the bounded case. Again, I am saying that we have proved that every bounded weak super solution, every bounded P supercaloric function is also a weak super solution for the full range. There will be no problem. To see this, we mainly use the truncations and the lower semi-continuity property of P supercaloric functions. Since P supercaloric functions are lower semi-continuous, so we can approximate it by a continuous increasing sequence of continuous increasing sequence of continuous function by a sequence of continuously increasing function. Now you solve obstacle problem for each size and you will get a super solution. Now take the case. That is how the theorem is proved. Okay. Now let us move to the case when the physical function is unbounded. And we will consider here the case basically when P lies between in this interval, which means we are considering the supercritical case. We still don't know what happened for the subcritical case. The main key idea what we have used here is to again consider the truncation and to apply measure type iteration by using Sobolev inequality and Cauchy-Cooley type energy estimate. Here is the Sobolev inequality in parabolic settings. It looks like this, and the second one is the Cauchy-Cooley type energy estimate for the unbounded case. It looks a bit crazy. However, we have obtained this Cauchy-Cooley type energy estimate by using this as a test function in our modified equation. Basically. So here are the following results we have shown for the supercritical case. It says that if we have a non-negative T supercritical function and if it belongs to L alpha lobe, where alpha is bigger than this magical number, then we have beta integral. And we have obtained this magical number from our construction of the Q. And for the gradient term, it belongs to L2 lobe whenever Q less than this exponent. One important remark I want to mention here is that if T bigger than this number, then this exponent is strictly greater than 1. So in this case, the gradient U exists in the Sobolev sense. But if T lies between in this range, then this exponent is strictly less than 1. So in this case, we cannot think about the gradient U in the Sobolev sense. So in this case, we have interpreted gradient U as a limit of truncation. And if we interpret gradient U in this case, for this case, when bigger than this number, then it coincides with the Sobolev gradient almost everywhere. And here is the Barnum-Blatt type profile for the unbounded case. Of course, we are in the supercritical case. It says that if U is non-negative and if it belongs to this LP space, then it is a super solution. Now the natural question will come here. What happens if U does not belong to this space basically? And here is one such example. This function U infinity. It does not belong to any L2 space for Q greater than this magical number. And however, it is P supercaloric and it is not a super solution in any domain containing origin. So here is the complementary type to the Barnum-Blatt type solution. It says that if we have a non-negative T supercaloric function and if it does not belong to this case, then there exists a point in the space in which where the function is precisely infinity. If you recall the case when P is bigger than 2, then we will have a singularity in time. But for the singular case, we will have a singularity in space, not in time, which is a different thing. So to show this, we have used mainly the Harnack type inequality for the continuous mixed solution, and also there is a version of Harnack inequality for the with super solution as well. By using these two, we have shown that this type of profile holds. So before I conclude that, let me conclude that what we have seen so far is that every bounded T supercaloric functions is a weak super solution for the full range, and for the supercritical case, every one unbounded T supercaloric function are divided into two mutually process depending on if it belongs to L log P space or not. If it belongs to, then it is a super solution. If it does not belong to, then there is a point in the space with one which the function at which the function is precisely infinite. That's all I want to say. Thanks.
Yeah. Thank you, Ratan Kumar. The talk. Are there any questions from the audience? I'll just check the chat window. Okay. So in case there are no questions, Ratan Kumar for this talk. Thank you. Okay, we'll meet at 4 o'clock for 2 more short talks by Pratik Kumar Vishwakarma and Veer Singh. So 2 10-minute talk waiting after the break. Okay.
Hi, Pratik, can you hear us?
Hello. Sir. Yes, sir. I can hear you.
Okay, very good. So you can try to share your screen now.
Oh, yeah.
Sorry, I just realized that my mobile was not on mute.
Okay. Yes, it's perfect.
Is the screen visible, sir?
Yes, yes.
Okay. Thank you.
So Pratik, you are a PhD student.
Yes, ma'am. I'm a PhD student.
I didn't get you what you said.
I'm a PhD student. Yes, ma'am.
Okay.
You're
Okay.
right.
Sure. Thanks. Are you working with Manjunath?
No, I'm working with Apurva Khare.
I see.
I did my master's project under Manjunath, sir.
Okay, because I saw I was googling your name to just get the details, and I saw Manjunath's name somewhere, so I assumed.
Yeah. I mean, I think I'm on his. My name is on his website under integrated PhD student or something.
I think that's what I saw there. Okay, so we'll start in next 3 minutes. It's still 3:57.
Yes.
So your sound and video, everything looks perfect right now. Yeah.
Thank you.
Okay, I think we can start now. Grab a cup of tea, coffee, or any beverage of your choice in the short break that we had. So in the last session of the day, we have two short talks. The first one of them being by Pratik Kumar Vishwakarma, who is a PhD student at IISc Bangalore. His talk is Positivity Preserves forbidden to operate on diagonal blocks. Okay, over to you, Vishwakarma. Welcome.
Thank you, ma'am. Hello, everyone. Before we begin, I would like to thank the organizers for conducting this meet and letting me speak here. In this talk, we discuss about the classification of functions that act on matrices in the entry-wise fashion and preserve the cone of positive semi-definite matrices. Positive semi-definite matrices are Hermitian matrices which have non-negative eigenvalue, or equivalently that the corresponding quadratic form is non-negative over Cn. This directly implies that the class of positive semi-definite matrices is a closed convex cone, meaning that the class is closed under pointwise limit, summation, and positive scalar multiplication. In this talk, we focus on the class of PSD matrices which have entries in the interval minus rho or rho positive or infinity, and the entry-wise functions that preserve the positivity of this class. We use the notation Pn to denote the class of all n by n PSD matrices, and Pn of I to denote the class of all n by n PSD matrices which have entries in the set I. So the search for entry-wise positivity preservers began with the discovery of the Schur product theorem, which states that the entry-wise product of positive semi-definite matrices is again positive semi-definite. For instance, this implies that the k-fold entry-wise product of a positive semi-definite matrix, as shown in the picture, is again positive semi-definite. This implies that the monomials, when act on entry-wise on any positive semi-definite matrix, yields positive semi-definite matrix. This, along with the fact that the class of PSD matrices is a closed convex cone, any convergent power series with non-negative coefficient is again an entry-wise positivity preserver. Such power series are also known as absolutely monotonic functions. It was not very long after Polya and Zigo that Schoenberg proved that there are no continuous, non-absolutely monotonic entry-wise positivity preservers. This result of Schoenberg was later improved by Rudin, in which he removed the continuity assumption of Schoenberg and showed that the class of entry-wise positivity preservers coincide with the class of absolutely monotonic functions. This Schoenberg-Rudin theorem is gaining recent attention due to its applicability in modern analysis. And in one of those applications, it was necessary to understand the classification of entry-wise positivity preservers which acted on off-diagonal entries. This classification was obtained by Gu and Rajaratnam in 2015, in which it showed that such entry-wise positivity preservers are those absolutely monotonic functions which are bounded above by the modulus function. To summarize, in the beginning, we saw the entry-wise positivity preservers which acted on all the entries of the matrices, and that they are all absolutely monotonic. Then we saw the entry-wise positivity preservers which acted on off-diagonal entries, and that they are also absolutely monotonic. In this work, we have generalized to the idea where the function f is operating on generalized off-diagonal entries, in the sense, for instance, as shown in the picture, where the function f is forbidden to operate on the first principal 2 by 2 block, but is acting on A33 and so on. We have pushed this idea one step further, where the function f, where a given different function g is operating on the entries where the function f is not operating. More precisely, if suppose Tn is a subset of power set of bracket n, where bracket n is the set of integers 1 through n, then in the operation g of Tn, function g operates on the principal blocks which are indexed by the sets sitting inside Tn, and the function f operates on the rest of the entries. For instance, if T3 is the set containing 1, 3, and 2, then in the operation g of T3, function g operates on operates on principal blocks indexed by 1, 3, and 2, and the function f operates on the rest of the entries. Similarly, when T4 is the set containing 1, 2, 3, 2, 4, then the operation g of T4 looks like as shown in the picture. Note that in T4 there are sets that are intersecting with each other. we allow such intersections in our set of results. Now, the question that we ask here is of the classification of the functions g and f such that the operation g of tn preserves positivity over pn of I for all n given any sequence tn. Observe that the question here allows us to assume that there are no comparable sets sitting inside any of the tn's, because the smaller set would be redundant. Because of the time constraint, I would like to stick to the case where g is the identity function from now on. Please have a look at the paper for more refinements. Note that when Tn is the empty set, the function f operates on all of the entries, and which leads us to the Schoenberg-Rudin theorem. And when Tn is the set of singleton subsets, set of all the singleton subsets of set bracket n, the function f operates on all the off-diagonal entries, which leads us to the Giu-Rajaratnam's result. And in both of these cases, as we have seen, that the preservers are absolutely monotonic. Now, to look at the new preservers where Tn's are different than these two cases, we look at this result. Now, suppose f is a real function on the interval I, where I is the interval minus rho for rho positive or infinity, and Tn is the subset, and Tn is a given sequence for which each Tn is a subset of power set of bracket n, such that none of the Tn's contain the set bracket n itself. This extra assumption on Tn is there to make sure that the function f is operating on arbitrarily large matrices, essentially to make sure that the classification that we obtain is of dimension-free character, is dimension-free. Now, under this setting, the following are equivalent. That is, the operation ftn preserves positivity over pn of I for all n, if and only if the function follows the following characterization. Now, the characterization here depends on the sequence tn. So, for instance, in the first case, if in the sequence each tn is the empty set, that is, the function f operates on all the entries, as we have seen in the Schoenberg-Rudin theorem, that the function f has to be absolutely monotonic. In the second case, where the function f is forbidden from some only from some diagonal entry of large enough PSD matrices, and in which case, as we have found, that the function f has to be absolutely monotonic and has to be bounded above by the identity function over the non-negative side of the interval. Note that a particular case of this, in this case, leads us to the Giu-Rajaratnam's result. Now we move on to the third case, in which the function f is forbidden to operate on at least one 2x2 principal block, in which case, as we have found, that the preservers are all linear functions which vanishes at the origin, and where the coefficient c could be negative if each of the Tn is the partition of set bracket n, and the number of parts in Tn is uniformly bounded. Note that this is the case which yields us the first non-absolutely monotonic entry-wise dimension-free preserver. Now, for the rest of the remaining subcases of C, the coefficient C has to belong to the closed interval 0 to 1. And finally, for the case where the function f is forbidden to operate on at least two intersecting principal blocks, the preserver's f has to coincide with the identity function in this case. Now we have seen that with having seen this classification, we observe that this classification has brought the classical result of Schoenberg-Rudin and the modern result of Giu-Rajaratnam under the same frame of work. This classification has also yielded first examples of dimension-free non-absolutely monotonic entry-wise positivity preservers. Since the search for such entry-wise positivity preservers began with the observation of Pauli and Zico. This work has also increased the richness of the preserver problem by introducing the notion of two function GF preserving positivity, and the initial classification done along this direction follows us to a problem which could improve upon the work done on the critical exponent of graphs. Here are the references. Thank you. I'll stop here for questions.
Thank you for this very delighted. Questions from the audience? No question? Okay, in that case, let's thank the speaker once again. Thank
Thank
you.
you, ma'am.
Thank you very much. Yeah. So we'll meet in say 3 minutes for our next talk in the meantime, Veer Singh can try to present his PDF file. Thank you.
Thank you, ma'am.
Are you there, Veer Singh? Yeah.
Hello.
Yeah. Hi.
Yes, ma'am. Is my video there?
Your screen, we can see the screen,
Yeah,
but
yeah.
we can't
Right,
see
right.
the file.
Okay, just a minute.
I can
Is
only
is
see
it
your
there?
desk. Yes, yeah, now it's visible.
Yeah.
So you are also a PhD student at Shiv Nadar University, right?
Yes, ma'am.
Okay. Good. So we'll start in a couple of minutes. Yeah?
All right.
So right now, your sound quality, everything sounds fine.
Okay.
Who is your PhD advisor, if I may ask?
Yeah, sure. Priyanka Grover. Dr. Priyanka Grover.
I see. We'll start in a minute.
All right.
Okay, let's start the talk. So it's my pleasure to introduce the last speaker for the day, who is Veer Singh Pawar, who is a PhD student at Shiv Nadar University. And the title of his talk is Positivity Properties of Some Special Matrices. Over to you, Veer Singh.
Thank you, ma'am. Good evening to all. Before starting my presentation, I would like to thank the organizers to giving me this opportunity to present my work here. And so I start my presentation by some basic definitions that most of us are very familiar with, and we have also seen these definitions in the previous talk. So again, I'm repeating it. Any Hermitian complex matrix is called positive semi-definite if this inner product is non-negative for every x belongs to Cn, and it's called conditionally positive semi-definite or CPSD if this inner product is non-negative for some spatial vectors x for which this summation is 0, where x is the n tuple x1 to xn. And we have already seen in the previous talk that according to the Schur theorem, the positive semi-definiteness is preserved under the Hadamard product. And so, okay, so the next definition is infinitely divisible matrices. Any entry-wise non-negative Hermitian matrix is called infinitely divisible if for any positive real number R, the matrix AOR, we call it as rth Hadamard power of A, and it's nothing but the matrix whose ijth entry is the rth power of the ijth entry of A. So if for every positive real number, this rth Hadamard power of A is positive semi-definite, then we say that A is infinitely divisible, or in short, we say that A is ID. And again, the infinite divisibility is also preserved under the Hadamard product. Now, any matrix A is called totally positive if all its minors are positive. So next is any function defined as this is called matrix monotone of order n if whenever we take any two n square positive semi-definite matrices A and B such that A is less than or equal to B, that is B minus A is positive semi-definite, then we must have FA is less than or equal to FP. And if such function f is matrix monotone of order n for every value of n, then we say that f is operator monotone function. Now we take a quick look at these three things. First thing is obviously showing that there's a connection between ID, that is infinite divisibility, and CPD, conditionally positive definiteness. Second thing is the characterization of matrix monotone function, which includes this matrix, which is very well known. This is called a Lowiner matrix. Third one is a characterization for a function f to be operator monotone, and here also we can see that this term is available here. So these three things actually shows us that infinitely divisibility is connected with these very well-known and useful concepts in matrix analysis like CPD and operator monotone and matrix monotone. Now, these are some references, some good references where one can find good literature related to infinite divisibility, and also very nice examples on infinitely divisible matrices. Next, there's no doubt that total positivity in itself has always been an important and powerful concept, which often arises in various branches of mathematics like statistics and probability theory and many more. And people have always been interested in working total positivities. Some of the recent publications on total positivities are these. Now we take a quick look on these well-known, very important results for and examples on infinitely divisible and totally positive matrices. For example, let's take a look at these two matrices, which are very well known. This is called Cauchy matrix and this is called Pascal matrix. Both are very good examples of infinitely divisible and totally positive matrices. So are the rest of the examples. And one can find the proof of their infinite divisibility and total positivity in the given corresponding references. Now we start our work. What we did, we constructed a matrix denoted by B, and we call it a beta matrix of order n, whose ijth entry is 1 upon beta I comma j, I and j vary from 1 to n, where this small beta denotes the beta function. For example, beta matrix.
We can't hear you. Are you saying something? Veer Singh, your audio.
I think there is some issue with his.
I think he froze or something.
Yeah. Veer Singh, are you there? I think he froze, or maybe his internet froze. So.
Okay.
If any of you have his mobile number, could you just connect to him and ask him, or what's the problem?
Ma'am, I'll call him.
Yeah, please do. Thanks. Yeah, so in the meantime, I would like to apologize for calling it the last talk of the day. It is the last talk for the session. There is a panel discussion and night talks, 2 night talks happening later as part of the virtual math fest. So did he pick up the phone or whoever called him?
So someone wanted to call Bev. Did you
Yeah,
call?
there was one person in the audience who
Yeah.
was trying. Yeah. So could you succeed in connecting to him? Whoever tried.
Hmm.
Actually, ma'am, his phone is busy. I'm trying calling him.
Yeah,
Okay.
maybe he will not pick up because he's in the middle of a presentation or something like that. But do the organizers have any other
Actually,
contact?
we don't have his phone number. He didn't give us. So we
Mhm.
asked for his phone number. Now he's
Yeah,
Now
he's
he is here.
asking
Yeah,
to
okay.
enter.
Yeah.
Yes. Yeah, he's here.
He's
Yeah. Sorry, Veer Singh, are you there? Can you hear us? Veer Singh, are you there?
Yes, ma'am. Can you hear me?
Yeah, and we can hear you. So in between, I think there was some internet problem from
No,
your side.
not internet problem. Actually, my laptop got hanged. I don't know why.
Okay, okay.
Can
So
I
no
continue?
problem. So I think
Yeah, you can continue.
you still have 5 minutes to
5
finish your
minutes.
presentation.
All right, all right.
So yeah, slightly less than 5 minutes, but it's okay if you take 5 minutes. Yeah. Okay, you can start from where you had left
Yes.
it incomplete.
Can you see the slide?
No, Shomo, can you make him co-host? Oh, just a second.
Yeah.
Tomo, can you please make him co-host?
Maybe I can make him a co-host.
No, I think you can't.
No, I can't. Also.
You can't. Only a host can make someone a co-host.
But I think
Shomo, একে co-host করো বীর সিং কে তাড়াতাড়ি। না 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 আগে কানেকশন কেটে গেছিল।
Okay, yeah. So try to present your slide now, Veer Singh. You are a co-host now. So it is 4:25 now. We'll stop at 4:30. Okay.
Yes. Is it visible now, the screen?
Yes, it's visible.
Okay.
Yeah.
Thank you, ma'am. So I was talking about this beta matrix. So few beta matrices are shown here, and we can easily see that every beta matrix is a principal submatrix of the bigger one. Okay, so we have these results in a paper for a beta matrix, and beta matrix is infinitely divisible and it is totally positive. And we can easily see this by these relations where this is the ijth entry of beta matrix and this is equal to this. This thing is the Cauchy matrix and this thing is a submatrix of Pascal matrix. Now Cauchy and Pascal both are infinitely divisible. So our beta matrix is nothing but Hadamard product of Cauchy matrix and this principal submatrix of Pascal matrix. So beta matrix is infinitely divisible. Again, by this thing, we can see that beta matrix is also totally positive. Now, we consider this Rth Hadamard power of beta matrix, where R is any positive real number, and we showed that this is also totally positive. Then we gave Cholesky decomposition for beta matrix, which must exist because beta matrix is a positive semi-definite. So it must have Cholesky decomposition, and where L is a lower triangular matrix given as this. And from this theorem, we can easily get this corollary where we are giving the determinant for beta matrix and also the inverse of beta matrix. Now we generalize our beta matrix. We first consider this matrix whose ijth entry is gamma of lambda I plus mu j, where lambda i's and mu j are any arbitrary positive real numbers, when gamma is a gamma function, and we show that this is totally positive. And this matrix is a generalization of beta matrix because here we are replacing I and j by lambda I and mu j, and we show that with the help of this theorem that this matrix is also totally positive. Now we consider some factorization. These matrices Li and Uj defined like this are called elementary bidiagonal matrices. For example, L2S is this, U2T is this. And we gave a factorization for a totally positive beta matrix like this. And this is a particular factorization for a totally positive matrix known as SEB, like successive elementary bidiagonal factorization. So we gave SEB for beta matrix. Other than beta matrix, we studied many other combinatorial matrices, and like I'm only discussing Bell matrix here. Bell matrix is actually the matrix whose ijth entry is I plus jth Bell number, where nth Bell number is given by this. And we gave two results for Bell matrix, that it is totally positive and it is infinitely divisible if and only if its order is less than equal to 4. So that was it. And this talk was based on a recently published paper. This is the screenshot of our paper. And I would also like to thank my co-authors, Priyanka Grover and Satyanarayan Reddy, for helping me in working this. These are the references. So this was it. And I again thank you, the organizing committee, for letting me presenting my presentation here. So thanks a lot.
Let's thank Veer Singh for such a short and challenging presentation. I understand it's very difficult to present the work in 10 minutes time, but you did a good job.
For that.
Yeah, you did a very good job. Yeah, so thanks, Veer Singh. So the floor is open for the audience if they have any questions.
Anyone can unmute and ask.
Yeah. No
questions. So Veer, maybe you can talk about some future problems you want to do in this.
Yes, actually we other than these properties of beta matrix, we are also looking forward to find the inertias of beta matrix, and especially the inertias of Rth Hadamard power of beta matrix. So we are working on these inertias problem nowadays.
Okay, thank you.
Yes.
Question, comment, remark, suggestion, feedback. Okay, if not, then let's thank the speaker once again. Thanks, Veer Singh. And I would now maybe hand over to the organizers.
Yeah, so I would like to thank Dr. Anisha for chairing the session, and we
Thank
close
you
this
for
session here. This
my
analysis
pleasure.
PD, and we come back at 5. Okay. See you.
Okay, thank you. See you all. Bye.
Now, the purpose of the panel discussion is to inform masters and doctoral students and undergraduate students about job opportunities in academia and industry. We have a very distinguished lineup of panelists. They will make short presentations as per the area of their expertise. And the organizers have chosen them in such a way that we have very little intersection in their expertise, although there are people with multiple expertise here. And you will see that from their presentations. So mathematicians, as we all know, nowadays they are preferred by many types of industries because mathematicians have analytic skills, they can think rationally, they can extract the essence from any kind of data they are presented with. So they have a unique background in comparison with the people with other subjects. So they are trained in mathematics. The mathematics that they learn may not be completely useful in what they do, but that training is extremely important, and some part of that training certainly goes into their job profile, and everyone has to keep learning various skills throughout their life. The panelist will first speak about the skills that the students must acquire during their presentations. We have received a large number of questions from the audience, and we will answer those questions first, and then we will take questions from people who are present here and didn't get the opportunity to ask questions. So that is the structure of this program. For about half the program, we will have presentations by the panelists, and I'm sure you will enjoy listening to them. They have very long experience in various areas of expertise. So we are looking forward to listening to them. The first panelist is Professor Rajiva Karandikar. He is a mathematician, statistician, and a cephalologist, if you know what that means. You must have watched and look, the election results, and he is perhaps the most popular statistician in India because the elections keep happening every year, and we see him in some role somewhere, and his analysis have predicted many poll results correctly. He graduated with a PhD from ISI, and then he taught at North Carolina University. After coming back to India, he joined ISI in 1984. He served ISI in many roles for a long time until he decided to take a switch to industry. So this is something that our audience should notice, that a hardcore statistician and mathematician can switch, because he has the required skills required in the industry. So he switched to Crane Software. He was executive vice president, and he helped in many execution of many programs which relate with statistics and data. He is a fellow of Indian Academy of Sciences and Indian National Science Academy. His research interests are in probability, option pricing theory, cryptography, and psephology. So these are all current applications of mathematics and statistics. So it is a pleasure to have Professor Karandikar to speak to all the people in the audience. So I invite Professor Karandikar to speak to our audience here.
Yeah.
Can you share your screen? I don't see you in the panel right now.
Just a minute.
You have to go up and down, then you see. Once it shares the screen, it will be there.
Right.
Zoom. Can you see my screen?
Well, it will take a few seconds for us to see the
we
screen.
can't see it. No, we can't see it.
There is an option to say share screen, right? So you.
Yeah, at the bottom there is an option to share the screen.
Earlier I have shared with Zoom. Today it is not allowing. I don't know.
Oh, you are not being allowed to share the screen?
No.
There is a file in the Dropbox. Should I share it?
Yeah, I think you share it. I think we should not lose time. You can share it. The same file, yeah.
Okay. Oh, it says only one participant can share at a time.
Yes,
so you have to stop sharing maybe then.
But I have not shared then. Then who has shared? Because my thing is not yet successful.
Okay, so yeah, but I have to get it out of Dropbox, then only I can.
Riddhimam, can you share it? I mean, is it possible for you to share? Or?
Yeah, I will share it, but I have to first find it. So it's on the
Dropbox.
Okay,
yeah.
While you share, let me start speaking so that we don't.
Yeah. Okay.
Yes.
Yeah, please do. Okay, you share, but I'll start speaking. So I am going to talk about career options with maths, and while I will focus on talking about industry, I should put on record that the traditional career has been, of course, the academic career, MSc, PhD, followed by teaching and research. And academic career is now a good option. The remunerations for academic positions have gone up significantly in comparison to other jobs, say from the time when I chose academics and today. If I compare with a salary with a bank officer and so on, the academics has actually moved up in the ladder. Also, if one adds to this the lifestyle that comes with it, academics is an attractive option. So what I say later should not be seen that I am dissuading people from academics. Okay. Also, today one can consult with industry in addition to teaching and research, making it even more remunerative and attractive. But of course, academics is not everybody's cup of tea, and therefore, there would be people who can choose academics. There will be people who will need to do something else. And what is that something else? That is what I am going to talk about, at least partly. 20, 30 years ago, there was nothing else. Yeah, okay.
I started the file, Rajiva.
Yeah.
Okay.
Yeah, so I will
slide 4 or 5, something like that.
Yeah. Just a minute. Let me go to full screen.
Yeah, I am also stuck. So, you are starting the file. Okay.
Yeah, I'm starting the file.
Yeah.
Okay. Can you see the file?
Yeah. The file, yes.
Okay. So, just a minute.
Go to
Control L should take it to full screen.
No, I'm working with Ubuntu and I don't have the correct software, I think.
Okay.
Yeah, so I will slide as
I think just slide, yeah. Go up further. Yeah, go up further. One more. Yeah, that's it. Now, next. Yeah, next. Yeah, sure. So, sorry, the previous one.
Yeah, you were here.
Yeah. So I'm going to talk mainly about jobs in data science and cryptography and what do math students should do to prepare themselves for these jobs. One point I would like to stress is that the student should take the courses undertaken during BSc, MSc as training how to learn mathematical ideas and not an end in learning. As Professor Jugal Verma said in the beginning, the learning doesn't end with your courses. You have to be willing to learn. And that is one point that you need to understand, that it should not take the BSc, MSc, I studied this, so now where is my job? You will continue to, next slide please. So certainly anyone who may not have studied, let's say, simplex algorithm to solve linear programming, but has an MSc in mathematics, so whatever specialization, but MSc maths but has somehow have not been exposed to simplex algorithm. They can quickly learn that by reading a book much faster than others can. Okay, so this is how one has to understand our training. Okay, this you should keep in mind. All right. Now let me come to one of the two topics, cryptography. So students who wish to keep this path as a possibility, okay, should learn number theory, elliptic curves, generally discrete mathematics, along with programming language such as C++ and Python. Okay. Now, various institutes offer these courses as part of BSc MSc, not all, but a few. And if you want to keep a door open to cryptography, you should grab and do as many as you can. In ISI, they have launched a MSc crypto program. This is after a MSc Maths and a BE Tech. And you should, that will definitely lead you to a good option in cryptography. Okay. Of course, in today's world, if you do MSc Math and on the side take up online courses, various places are offering online courses, some free, some paid, some with a certification, some without a certification. But you take online courses, read about these topics, master these topics such as block cipher, stream cipher, hash functions, public key cryptography, popular algorithms in use, blockchain, and you write down or create a document saying the books you studied, the courses you took, etc. And whether or not you have a certification, if you have a call for an interview, you can list these and you will be examined. Today, the world has changed. They don't simply go by what you can show as your degree. It is more, especially in industry, it is more by what you have learned and understood. Okay. So keep this in mind, that if you get opportunity to take these courses as I outlined, you do that. If not, just do online. Now, data science, these are analytics, data science are buzzwords. There is a huge demand for professionals who are familiar with data science and leverage the same. And the reason is very clear. Once the internet became all omnipresent and mobile network had spread wide and all, we start generating a lot of data, and this data, using powerful tools, we can utilize to make intelligent decisions in any business scenario. Now, for a century, techniques of drawing these meaningful conclusions had been developed by statisticians. Similar development came from the community of computer scientists, techniques which were called artificial intelligence and machine learning, AI/ML. The two approaches have many ideas in common, and yet both have some techniques and ideas not present in the other. And in my view, together, these two form the backbone of what is data science. People mean different things when they say data science, but my take, drawing meaningful, actionable conclusions from data to achieve objectives from using techniques from statistics, artificial intelligence, machine learning, implemented via efficient algorithms. Okay. So this is what I mean is data science, but there could be a slightly different view, but roughly this is what is data science. And okay, desirable skills for a career in data science. So analytical capability along with basic or some exposure to linear algebra and calculus, ideas from probability theory and statistics, good skills with one of the computer languages, basic understanding of ideas in AI/ML, databases, data structures, SQL, efficient algorithms, familiarity and comfort with use of Python and/or R, and mastery over at least one. You should not just be jack of all. One of these you should master. Just note that I said good skill set with one of computer languages rather than software skill, because later is sometimes taken as just using ready-made packages and drop-down menus, etc. Using all that is fine. You can accelerate your development, but if things don't work, you should get into backwards and go to the basics. So that's why I have said software skills. I would add to these core skills listed above good communication skills, without which ideas generated will fail to have an impact. And somehow it's not clear whether people with poorer communication skill are good at maths and take up maths, or we do something when you do math courses and we kill your communication skills. I have not been able to figure out. But generally, these are poor with kids who have, or students who are good with maths. But you have to work on it. You can get over that. And familiarity with basics of economics. It is all important because most tasks involve some concepts of economics and finance, maximizing profit, minimizing expenditure, and so on and so forth. So some familiarity with economics helps. Courses that students can choose for analytics or data science as career. Top one would remain MStat or MSQE at ISI, Master of Science in Quantitative Economics. MStat, MSc Statistics, Applied Statistics at IIT Kanpur, IIT Mumbai. These two I am familiar. Others may be offering, but these two I certainly am familiar and are good. At CMI, we have a specific program which we have launched recently, MSc Data Science. In general, MSc Statistics at some university and institute, and whatever lacuna may be there in the courses to make up by online learning. Likewise, MSc Computer Science with appropriate optionals. Okay. Again, as I mentioned earlier, degree may not be that important. If you don't know some of these things or you cannot join any of these programs, you can still aim for a data scientist and master some of the skills. So the important thing is that, okay, please, next one, yeah. So search on internet with terms such as, I've just listed some which occurred to me: probability distribution, estimation, testing of hypothesis, regression, classification, and go on, so on. If you do not understand some of the terms appearing on the page, go to them and understand them, go back and forth. And that is how you can create awareness amongst yourself about what is analytics, what is data science, and master that. Unless you are 100% sure about academic career, I would suggest keep other option open. Should not say that, oh, I earlier was only focusing on academics and then now I am not getting a good job. Now what do I do? Unless you are 100% sure, keep other options open, develop other skills, software skills, communication skills, keep your eyes and ears open, and parallelly prepare for a industry job. Good luck.
Okay, so thank you very much. We will come back to the answers to questions which were posed to you later.
Yeah.
We go to the next panelist. So our next panelist, let me, is Professor Gautam Menon. Professor Gautam Menon is professor at Ashoka University and Met Science. Let me tell you a little bit about his background. His background is very, very diverse. He graduated from IISc Bangalore in physics, and then he joined Tata Institute, and later he also taught at Simon Fraser University. He joined Met Science in '98, where, as I said, he is a professor. He is also an adjunct professor at TIFR, and is a fellow of National Academy of Sciences, recipient of Swan Jayanti Fellowship, and he is interested in all areas of science. And you can look at his research output. It is extremely diverse, and now he is thinking about mathematical models of COVID-19. We are all very eager to listen to him. So, Professor Menon, you may present your slides now.
Thank you.
Yeah.
Can you see my slides?
Yes, yes, please. Yeah.
Okay, so I want to tell you about opportunities for mathematics students in both in industry and academia, but that have more of a scientific tinge. So areas in science outside of mathematics for which mathematics students might be well prepared for. So first of all, the question is, where are the jobs of the future for those of you who are mathematically inclined? And if you're doing anywhere near a degree in mathematics, it can be assumed that you're mathematically inclined. So these jobs, as far as they relate to the sciences, into areas outside of pure mathematics and applied mathematics, are in the sciences and the social sciences. And they can be industrial jobs, they can be academic jobs, and they can be part of the non-governmental sector. And of course, there are jobs for which mathematicians are well suited that are in government, in a multitude of government organizations that deal with data, for example. And defense is another area where people who are mathematically trained can find work to do. So let me give you some examples that I want to illustrate. The first, of course, is bioinformatics, which is a term that you may have heard of. And at its simplest level, it's a computational discussion or analysis of long sequences. These can be sequences that make up DNA, or they can be sequences that make up proteins. But essentially, it's a mathematical question of where is the information that is contained in sequences of some form. The second option, of course, is mathematical modeling of some sort. For example, something you may not have thought of is a mathematics that goes on to deciding fisheries, who fishes where, what are the constraints that you must apply, when do you prevent people from fishing, from going out or staying back, just because you want to keep your catch manageable. Computational biology is a third area, very, very broad and vast area, where again, the algorithms and the techniques used are much more natural to someone who has a mathematics training. Medical research is something that, again, many of you may not have considered, but the question of how do you get a drug to market? How do you determine the efficacy of a drug? How do you understand how your body reacts to a drug, to any external influence, to any environmental influence, and how does your body function? Is somewhere in between medical research, biology, biophysics, as well as mathematical modeling. So I think of all of these as really being related to mathematical modeling in its examples. My fifth example is one that is particularly current now, and that is of epidemiology. You may have seen notices in the newspapers about how the government is desperately searching for epidemiologists. It can't find them. And epidemiologists are people who do many things, but among them, they do mathematical models of how diseases propagate inside a population. They analyze the distributions of diseases. They may peak now, come down. So you might want to ask, when do you expect dengue to come to Chennai or to Bombay or to Calcutta? Over which months? How does that depend upon the rainfall in the month before? So you can think of mathematical models, you can think of statistical models, but finally the ability to work with equations and concepts that are more mathematical in nature is very crucial to how you think about it. Pharma research, again, very well-paying area, and that's where a lot of mathematical modeling is called for. How do you determine the dosage of a particular medicine? So right now, there are lots of questions around what might be good antiviral medicines for COVID-19. How do you determine whether they work or they don't work? Again, an area that overlaps both statistics, mathematics of various kinds, applied mathematics, as well as a general quantitative understanding. The study of weather or weather patterns is something that is very, very computer intensive. It requires very clever algorithms that require Navier-Stokes equations. So take stiff PDEs, systems of stiff PDEs, and methods of understanding, conceptualizing them, and solving them is what you will be doing if you work in a mathematical area with the meteorology department. There are other areas that you might not have thought of. Again, this is an area for design, industrial design, for example, is an area where a familiarity with curves, geometry, etc. All of these come in. Of course, there's lots of software that helps you do these things. But in general, the more mathematical you are, the more intuitive you are about mathematical concepts, the easier it is to be able to contribute significantly to that area. Aerodynamics and fluid flow. Again, fluids is something that any good applied maths course studies in its master's degree. These are very canonical and important equations, the Navier-Stokes equation. And these are fundamental to understanding how planes fly, how fish swim, etc. So all of these, anything that involves fluids, the computational simulation of fluids, is something that applied mathematicians are especially qualified to discuss. Something else is science and mathematics communication in general. And this is an area that, in fact, nowadays, many students, even after a PhD in physics or biology or chemistry, are moving into, because they find that it appeals to a part of them they have never really thought of earlier, which is the interest in communicating fresh developments, new developments in a particular area that might be complex. For example, the Riemann hypothesis. How do you explain it to a layman? How do you explain mathematical concepts in general, the prime number theorem, to a layperson? Communicating mathematics is again very important, and there are jobs in there, science journalists, which again use this information. It's particularly hard to find good people who explain maths well. It's possible to find people to explain biology or physics, etc. But math seems particularly difficult to have good people who can explain it to the public. Finally, social surveys, data analysis, presentations, etc. all belong to the social sector, the NGO sector. For example, you might want to find out what is the uptake of a particular type of medicine or contraceptive, etc. in a village area. How would you set up a survey? How would you analyze it? All of these need both statistical as well as mathematical understanding. And finally, of course, all of us enjoy teaching and training. You can anywhere between school and above. So the importance of a mathematics teacher and the fact that there are not that many good mathematics teachers around. These are jobs that you should not neglect. They're very important. They will likely be even more important as we move on in the future. Here are some examples that I chose. How do you design a plan for a clinical trial? That's a question that a mathematician might be able to comprehend and understand. How do you predict climate change and ecological change? How do you use models to do that? If a pharma company wants to search a database of proteins to match one that they may have synthesized, how do they do that? How do diseases spread in the case of bioterrorism? This is something that any defense agency would be interested in. How would you contain it? How do you model the spread of forest fires in the Himalayas? Say, what is the mathematics that goes into describing a forest fire and how it moves? What is the boundary of the forest fire as a function of time? There are differential equations or PDEs that go into such a description. How would you write them down? How do you use genome analysis to understand how you can tailor a particular treatment to one person and not so much for another? What works for one person and might not work for another? And finally, as I said, public outreach and discussion. How do you explain a new mathematical result to the public? Okay, so let me just concentrate on what you should have. And again, this is something that will come up in the discussions of the other speakers. And already Mr. Karandikar mentioned many of these. First of all, an overall competence and interest. If you're not good at mathematics, but you want to do something related to mathematics, you shouldn't look for jobs that are like that. And I will assume that you're already interested, you're already competent enough, but it's important to stay within that zone of competence and improve that competence wherever you can and have interest in what you do. Computer skills, again, very important, very generically, Python, R, C++, etc. These things change very fast, exactly as Professor Karandikar pointed out. So an overall flexibility and ability to learn new things, new computer skills is also important. Technical skills, again, coming from your mathematics training, statistics, applied maths of various sorts. But now let me focus on things that, again, Professor Karandikar said, are things that usually mathematics students don't think they need to have. And that is clarity and confidence in presentation. Very important if you want to look for jobs outside purely academic jobs. Whenever you go to a job in industry, whenever you interview, they will look for things like the confidence of what you say, your clarity of explanation, your ability to write, also very important. It's as important in writing a paper as it is in other types of work where you have to present material to another person. So look for brevity, look for clarity, and look for expressiveness, how cleanly and clearly you describe an idea or a concept. In moving from mathematics into any of the areas that I described, it's important to retain the idea that you should be able to reskill yourself, learn new things very fast. So that requires flexibility, the ability to adapt, the ability to learn on a job. Even if you convince an employer that you can go there and learn something, you should actually be able to do that in person, even though you may not have heard these technical terms before. The ability to work in groups is crucial to anything that you do in industry, anything that you do apart from just simple one-on-one mathematics research. All of life involves working with others in groups, working collaboratively. And it's important to understand and to maintain that ability. Enthusiasm is something that you can't fake. It's easy to understand when someone is enthusiastic about something, who wants to sell you an idea. So the ability to describe what your interests are, what you do in a short, it's called an elevator pitch, which is 2 minutes or 30 seconds or 45 seconds that summarizes your interests, what you are, what you can do, what your abilities are, and why someone should hire you. That again is very important. Whenever you're looking for jobs in any of these areas, or even more generally, it's important to understand what that job involves and to understand and to be able to express why you might be specifically skilled in order to deal with that job. So let me finish up here, and of course we'll come back and we can answer some of these in the question and answer session. Thank you.
Okay, thank you very much, Professor Menon. We now go to our next panelist. She is Professor Riddhi Shah. She graduated from TIFR. She has been in academics throughout her life. She finished her PhD in mathematics in 1991. She was a faculty member at TIFR for quite some time until she joined Jawaharlal Nehru University in 2007. She is a recipient of Indian National Science Academy Young Scientist Award and a Japan Society for Promotion of Science Fellowship, Alexander von Humboldt Fellowship. Her research interests are in dynamics of group actions, probability on groups, and their structure. I requested Professor Shah to focus on jobs in academia for students of all levels. So, Professor Shah, you may now present your thoughts on this topic. Yes. You have to unmute yourself. Yeah, we can't hear you.
Unmute. Okay.
Yeah,
now, can you hear me?
Yes.
Okay.
It's very clear now. You may start. Yeah.
So, my main focus is on academic career, and I'm going to talk about what you do to gear towards academic career. So if you do an MA, MSc in mathematics or statistics from a good university or institute, and if you want to teach in a college, you can go for higher level master's degree, which is an MPhil program offered by many universities like DU and some other places. And many students do, many people take up a job in a college and then do PhD on the side. Now from 2022, if you want a job in a university, then PhD would be compulsory. So PhD, there are two ways to do it. One is a regular route, where you have PhD offered by many universities like JNU, Delhi University, Hyderabad University, this is Punjab University, Chandigarh, MS University, Ramakrishna Mission, Swami Vivekananda University, and there are some other universities. This is just some examples that I'm giving you. Then there are institutes like TFR, IMSC, HRI, ISI, IITs, ICERS, NICER, CMI, etc. You could also do a variant of integrated PhD program and MSc program, which is called integrated PhD program after a BSc. So you get a dual degree with that. Of course, your BSc could also have been a dual degree with undergraduate and masters together. One thing you should remember is wherever one studies, one should choose a good place, whether it's in India or abroad. There are many good universities abroad for pursuing higher studies, which also provide teaching assistantships, but the admission and funding may be reduced for the next year due to the crisis this year. So a lot of students are deferring programs, so they would be accommodated first next year and then they will take new admissions. Though I see a lot of advertisements on Google for PhD fundings all over abroad, Europe and US. You may look up. I will tell you where to look up. So financial assistance to pursue higher studies in mathematics. So NBHM has a master's scholarship for MSc students and PhD scholarship and postdoctoral fellowship. For PhD scholarships, they take national level exam and interviews, and then they choose students to give them fellowship. There are also research fellowships from CSR in UGC, which are called junior research fellowships. So you have to give an exam, which is twice a year, and then qualified students get junior research fellowship, which is quite good. And there is a lower cutoff for JRF, net JRF, which is called net qualification. So if you want to teach, you can just get that certificate and get a job depending on how you perform in interviews. Then all these institutes I mentioned have their own scholarship to do PhD. So they have their own entrance exam and interviews, and they select some students from that, top students from that, and give these scholarships. Central universities have their entrance exams and interviews, and then they have what is called non-net fellowship, which is quite small but enough to survive. Then there is DST Inspires Fellowship, then GATE Teaching Assistantships for IITs. And then if you want to do postdocs, then as I mentioned, NBHM you can apply to. Then institutes have postdoctoral fellowships, and there is also National Postdoctoral Fellowship from DST, which is called NPDF. And there are project research assistantships, which are for PhD students as well as for postdocs, which are called JRF, SRF, RA, research assistantship, which are based on faculty's individual project in which they have fellowship to support students. So let me give you some idea about what to do after higher studies in mathematics. So there are many possibilities for a career after a higher degree in mathematics, as you saw, because it teaches us logic and to think analytically, which is very useful for any career. Masters and doctoral students of mathematics, besides learning advanced mathematics, develop important skills such as patience, discipline, and problem solving in a step-by-step method. A career in research and teaching is a well-trodden path that is very rewarding if you love mathematics. So you have to first decide whether you would enjoy this and whether you love mathematics before you take up a career, academic career. So these are some of the advices, recommendations for preparing for a career in teaching and research. So for an MSc degree, choose different electives to learn many subjects while learning basic subjects in mathematics, such as algebra analysis, topology, number theory, probability and statistics, ODE, ordinary differential equations, PDE, and computational mathematics. And then you can choose some other electives if offered, like cryptography, finite element method, fluid dynamics, and advanced number theory, dynamical systems and ergodic theory, etc. This is so that you get an overall background, and you should learn hard and all these basic subjects, which will take you a long way in your academic career. Go for summer internship during MSc. All these institutes I mentioned, TFR, HRI, IISc, they all offer summer internship. It's called Visiting Students Research Program. There is also an academy, Science Academy fellowship for students to go and do summer internship at various places. Join a good place with an open mind, do 1-year coursework in advanced subjects, and then decide on a topic and advise for a PhD. Develop good written and oral communication skills. Attend many departmental seminars, and also those at nearby places. Currently, you can attend virtual seminars on many topics on the website researchseminars.org. It lists many seminars in different subjects of mathematics. So you should also attend workshops and conferences. Workshops are for learning advanced topics, and conferences keep you informed about new research. These are some of the organizations which have regular conferences and workshops every year. One is National Center for Mathematics, which is jointly run by TFR and IIT Bombay. It conducts foundational and advanced instructional schools and specialized workshops. This is the address. You can go and have a look. Annual foundation schools are very good for beginning PhD students. Indian Women and Mathematics conducts activities for MSc and PhD students to promote mathematics teaching and research among women. But activities are open to all the mathematics students regardless of gender. And this is the website. ICTS TFR conducts workshops and conferences for advanced PhD students, postdocs, and faculty. And this is the address. Many institutes and universities have workshops and conferences funded by NBHM, UGC, CSR, DST, Government of India. Run a regular student seminar journal club at your university institute. This is my advice, because unless you learn some topic and talk about it, you will not be, what I'm going to say is that you become more of an expert when you teach somebody else, because they ask you questions and sometimes you haven't thought of them and you learn more. Teaching always makes you more and more of an expert in a subject. So how do you get to know these? You can go to those websites and find out. These are further recommendations. But one more thing I would like to say is that you make it you know, have a PhD in a good area, so have a broader perspective to do PhD. Don't work in a very narrow area. Also learn things from other areas, from other students, from other faculty, and have an overall education. PhD is not just about writing papers, and it is an overall learning experience. So these are some of the things you might want to read while you're doing MSc or PhD. These are inspirational essays called Lilavati's Daughters. Those are on academy website, freely available. Those are women scientists and mathematicians essay. Another one is 100 Reasons to be a Scientist. This is on ICTP website. Man of Mathematics, of course, is not freely available, but that's also very inspiration. One thing I like to read is mathematics articles in Quantas magazine. These are freely available. They often have biographies, but not only that, they often have articles, popular mathematics articles explaining current research. Suppose somebody proves a conjecture, they explain it in very simple terms, those articles, and it is really good to read them, because we cannot be expert in every discipline of every area of mathematics, but you can learn a lot about current research from these popular articles, current advances in mathematics. After a PhD, a postdoctoral experience is recommended, and you can give seminars at conferences, visit other universities and institutes, and give seminars to let people know about your work. You can also be informed regularly from online resources like MathSciNet, Zentrablatt, Math Archive, and ResearchGate. The last two are free. The others, the university or institute have to have access to these things. So now, where to look for academic jobs, PhD and postdoc positions and grants? So websites of institutes, universities give you information at appropriate time. Newspaper advertisements, Google, and informal. This is called Maths India Google group, run by Dr. Ramesh Kaslingam of IIT Madras. And if you want to be a part, you can do Google search, and if you want to be a part of it, you write to this email address, nomathematics@gmail.com. So there you get to know about all conferences, workshops, PhD positions, project positions, not just in India, also abroad. And so many faculty all over world send him these information, and then he puts them up. So it is very informative place if you want to look for anything like that, but all about academics, not industry. Then there is AMS job listing. Then there is mathjobs.org. Then this is phd.org. Then Association for Women in Mathematics, AWM, and European Women in Mathematics. These two also list PhD positions, postdoc positions, and jobs all over. Thank you very much. And if you want to see overall presentations of consolidated presentation in many things, many job opportunities and so on, you can see this V. Sunita's representation and Dheeraj Kulkarni and Rohit Holkar's presentations on these sites. Sorry. Thank you very much.
Thank you, Professor Shah, for a very informative presentation for people who want to remain in academics. Our next panelist is R. Venkatesh. He is a chief scientist at Tata Consultancy Service. He is a BTech from IIT Bombay and MSc in computer science from Pune University. He is the head of verification and validation program at TCS. He has spent more than 3 decades as TCS, working in the area of software development, formal methods, and verification. He publishes widely in several areas of computer science, and the tools for these areas that he and his team have developed have many, many awards. So he is enjoying both the worlds, doing research and also working in industry. So he has a unique perspective on all the topics that we are discussing. So I invite R. Venkatesh to make his presentation.
Yeah, thank you, Professor Jugal, and thanks. Welcome everybody to this panel discussion. So I'm going to give some very high-level thoughts, more from based on my experience in the industry than on any academic. So when you are doing a course, be it BTech, MTech, PhD, or whatever it is, don't look at it as some just a course that is imparting you with some maths knowledge. It of course is imparting you with a lot of math knowledge, whatever it is. It could be statistics, it could be functional analysis, it could be calculus, and it is also imparting you with skills on applying those maths knowledge. But it is imparting much more than that. It is imparting you with some critical thinking skills. It is imparting you with some problem solving skills. Essentially, it is teaching you how you can take any problem, model it mathematically, how to come up with a mathematical model for that problem and to reason about it and come to some conclusions. And these conclusions could be how COVID is going to spread. It could be which party is going to win. It could be whatever. So it is essentially giving you these skills, the ability to think very, very critically and very, very logically and systematically. And that is how you should look at when you're looking for a job in applying your mathematical skills. Don't look at a job that just enables you to apply the knowledge that you've gained as part of your maths course, because you're not going to find a job that is a direct application of the knowledge. Whatever you do, you're going to have to go beyond the knowledge that you've been given, but you have to be able to apply more skills than the knowledge. And I'm sure Professor Rajiva will agree that just mere statistics knowledge is not good enough to predict election results. You need to go way beyond that. And so that's what is important when you're getting onto a job and being successful in a career. And I would say you need to focus on that. Opportunities, of course, everybody has said, and here I'm just saying the opportunities are really plenty. There is no dearth of opportunities. You could finance, insurance, banking, accounting. You pick an area, there is an application. There is no job opportunity for a mathematician. And in fact, if you look at future skills, the skills that are really critical are critical thinking, problem solving, and analytical thinking. So long as you have those skills, you have plenty of job opportunities. And these opportunities I've listed as these will also have, in addition, opportunity to apply your math knowledge, the math skills that you have learned in school or college or whatever institute, whatever degree you have got. It will give you an opportunity to apply this knowledge. But even without the knowledge, you will have a lot of job opportunities. So don't even be concerned about whether there are enough opportunities or not. For a good person, for a person who can apply these skills, there are plenty of job opportunities and they will all be successful in careers. That is the first point I want to make. The second point I want to make is the attitudes that you need to. So recently, computer science, ACMA, that is a computer professional body of computer science, are coming up with something called CC 2020. What they are introducing in a curriculum design is a concept that they call as disposition, which is unfortunately not taught in any institute very explicitly. All institutes expect you to learn those skills implicitly without any, and these are skills that are very important when you get out from your degree to a job. Problem solving, of course. What I mean by problem solving is you're given a problem, which is very different from a task. A task is you're told that you have this math knowledge, apply that. Here is a place where you can directly apply that knowledge and solve a problem. Please do it. That's a task. A problem solving is being told that please predict how COVID is going to spread in Tamil Nadu or how COVID is going to spread. And it will require you to figure out where to get the data from, what are the mathematical models, how to model various interventions like lockdown, travel restrictions, whatever interventions come, how to model those. You're not going to learn that directly in any institute of yours. You will have to figure all that out. So when we say problem solving, it is about taking that ownership of finding everything that is needed to solve that particular problem. And it will go way beyond the math knowledge that you have. And that problem solving will need you to connect with the right people, maybe connect with government officials, connect with faculty somewhere, connect with industrialists somewhere, whatever it is. It needs a lot of skills beyond your math knowledge. And so that's a very important disposition that you need to have. Task ownership comes with problem solving. When you're assigned a task, take ownership of that task. We have found very often people come and say, assign them a task, go to them after some time, and they say, but, internet was down and therefore I couldn't find this information. Or I need this for particular data for solving this problem and that was not available to me. When you say task ownership, you address all these issues yourself. If need escalated, go to your superiors, ask them, this is where I'm stuck, how do I get it? These are options, whatever it is. It's an ownership that you need to have. The third thing is skills. Skills is, you develop skills when you practice applying your knowledge several times. It's like take a footballer or a cricketer or whatever. The way they develop their footballing skills or cricketing skills is by practicing for hours. You may wonder what's there in a cricket batting stroke, but Tendulkar practices the same stroke for hours to develop that as a skill. And so when you want to do similarly for math, you need to take your math knowledge and apply that skill in solving several problems. That's how you develop a skill. So it needs hours of practice, hours of hard work. And that's what you would need. And that's what will make you a successful professional. Beyond math knowledge is absolutely required. The training you get is absolutely required, but you need to go way beyond that. And at some point, I hope academics figure out how to impart these skills. And it's very hard to really impart these attributes in life. And Professor Gautam Sen said, Professor Riddhi also said, I think, enjoy your work. That is absolute critical. If you don't do that, you won't be able to spend hours practicing, developing a skill. You won't be able to spend the hours needed to look for data wherever you want. So if you don't enjoy it, you're in the wrong field. Just get out. And so that's how do you get these? What are really down to earth, implementable advices that I can give? Pick up internships. As many internships as you can. It really puts you on the field to solve specific problems. You will get a exposure to what it is to be in a real life situation, solving and applying your knowledge. Preferably pick internships in areas that you like, internships in companies that will let you do a lot of. Don't look at internship as a tick mark for your degree. Look at internships as an offer. Even if your institute doesn't require you to do an internship, do an internship wherever you can. And it will also teach you to network with people, connect with everyone. People interaction, absolute must. In today's world, which requires very high quality communication skills that several of our speakers before spoke about. You should be able to develop relationships with people. You should be able to, call someone up, say, I need access to this particular data, and you may have some, can you just give it? You should be able to develop that kind of relationships with people. And that's very, very critical. So attend conferences, develop relationships with people, attend, even in a webinar like this, ask questions, interact with people, interact with peers who are attending this lecture. What do you think of this guy's talk? I feel this is absolute rubbish. Whatever. Express yourself clearly, interact with people, develop relationships. That's going to be more and more critical as in the future. Solve completely unrelated problems. Whatever degree you're doing, pick a problem that you think interests you, try to solve it. Today's era, of course, solve the COVID prediction problem in whatever way you can, with whatever data you have access to. But there are many such problems you can put your finger on. Pick it up, try to solve it. That will expose you to the kind of skills that are required to solve a problem. Solve as many problems as you can while you're obtaining your degree. And there'll be many people who have put up problems, be it whether you want to go in academia or industry. Solving a lot of problems will really help. Learn technology. very critical in the future. A lot of people have said, I didn't want to put programming because people will think I'm biased coming from the IT industry. But so I just abstracted it out to technology. But learn whatever technology, learn programming, learn technology. You cannot be, today, a lot more can be achieved through technology than by using pen and paper. You need to be, even proving theorems. If you know how to exploit technology, you can prove more complex theorems that need long winding arguments than you can if you're going to do just using pen and paper. So learn, master it, develop an aptitude towards technology and use it as much as you can. Yeah. So that's all I have to say. Thank you for your attention.
Thank you very much, Venkatesh, for your very valuable advice to our audience who may want to go for industry. I remember when I was a student, I had option of going for engineering or computer science or humanities, because I studied in a place, BITS Pilani, which offered a lot of flexibility. That is not the case in many places. So whichever place you are there, try to, as per the advice of many panelists, if you are not sure what you want to do in future, try to get diverse knowledge in many areas, so that when it comes to making an actual decision, you are not short of skills. It is the time when you are student to learn all these skills. I can tell you a trade secret that whenever Google hires a person, it conducts 10 interviews. And the first interview is to test the programming language skills. They say that every Google employee has to be a master in programming. He may not do programming later, but they have to be programmers, because they know that if a person can do good programming, his analytical skills are in place. Same thing can be done about statistics or mathematics. And so these areas, they require very clear understanding, very clear communication, and you may not use them right now, but later on they become extremely useful. I started out as an abstract algebraist, and those words abstract, in those days abstract was used, but nowadays it is very concrete. And I guide my students to write programs to solve many abstract problems, the so-called abstract problems. As you can see that from the panelists, the common advice is to acquire as many skills when you are young, and you never know when these skills will become useful later in your life. You have examples among the panelists themselves that their training was in something else, but their interest changed and certain circumstances required them to learn new skills, but they have been learning. We all have been learning. And so whether you go for industry or whether you are in academia, we have to be students all our life. We have to keep on increasing our skills so that we are fit for any kind of job. So we have actually received many questions from audience who registered for this panel discussion. And we have distributed these questions among the panelists. So now I will invite the panelists one by one to answer the questions which were posed to them. So I start with Professor Karandikar first.
Thank you.
Yeah, Professor Karandikar, are you? Can you unmute yourself?
Sorry, yeah.
Yeah.
Can you hear me now? Yeah. Okay.
Yes.
So
yes.
Let me just start with the one question which many of the students have asked, and actually which is covered in our presentation, but I will stress. So students have asked what industrial jobs after MSc in pure math, especially topology, functional analysis. Others have asked the same question, algebra, differential equation, numerical analysis. I would like to say this is a wrong question to ask. This is like asking, I have a key, which locks can it open? Okay? So there is no lock which will exactly open with your key. You will take forever to find it. You have to look at your education as we have taught you how to make a key. Now you are given a lock, make a key. I mean, this most of our presentations, we have stressed this point. It cannot be stressed again and again, but it is very important. The coursework is not an end in itself. It is enabler. We have trained you how to think mathematically, analytically. In real world, nobody says that it's not an exam, that in next 1 hour you have to solve this problem. You cannot look at the book. You cannot call anybody. You cannot use internet. No. You can do all of that and you can take suitable time and come up with a solution. So if you don't know something, you can find out about it and learn. So don't look for, just where can I apply this? You look at mathematical knowledge in general and then try to access a problem. Everybody's presentation at this point, but still lots of questions on that. I will take one more question and then related, then we can go around the table. I can come back with more questions. So one, between applied maths and pure maths, which has more opportunities in job. Again, whatever math you do, you are unlikely to be able to find a job where exactly that one will fit. In fact, for no other profession also it works. Everybody has to learn on the job. So you try to get whatever education is possible, make your choices, learn in parallel, and then look for jobs. So by taking pure maths, you should not take a view that, I have nothing else to do with the world. Remember, nobody is going to pose a problem to you as a mathematics problem. They are going to pose a language in their own domain phrases. You have to formulate it as a problem, appropriate techniques, and solve it. I will just end this part of my answer by saying that my research work is more or less completely orthogonal to whatever applied work I have done. I have done applied work in areas where I have done no research, and the areas in which I have done research, I have done no applied work. So let others take up other questions. I will come back to more questions.
Okay, so Professor Menon, would you like to take some questions from the list that you saw?
Yeah, I can take one question which says, during recruitment in high-level scientific centers like ISRO, DRDO, etc., the hiring of maths people is very, very lower. Many times there is no hiring than engineers, chemistry, physics, master's degree holders. Why? How does one shine in these kinds of areas for math people? Again, I think it's a question of how you present yourself and how your orientation is. And as I said, usually mathematics students present themselves as being very limited in what they do. They know mathematics well, but you have to sort of show anyone who's interviewing you that you have a broader scope, that you can learn new things, pick up new areas, move to new frontiers that you may not have thought of before. And as I said, any job that you want to apply for, research it well, find out what it is that they're looking for, and understand for yourself what is it that your skills can do to contribute to that particular area. So I think this is important. I don't think those are close to mathematicians at all. But I think the young mathematics students should understand that they have to present themselves in a particular way to make themselves attractive to potential employers. And part of that is enthusiasm, the ability to learn. You have to show your employer that you're willing to learn new things, even though you don't have that, you may not have that particular training up to that point. And if there is some specific skill needed, learn at least that much to be able to present to your interviewer that you're interested and you have taken some effort to come up to that level. That's the only advice that I can really give. We can move on from here to the next panelist.
Maybe I can add to this. I check, when people ask, they don't check these websites. They are just putting questions here, but they should check websites of various places where they want to go. So DRDO, I saw, currently has 4 positions where they ask for MSc with first class in mathematics, applied mathematics, or computer science. So MSc in these 3 subjects they are asking. So just mathematics also they are asking. You can apply and you can get a job. In ISRO, they are asking specific, more engineering, but also they have PhD in computational fluid dynamics or computer science as one of the specialization. Then if you have aeronautics, if you learn some applied mathematics with aerodynamics as electives, National Aeronautic Laboratory, NAL, also hires people with applied maths and some specialization in various subjects. But you have to look up these things before just posting a question is what I would like to say.
Yeah. Thank you. Venkatesh, would you like to answer some of the questions you saw from the audience?
Yeah, I can pick up, for instance, there is a question on which nobody wants to take up, I guess, is doing a PhD from IITs, IISER, or anything is significantly better than doing a PhD. So I would like to say that doing a PhD from the institute matters when you're getting your initial placement, because they have built a brand value for themselves, and that's for a good reason. It's like when you go to buy a mobile phone, you're going to buy a mobile phone of a brand that you really know and understand. But does that mean it's the end of your career? Not at all. There are a lot of people who have got their degrees from lesser known institutes and have done extremely well. If you just look at the CEOs, our prime minister is an example. You look at CEOs of companies, you'll find examples. So the university doesn't determine necessarily your final destination. That is up to you to a large extent. Your initial path may be hard, but it's how you put in the effort after that, how exactly you perform is what is going to determine your future career path. And not nobody is going to ask you where did you graduate from 5 years down here once you've got 5 years of experience. They're just going to ask, they're going to judge you based on how you converse with them. They're going to judge you based on how you're expressing yourself technically or otherwise. Those are the points they're going to make before deciding whether to take you or not. Yeah, that's the one question. There are others I can take up, but this is what I thought I'd pick up.
Okay, so thank you very much. So we will now take questions which have been sent in the chat box first. Let us see. Yeah, so I don't see any questions actually.
Okay, let me take up one or two more that I have seen. Okay.
Yeah.
So someone has asked, how can a student enter reputed management institute after MSc Math, and how, etc. Now, again, the question has been asked without really looking at their entrance exam question papers. If you see, a major chunk of their questions are on what they call quantitative skills, which is mathematics at class 12 or BSc level. Now, one thing you should remember is that after you do MSc, you should not forget what you did at BSc and certainly not what you did in class 12. So essentially, if you have done MSc and carry forward all the knowledge that you have done so far, you should be able to do the quants part very easily, and then you can focus on the verbal ability and other skills there. In fact, the same thing goes in other questions people have asked, how to prepare for CSIR NET, UGC NET, etc. Now, again, if you see the last 8-10 years question papers on CSIR NET exam, they are mostly at BSc level core mathematics, linear algebra, calculus, and analysis. None of them are on your special topics in MSc. And some students say, oh, why don't you ask those questions? So doing special topics doesn't mean you forget the basics. Okay, so if you retain your basics, you should be able to address CSIR NET things, or if you wish to join IIMs, etc. The core quantitative skills that you have developed should continue. You should not say, I have done MSc, why are you asking me, is something a continuous function or not? Why not? You should not forget that. That's the point.
Yeah, thank you. So let's see our hosts, Saurav Sen.
There are now a few questions that have come on the chat box. So
Okay.
You may want to pick up some of them.
Yeah, so I invite the panelists to take up their favorite questions and answer them. Yeah, there are many questions here now.
Okay, let me take some questions which people are asking CMI. So CMI related questions, you please write an email to me or to admissions and we will answer them. I don't want to talk about my institute too much in this.
You're missing an opportunity to publicize.
Questions are, how to do this, how to do that, etc., etc. They're too specific. In general, you prepare well for the question from whatever you know, and look at past question papers. That will give you an idea of what level we expect. Okay. Yeah.
So yes, go ahead, someone.
No, there is a question about chaos theory having applications apart from weather prediction models. So, Gautam, would you like to remark on that?
Certainly, sort of chaos theory, statistical fluctuations in quantities is very crucial, for example, to understanding diseases, which is something that I'm looking at now. Most models, you can either have completely deterministic models that describe a disease, or you can try to understand what are fluctuations about this. And these fluctuations typically are chaotic in general, but there are ways in which we can model them using stochastic differential equations. I'm not sure, I would sort of not look at it saying I'm an expertise in this particular area, and does that qualify me to study something very, very specific? It's more, what does my mathematical training and understanding qualify me to think about a larger set of problems? So you will never find something that is purely in chaos theory. But what you need to do is to find something that is to understand how your training prepares you to solve problems in general that have a mathematical flavor or a mathematical tinge.
Yeah.
So somebody asked, what is the application of real mathematics? So I would just like to say one thing. I don't know what they mean by real mathematics, but ICM 2018 in Rio, they gave a Gauss medal to David Donoho, who has developed this advanced and very quick MRI technique to do MRI in a short time. And he uses many things like wavelet analysis and probability and all, but he also uses a lot of pure maths which he thought he would not use. For example, he uses functional analysis and L1 norm from functional analysis. So, and he himself was surprised that that has an real life application in mathematics. So this is just one of my examples. There are many examples like in credit card transactions, banking transaction, all these security, cryptography and all. There is a lot of prime number theory used there. So I don't know what they mean by real mathematics.
I can answer one particular question as I've seen here. Is that okay?
Yeah, sure. Yeah, please.
The question was, if you have only MSc mathematics degree, what do you need to go into interdisciplinary subjects like either in physics or in biology? So the computational biology group at IMSc takes students from any science background and any mathematics background. So we've had students from maths background, from applied maths, who apply to us and then they join us. What we look for is, first of all, some ability in the degree that you have, certainly, but also a broader interest in biological problems. So if you are not interested at all in biology, but have just applied to the program, then it's easy to figure out that that's the reason that you applied. So an interest and some knowledge, reading, understanding of biological problems that you're interested in is something, but your degree doesn't really matter to that. And that's also true, for example, for NCBS in Bangalore, which has a group that works on more mathematical biology, theoretical biology areas. I think with a field like computational biology, essentially you want to spread the net as large as possible. So to take people with an engineering background, mathematics background, varied science background. So we're really looking for students who are good and interested, but the interest is very crucial. Not so much your abilities or your specific training in that area, but certainly your interest in that area.
Yeah, so I will pick up from where Professor Gautam has said. There are a lot of questions on whether I should learn X or Y, which could be, should I do theoretical mathematics or applied maths? Should I do linear algebra, or should I decide based on what your interest is? Whatever is your interest is, just go after it. Don't really be picking a subject based on what offers better opportunity, career opportunity, or if you're good, you will have a good career. It's just have faith in that and pick what interests you and become good in that. And that should answer a whole bunch of questions on should I do X or Y.
So there are students who have asked questions like, what jobs can we get after BSc mathematics? So you see, it's BSc maths by itself doesn't give you a specific job opening. Okay, other than jobs which require just an undergraduate degree in any subject, you can take that up and be with rest. I mean, it doesn't prepare you specially for using your math skills per se. So ideally, I would say if you can get a job which uses these things, get into that. But even after that, parallelly try to do MSc at a later date and so on. Don't stop your education only at BSc.
Yeah. Again, taking off from what he said, there's also questions on should I do a PhD or an MSc. There are quite a few people who have asked that. I believe if you have the interest and temperament to do a PhD, do a PhD. And only if you feel you don't have it and you would like to get on with a job after MSc, do it. Because a PhD really gives, apart from many things, it's a fun time, fun 5 years where you really, many may not agree, but gives you a lot of freedom, trains you into getting into the depths of a subject, trains you into how to do research and all that. So it's a very good opportunity. You won't get those days back once you get into a career.
Let me add, after that, don't say that I have worked on this problem, now where I can apply this problem.
Exactly. That's the point.
Okay. Yeah. I agree, doing PhD is a good idea. It shows your higher analytical skills, etc. But don't limit yourself to just applying whatever you have proven.
Yeah. Don't look at PhD as training you in a very specific, narrow field. It is more about training you to do research and getting into depths of a subject.
Yeah. When I was leaving my PhD program, I graduated, I asked my advisor, give me some advice which is useful to me later. And he said, what you have done is your first PhD. Now you have to do PhD every 2 years in a different topic. So it's the same underlying principle of all kinds of jobs that you have to constantly learn and new skills and diversify into different domains. And life can be very interesting if you diversify. As you can see, what Professor Gautam Menon is doing, he's mixing all kinds of sciences and having fun. Right, and I'm sure this is same is true in industry where you are called upon to solve very diverse problems and learn different skills and enjoy. So, but the first requirement that every panelist has said that you have to find your area, your domain in which you feel comfortable and you love that subject. That is extremely important. If you can find this during MSc, well and good, but it has to be done towards the end of MSc, what you want to do. So whether you want to go for industry or PhD, that's the time to decide. So that can be done by doing a variety of courses so that you find what you love. Right?
Let me take up one question.
Yeah.
Elaborate on jobs in science communication. How can I start working towards it while pursuing MSc? So in general communication, including science communication, firstly, just start by explaining whatever you are doing in your class to someone who is not taking up that course. A fellow mathematician or mathematics student who has not taken a special paper that you have taken, try to explain that to the fellow mathematics student who is interested. Okay. Next, go to someone outside of MSc Math group. Let's say if you're doing a MSc, go to someone who has had a BSc Math, try to explain that to them. Why is it important? So it has to start with why should they listen to you? Okay. Next, you can take up some news item. Let's say right now everything is around Corona and COVID and so much of thing comes up. Pick up something, read about it and try to explain it to someone. Okay. So develop your communication skills to begin with to a very interested audience, and then you have to work towards getting someone else interested. So there is no coursework for this. You have to really practice and learn on as you go along, and you will discover interesting facets. I used to think 25 years ago that I am useless for the rest of the world. Nobody will be interested in talking to me because, as my friend said, I used to live in a Hilbert space. So
I can add a little bit to that particular answer. I also noticed that question. I think one other thing is that you should write in order to communicate. Write. There are many online venues like The Wire, for example, which accepts articles on science and mathematics. So use that to figure out how is it that one writes for the public. There are several jobs right now in multiple places that look at, they call things like science outreach fellowships, science outreach assistant, etc., project positions, as well as more long-term positions. The Indian Academy of Sciences has a program that is devoted to science communication and writing, and the other academies too. So if you want to move in that direction, the best advice is actually begin to do it. If you're good at drawing, begin to draw science-related cartoons. If you're good at writing, begin to write. Find venues in which you can publish these, and make sure that that people begin to see this. Then you can apply with something like a portfolio of work that you've done and interest people in what you've been doing.
Yeah, I absolutely agree. There was also a question somewhere on do MNCs employ math students? Google, Facebook, IBM, everybody employs maths people, and so there is no dearth of maths job employment opportunities in MNCs.
So I want to add to what Karandikar said. This is, people are asking specific questions. If I do this, what kind of job I get? If I do that, what kind of job I get? Main thing is, whatever you do, first you have to like that and learn that well. And you of course, it's not one subject that you learn around it, and then look for job. Before doing it, you are looking for a job, that's not going to work. I mean, yeah, of course, we have, I think Karandikar and Venkat and Gautam have given what all you need if you want specific kind of jobs. So you can have a look at those. Presentation will be online, and you can find out what you need if you really want only a specific kind of job. But otherwise, first do what you love most. Do the subject which you like, and then think about jobs.
Yeah, there is a question which can be answered, I think. Which government sectors which offer jobs in cryptography?
Defense is the main, defense and space. These two are the main consumers. Of course, through this only, you cannot directly join a intelligence bureau or something like that. But that requires, but how they get hold of these people, I have no clue. Okay. But direct job openings you will see in DRDO and other related defense entities directly with Navy that I work with, or ISRO.
Yeah. Okay. Which are the most important languages which work for mathematics? Yeah.
Important languages work for mathematics? I don't understand.
I mean, I think they mean to say there are so many languages like Python, C, or C++. So what should they learn?
I would say a lot depends on what domain you later want to work in. But if anything related with data science, analytics world, then the top thing is Python and R. Preferably both, if not one of the two. Python, probably. And if we are looking at a real core something, nothing like C++ or C. Because ultimately everything is translated to C and then implemented. But I'll leave to Venki to also elaborate on that.
Yeah.
This is, if you ask a computer scientist that's a,
Yes,
there'll be a war. There'll be war in the room. People picking up one language over the other. But currently what is popular is Python because it gives a very powerful language constructs to express your solution. So, and it's very easy to learn. So Python is a language I would start with. But Python has obvious limitations, like performance is a challenge. So you may want to learn other languages in case you're hit the performance hurdle that Python has. If you're going to work with just available libraries which solve the performance problem anyway, then you can. But Python is much easier to learn and has a rich library that you can use. So that's where I would start.
Yeah, I mean, there is a group in IIT Bombay. They bring in high school students and they teach them Python. And they really love, they write programs to do their math problems. And so it's a high level language, as you said. And people working in AI and machine learning nowadays, they program in Python.
There's a relevant question. What about Java?
Yeah.
For math student, Java, I wouldn't advise immediately. Much later, if the problem at hand really needs you to learn Java, like many of the panelists have said, you should be open to learning something new as per need. But if you want to learn a language for the sake of a language, it would not be Java.
And once you have learned one, let's say Python or C++, if your job requires Java, yeah, you can pick it up very quickly because there is a different construct. There will be few core differences, but mostly it will be syntax. So learning one language will enable you to learn other language quickly enough. So I would say today stick to C++ and or Python if possible both.
Yeah. And there are these great books called Art of Computer Programming, and we start with mathematical skills first.
Absolutely.
And yeah, so that is the basis. Just the language is not enough. You should be good at the mathematics and algorithms and so these things before you write a program. But the efficiency is obtained by knowing the relevant mathematics.
Well, someone is pumping
Absolutely.
one question again and again. So let me take that. Do you need multiple postdocs for a research position? Now, this is institute to institute, different policies. Some may require several, some may not require. So very difficult to say, is it required or not required? Okay. It also depends on how good your earlier CV is, publications are. This is a complex question. There is no generic answer. Yeah.
IITs and ICERs and MHRD institutes, they don't require postdoc position at all. Immediately after PhD, you can get a position if you are good. So the first 3 years, nobody gets a permanent job, but you can get a position in these institutes even without doing postdoctoral position. But many people advise that immediately after PhD, you should move to a institute where there is a research group which works in your area and broaden your horizon. So most people do one postdoc, and it's not difficult to get a permanent position after doing one postdoc.
The interesting question, what is the scope of MSc Math student in game theory, design and programming? Well, there is a lot of scope, but you have to be interested in gaming and programming. You should have participated. You should know what it all involves. Then you can bring in your math skills and apply them, right? You can't just take your MSc Math and say, okay, I want to do gaming and programming. What should I do now? Next. You have to understand. So generally, math application to any domain, you have to be comfortable enough to understand that domain. Okay? If you get a job as in finance industry and you don't know the difference between profit and revenue, then you have had it. You may be a great mathematician, but you will be a disaster. So you have to understand the domain and then try to apply your math skills there.
Yeah. So, Rajiva, there is a question which I'm sure you can answer this.
Jugal, I'll have to drop out now for another meeting at 6:30.
Yeah, we will soon close. Is there any application of differential geometry in the field of computer science? And I will add statistics also.
Application, if you say, okay, name one explicit thing, I don't know of. Okay. But what idea will come up where? So there is some area which is called topological data analysis. Okay, some concepts, some topology is getting used. One of my colleagues at CMI is into it. We have had a few seminars. Differential geometry, I really don't know. There must be some. There may be some. You can add something.
Yeah. I mean, in computer science, of course. The basic concepts in differential geometry play an important role in computer graphics and image processing. And, you are seeing our images. So how is it possible to see other people's images on the computer screen? So this happens because of image processing algorithms, which are heavily dependent on differential geometry and projective geometry.
Before we close, let me tell folks that those who had questions which were not answered, they could write to me or to all panelists, etc. We will see if that is enough meat in them. We'll answer them. Try to.
We will put these presentations on the website of VFM. Some audience have asked that they would like to read them further for reference. So all the panelists, I think they will be happy to leave their slides on the website of Virtual Math Fest 2020. I think we have, let us thank all the panelists for wide knowledge they have shared with us and from their long experience. And I'm sure it has been extremely useful to the people in the audience. And we thank the organizers to think about having these panel discussions, because this is the questions that we got are probably very, very relevant for their future careers. And I hope this panel discussion is useful to them. So let me thank Professor Menon, Professor Riddhi Shah, Professor Karindikar, and Professor Var Venkatesh for spending their valuable time from their busy schedules to come for this panel discussion. On behalf of all the organizers, I thank all of them. So thank you very much.
Thank you, everyone. Thanks.
Thank you, everyone.
Thanks.
Bye-bye.
Thanks a lot, Professor
Bye.
Verma, for being the chair.
Yeah, thank you, Professor.
Thank you.
Thanks a lot to all the panelists. Yeah.
Bye-bye. Take care, everyone.
Bye.
Bye.
Okay, bye. Bye.
Yeah, so maybe we can start. We'll welcome everyone to the symposium on topology, geometry, and dynamics session. We have here with us Dr. Shiv Prasad. So he will chair today's session. Yeah, over to you, Dr. Prasad.
So I welcome Dr. Ved Datta. So let me introduce Dr. Ved in brief. So he is currently an assistant professor of mathematics at Indian Institute of Science, Bangalore. He received a PhD in maths from Rutgers and in 2014. So thereafter, Dr. Ved spent some time at UC Berkeley, where he did his postdoc for 3 years. And he's very much a geometric analyst, and he's interested in complex geometry as well. So today he will speak on moment maps and canonical metrics in complex geometry. So over to you, Dr. Ved.
Thanks, Shiv, for the introduction, and also thanks to the organizers for the opportunity. It seems like a great initiative, and hopefully it will be repeated in years to come. So my talk will be largely expository, and I won't actually, apart from a very sort of small mention, I won't really talk about my own work at all. So the talk will broadly be about sort of one instance of a rather ubiquitous principle in Kähler geometry, namely the Kobayashi-Hitchin correspondence. So this correspondence seeks to sort of construct bridges between differential geometry on one side and algebraic geometry on the other side. And the first instance of this was, in fact, the Narasimhan-Seshadri theorem. So it's rather unfortunate that Professor Seshadri is not with us anymore, but of course, I mean, his immense contributions will far outlive him and will continue to inspire us. So I'm, of course, also an alumni of CMI, the institute that he founded. And I read somewhere that when he was visiting Harvard, he observed that a mathematician of the stature of Raoul Bott had to teach calculus to undergrads. And that got him thinking that in India, we have this sort of artificial divide between research institutes and universities. So of course, now with more and more IISERs and more IITs sort of hiring people who do active research, this going away slowly. And of course, IISc also now has an undergrad program, but Professor Seshadri was definitely a pioneer in India for this, and I mean, for this reason, he'll continue to inspire me in other ways than just his mathematics. So yeah, let me start with the talk. This is sort of a brief outline. I'll first talk a bit about the main problem, which is to construct constant scalar curvature Kähler metrics. I'll then take a detour and talk a bit about geometric invariant theory, which is sort of a finite dimensional analog and a motivation for the Kobayashi-Hitchin correspondence. And then finally, I'll describe what the Yao-Tian-Donaldson conjecture is and what are sort of the recent developments and what are the broad general problems that people will be working on in the future. So let's start with something very classical, the uniformization theorem. So it's of course well known that sort of two-dimensional orientable surfaces are all classified by their genus, that is the number of holes. And there's also a much coarser classification in terms of the sign of the Euler characteristic. So let's say I'm given an orientable surface and a Riemannian metric ds squared. Then there exists isothermal coordinates near every point. So in these coordinates, your metric looks diagonal. And the advantage is that the Gauss curvature then has a very nice formula. So you should remember this formula because you'll see something similar later on. And then of course, by the classical Gauss-Bonnet theorem, the total curvature is a multiple of the Euler characteristic. So then one form of the uniformization theorem is that given any compact oriented two-dimensional Riemannian manifold, there exists a metric conformal to the original Riemannian metric, which means it's a multiple of the original Riemannian metric. And this new metric has constant Gauss curvature. So a more sort of classical way of stating the uniformization theorem is that given any compact Riemann surface, its universal cover is either P1, which is just the sphere, or C, or the disk. And so the contact between these two statements is made by the observation that if X and Y are isothermal coordinates for G, then Z is a local holomorphic coordinate. So the set of, if you fix a G, the set of all metrics that are conformal to G, they're set to, they're called the conformal class of G. So much of geometric analysis in the 20th century was driven by attempts to generalize uniformization theorem, and many of these continue sort of obvious directions of generalization. One can just sort of seek a verbatim generalization of the uniformization theorem. So given a Riemannian metric, you seek a conformal metric with constant scalar curvature. But I'll actually talk about the second problem, which is given a Kähler manifold, instead of looking at conformal classes, you look at Kähler classes and you seek a Kähler form which has constant scalar curvature. Right. So I'll need to describe what all these terms mean. So in the next two slides, I'll sort of give you a quick crash course on Kähler geometry. Okay, so let M be a compact complex manifold of dimension n. Then this induces an almost complex structure. So this is basically just an endomorphism of the tangent bundle whose square is minus identity. And in local real and imaginary parts of the holomorphic coordinates, one can explicitly write down what this J looks like. And in fact, these sort of local transition functions satisfying the Cauchy-Riemann equations is equivalent to this J. This is a local definition for J, but this is equivalent to this J actually defining a global endomorphism. And so then we have this J, this almost complex structure. We also take a compatible Riemannian metric. So this is basically a smoothly, a Riemannian metric is just a smoothly varying inner product on the tangent space. And you want it to be compatible in the sense that J is an isometry. So then from this data, one can concoct a real positive 1-1 form called the associated 1-1 form. And so when I say real positive 1-1, I just mean that locally you can write omega as this, where this G alpha beta bar is a local matrix of functions which are Hermitian and positive definite, right? So we say that this Riemannian metric is scalar if this associated 1-1 form is closed. So that might appear to be a rather artificial condition, but it turns out that this is precisely the condition that's needed to sort of marry the Riemannian geometry with the complex geometry. So what do I mean by that? So the Kähler condition is equivalent to the statement that if you take the Levi-Civita connection, then the complex structure is actually parallel with respect to the Levi-Civita connection. So geometrically, this means that if you take a 1-0 vector field, if you parallel transport it, it will continue to remain 1-0. From an analyst point of view, this also means that there exists holomorphic coordinates Zi, so that locally your matrices are Euclidean up to the second order. Okay, so of course G alpha beta bar is positive and Hermitian. So of course by a linear change of coordinates, one can always diagonalize it at a point. And in fact, the diagonal will be the at that point will be the Euclidean metric. But more importantly, one can introduce a quadratic change of variables so that one can actually also kill the order Z term. And of course, one can't play this game further because the quadratic terms, the order Z square terms, also encode information about the curvature of G. So you can't sort of wish them away by a simple change of variables or by any change of variables. Okay, so because omega is closed, it represents, and it's real, it represents a cohomology class in the second de Rham cohomology, but it also represents a class in the 1-1 Dolbeau cohomology. So I'll denote this intersection by H11 of MR. And the class alpha, so this guy is a finite dimensional vector space. So class alpha in this space is said to be Kähler if there exists a in that class. And it turns out that the set of Kähler classes is an open convex cone denoted by script K, and this sits inside this finite dimensional vector space. So much of the power of Kähler geometry comes from this rather elementary DD bar lemma, which says that if you take any two cohomologous Kähler metrics, then they differ by DD bar of a function, right? So a priori, because they're cohomologous, they only differ by D of some one form. But then in the Kähler setting, you can actually refine this further and go sort of one step down and say that it's DD bar of a function. So in this sense, I mean, it helps in reducing many of the tensorial equations in Kähler geometry to scalar equations. So in this sense, Kähler geometry is similar to conformal geometry, where again, you only have one unknown function to work with rather than working with unknown tensors. Okay, so let me give you quickly give you some examples of Kähler manifolds. So the first simplest examples are Riemann surfaces. So the idea is that you take any compatible Riemannian metric, then the area form is the associated 1-1 form. And then because n has complex dimension 1, of course, D of the area form is going to be 0. Another sort of simple model example is that the complex flat space, our Euclidean space, which has a natural Kähler form, and the associated Riemannian metric would be the usual Euclidean flat metric. A more sophisticated example, which sort of plays the role that the sphere plays in Riemannian geometry, is that of complex projective space. So let me remind you of the definition. This is simply the set of lines in Cn plus 1. So you mod out Cn plus 1 by C star, where the action is basically the scaling action. And then it turns out that there's a nice Fubini's 2D metric, Kähler metric on this, which is called the Fubini's 2D metric. Once you know that the complex projective space is Kähler, you can construct lots of Kähler manifolds, because any complex submanifold, and of which there are plenty, you can always restrict the Fubini's 2D metric to this complex submanifold, and you'll again get a Kähler metric. So now, of course, you might wonder that all examples might be projective. This is wrong, because one can consider tori. So that's basically just Cn modded out by a lattice. And because the Euclidean metric is translation invariant, that induces a Kähler metric on the torus. And it turns out that for a generic choice of this lattice, this torus is actually not projective, right? So you can't embed this into CPN. So you might also wonder that all complex manifolds are Kähler. After all smooth manifolds have at least one Riemannian structure. In fact, there's infinitely many Riemannian structures. So you might wonder that maybe every compact complex manifold has a Kähler structure. This is not correct. So you can actually look at the classical example. So you look at C2 minus the origin modded out by Z, where the integers act by certain scaling. And it turns out this is not Kähler. You can easily see the good undergrad exercise that this is diffeomorphic to S1 cross S3, which means that the second Betti number is 0. But if there were a Kähler form, that would represent a non-trivial second cohomology class. So the second cohomology class cannot be trivial. So the Hopf surface is non-Kähler. Okay, so now let's talk a bit about curvature. So the Ricci form of the scalar metric is defined by this formula. So firstly, G alpha beta bar is a local matrix, but it turns out that this actually defines a global closed form, and the expression is very similar to that of the Gauss curvature. If you recall what the Gauss curvature looked like, and this is not a coincidence. This is because this form being closed, it represents a certain cohomology class, and in fact, it represents a very canonical cohomology class. It's called the first Chern class of the manifold. Okay, so in fact, in the Gauss-Bonnet, the integrand that shows up, which is K times dA, is also a representative of the first Chern class of the Riemann surface, which is why integrating that you get a topological number. Okay, so the scalar curvature is defined by simply tracing the Ricci form with this Kähler form omega. So you might wonder what happened to the Riemannian Ricci curvature. It turns out that the Riemannian Ricci curvature is related to this Ricci form the exact same way that the Riemannian metric was related to the Kähler form. And in fact, the Riemannian scalar curvature is also a multiple of the sort of Kähler scalar curvature. So in Kähler geometry, it's customary to forget about the Riemannian Ricci curvature and the Riemannian scalar curvature and only talk about these two, which is what I'll also do. So a question that Calabi asked was that given a Kähler manifold and a Kähler class, when does there exist constant scalar curvature Kähler metric in that class? So this is like the Kähler version of the Yamabe problem. So one thing to note is that if there is a constant scalar curvature metric, then that constant value is sort of a topological constant. In other words, if you choose any Kähler metric in alpha, then of course its scalar curvature might not be constant, but the average is always given by this topological constant. Okay. So this question has sort of driven progress in Kähler geometry for much of the last 70 years. So instead of talking about the entire Kähler cone, I'll talk about a sort of lattice within the Kähler cone. So I'll talk about what are called as integral Kähler classes. Although by now much of this discussion has been generalized to non-integral Kähler classes also, but there are more technicalities involved. And yeah, so there are more technicalities involved. So what are integral Kähler classes? Let's just take a holomorphic line bundle. So this is basically locally, if you choose, you can choose trivialization so that the line bundle looks like M cross C or an open set cross C, and then you have some gluing data, right? So then we say that L is ample. If you look at this quantity, so what is this quantity? This quantity is essentially, if you take a Hermitian metric H on L, which means you have a fiber-wise Hermitian product which varies smoothly, then this quantity is essentially the curvature of this Hermitian metric. So you take a certain multiple of the curvature of the Hermitian metric, then that is an element of the first Chern class of the line bundle. So no matter what Hermitian metric you pick, this omega H will always be contained in C1 of L. And C1 of L is actually contained in a lattice in H11 of MR. So we say that L is ample if there exists some Hermitian metric H, so that omega H is a Kähler form. And why are ample line bundles important? They're important because there exists an ample line bundle on a manifold if and only if it's projective by a theorem of Kodaira. Okay, so that's why ample line bundles are important. So I said, that you have an ample line bundle if and only if your manifold is projective. So we ought to at least construct one ample line bundle on a projective space. So on Pn, there is a tautological line bundle. Whose fiber over every point is basically the line corresponding to this point. Remember, every point of Pn corresponds to a line in Cn plus 1. And it turns out that all these lines sort of fit together so that you actually get a line bundle. That's called the tautological line bundle. And then the dual of this turns out to be an ample line bundle. This is called the hyperplane bundle and labeled as O of 1. Why O of 1? Because it turns out that all holomorphic line bundles can be essentially parametrized by multiples of or tensor powers of O of 1. Okay, so now I'm going to be always in the setting of a polarized scalar manifold. That means a manifold with an ample line bundle. Then the Yau-Tian-Donaldson conjecture states that there exists a CSCK metric in this scalar class if and only if this pair is stable. And stable is in quotes because part of the problem is to also understand what is the appropriate stability condition. Okay, so maybe let me make a few remarks before I move on to finite dimensional geometric invariant theory. So firstly, if omega naught is a reference scalar form, then by the DD bar lemma, any other Kähler form is omega naught plus DD bar phi. And then phi actually, if omega solves the CSCK problem, then phi actually solves a fourth order nonlinear PDE. So Q collects all the sort of nonlinear terms in the expansion of scalar curvature. So the linear part, you can see the principal part is basically like the Laplacian squared. So up to some error, the linearization is the Laplacian square. But of course, this is a highly nonlinear PDE, so solving it is quite hard. And in fact, nobody knows how to do this in general, which is why this is still a conjecture. So this is an instance of this Kobayashi-Hitchin correspondence that I mentioned at the beginning, which is sort of a correspondence between existence of canonical metrics on the side of differential geometry and some algebrogeometric condition of stability. And usually this correspondence is via solving a nonlinear PDE. So this provides a rather fertile ground for rich interaction between Riemannian geometry, analysis via PDEs and algebraic geometry. And as I mentioned at the beginning, the first example was the Narasimhan-Seshadri theorem, which was later generalized by Donaldson, Uhlenbeck, and Yau. And there are also many other instances. One very sort of rather cute example is that of Kähler-Einstein metrics on the sphere with cone singularities, which also is of interest to hyperbolic geometers and low-dimensional topologists. So in certain circumstances, when the cone angles are below 2 pi, this is actually connected to an algebrogeometric stability condition. All right, so now let me describe geometric invariant theory. So the whole point of geometric invariant theory is to be able to construct quotients. So let's take sort of the simplest example of GIT. So consider the C star action on the two-dimensional projective space. And the idea is to be able to construct a quotient of P2 by C star. Now, if you notice, there are three kinds of orbits. So a generic orbit will basically be, this is an affine picture, but a generic orbit will be like a hyperbola. But then there are these three special orbits One is the y-axis, the x-axis, and then the special point 001. Okay, so you can notice that this point 001 is actually in the closure of the orbits of corresponding to the y and the x-axis. And so the naive quotient, I mean, if you try to construct the usual quotient, that will clearly not be Hausdorff, right? On the so what GIT does is it basically throws away some bad points and it identifies some orbits. You must have heard this word S equivalence in Professor Balaji's talk in the afternoon. And so that is what GIT does. But before we go on to the actual definition, just consider the sort of coordinate ring of P2, which is basically just the polynomial ring in 3 variables. Now, the motto is that sort of functions on the quotient should be sort of G invariant functions on the top. And so if you look at the G invariant functions, that's isomorphic to the 2-dimensional polynomial ring, which is of course the coordinate ring of P1. So one would expect that any reasonable quotient would be sort of isomorphic to P1. Okay, so now let's actually define what a GIT quotient is. So our setting is going to be much simpler than what is normally considered. So let M be a projective variety and L is an ample line bundle, which is simply the restriction of the hyperplane bundle to M. My G is going to be a compact connected subgroup of the unitary group, such that its complexification also acts holomorphically on M. And then, as I said, the motto is going to be that functions on M mod GC have to be GC invariant functions on M. So here's a definition. Let P be a point in M and P hat be any corresponding lift to a point in Cn+1. So remember, if you have a point in the projective space, it corresponds to an entire line in Cn+1. So just pick some point in that line. Then P is called semi-stable if 0 does not belong to the orbit closure of P hat. And it's called polystable if it's semi-stable and also the orbit is in fact closed. Okay. So then the GIT quotient is simply defined by taking the semi-stable points and modding out by an equivalence relation. So P is equivalent to Q if and only if the orbit closures of P and Q intersect. Right, and it turns out that this also parameterizes the set of polystable orbits. Okay. So now I want to, so this is the algebraic viewpoint. Now I want to shift and consider what are called as moment maps, because that sort of makes contact with the differential geometric side. So with the same setting as before, suppose omega is in, I've written 2 pi, but let's say omega is in C1 of L. And suppose the subgroup of the unitary group acts by isometries. So this will of course happen if you take omega to be the restriction of the Fubini's 2D metric. Then in fact, there exists a map from M to the dual of the Lie algebra of G such that if you take the pairing of mu with, so you take any psi in G, take the pairing of mu with psi, that's a function on M, take the D of that, that is basically the interior product of omega in the direction of psi. Right, because if you take the Lie algebra element, G acts on psi, so the infinitesimal action of, so psi will also induce a vector field on your manifold M. So this particular thing makes sense. So if you have seen Hamiltonian actions, this basically means that the sort of 1 parameter subgroup generated by psi is Hamiltonian, and the Hamiltonian function is given by this pairing. Okay, and then we also want some technical conditions that mu is G equivariant, and it turns out in many cases you can also modify mu by a constant to still keep it G equivariant, but then we want to somehow normalize our moment map so that 0 is in mu of M. Then such a map is called a moment map for the action of G on M. And note that there is a G action on mu inverse of 0. So if this action is free, then one can form sort of the Kähler quotient mu inverse of 0 by G. So let's first discuss a model case, which also explains why this is called a moment map. So it has something to do with momentum in physics. So take the sort of phase space of n particles. So that's R2n with position and momentum coordinates q1 to qn and p1 to pn. Then there's a natural Kähler form given by this omega, and let G be the translation group. Then the Lie algebra is just Rn. And in fact, if you take a vector in the ith position direction, then in fact, the contraction with omega is just dpi. So you can check explicitly that the moment map is basically just the projection to the momentum coordinates, right? And hence the name moment map. So more sophisticated, let's give a couple of other examples. So you can consider the standard unitary action on Pn with the Fubini 2D metric omega Fs. Then this also has a moment map that you can explicitly write down. And there's another example. If you recall, we started this section by talking about a C star action on P2. You can restrict that to the compact subgroup U1 contained inside C star or the circle group. Then this also has a moment map, which you can explicitly write down. And then one can in fact check that if you take mu inverse of 0 by U of 1, that is actually isomorphic to P1. Okay. So remember our guess that any GIT quotient should be, of that example should be P1. And here we have a sort of symplectic quotient, which turns out to be P1. This is not a coincidence. And this is a good segue to this sort of very important theorem called the Kempfness theorem. So again, we are in the setting where M is some projective manifold, omega is the restriction of the Fubini 2D metric with the corresponding moment map. Then the Kempfness theorem says that there's a 0 of mu in the orbit of a point P if and only if this point is polystable. Or correspondingly, there's a 0 in the closure if and only if the point is semi-stable. And moreover, if you intersect GC with the zeros of mu, this in fact has a single G orbit, and hence said theoretically the GIT quotient will actually be equal to the symplectic quotient. And so in our example, I'll just explain this pictorially. We had these sort of generic, orbits, and then the zero set is basically represented by this line. So you can see that this sort of represents a P1 sitting inside. This represents a P1 quotient. So this line represents a P1. Okay, so maybe let me outline the proof of Kempfness, because this will sort of motivate some of the definitions in the next section. So the idea is to fix a lift of P to Cn plus 1. So I'll call that hat P. And then one defines a functional M given by this formula. Here, this is simply the Euclidean norm. And so this function is well defined on this set of cosets because G is a unitary, is a subgroup of the unitary group. It turns out that you have a critical point for this functional if and only if mu of G dot P is actually 0. So searching for zeros of the moment map is equivalent to searching for critical points of this functional. So this M should be script M. And then the idea is you take some psi in G and consider the restriction to, look at the one parameter family generated by I times psi and consider the restriction of the function to this. It turns out that the function is convex. So this guy here is a symmetric space, and it turns out that these things are geodesics in that space. So you're basically saying that M is convex along geodesics. And then one can argue that this set is closed if and only if M is proper. But then if you have a proper functional, you can also check that if 0 is not in the orbit, this is bounded below. So you have a proper functional which is convex, and then it of course has to have a critical point, right? So simple exercise, calculus exercise. So this is how Kempfness is proved. So let me end this section by discussing numerical criteria. So remember, semi-stability and polystability were defined in terms of the orbit closures of this group action. So it turns out by a criteria called as Hilbert-Mumford criteria, you in fact need to only look at orbit closures which come from one parameter subgroups. So this makes it much easier to check. And the idea is that if you take a one parameter subgroup, let Y be the limit as you apply this one parameter subgroup to some fixed point X, then Y will be a fixed point for this one parameter subgroup, which means that if you take sort of the lift to Y hat, then lambda t times Y hat will be a multiple of Y hat. So it will be t to the some power w times Y hat. So then the weight is defined to be minus w. And then to check semi-stability or polystability, you just need to check the sign of this weight. Okay, so essentially what I want you to take away from this is that you have these sort of one parameter subgroups, you define a certain weight at the limit, and then you check the sign of the weight to decide whether the point that you originally started off with was semi-stable or not. Okay. All right, so now that brings us to the final section. So it turns out that Donaldson observed this in the mid-90s, that one could put the scalar curvature problem into a moment map formalism. But unfortunately, that formalism is slightly technical and it's slightly different from what we have been talking about. So instead, I'll directly work with functionals analogous to this M functional that we had in the proof of Kempfness and directly define stability. So again, our usual setting, then the space of scalar forms in C1 of L can be parametrized by this space. This is a sub, I mean, this is basically an open set inside the set of C infinity functions. So this turns out to be a Frechet manifold modeled after the space of smooth functions, and which has a Finsler metric given just defined by this. I mean, F is a tangent vector to H omega at phi. So that means it must be a C infinity function. So you just compute its L1 norm with respect to the volume form defined by omega phi. Okay, then there is a certain functional called as the Mabuchi functional, which turns out to be convex along geodesics of the Finsler metric. And again, these are all, I mean, I'm not taking names, but there are lots of people whose contributions go into all these statements. So people like Mabuchi, Donaldson, Chen, Tamash, Darvas, and so on. And then one can sort of define a sort of geodesic stability by observing the slope of this Mabuchi functional at infinity. So if you notice, if in the finite dimensional picture, if something is stable, the slope at infinity has to be positive, right? So you can define some sort of geodesic stability, and you decree that there'll be strict positivity unless the geodesic comes from some trivial, in some trivial way, namely from a holomorphic vector field. So I don't want to go into technicalities, but the problem with this is that it's extremely hard to actually check geodesic stability, because it's, I mean, it's a transcendental quantity, so it's extremely hard to check. So ideally, one would like to replace this by a more algebraic quantity, which is what, by a more algebraic criteria, which is what is done by case stability. So because L is ample, you have a Kodaira embedding into a large projective space. So then, in the spirit of the Hilbert-Mumford criteria, I let M degenerate via a one parameter subgroup of GLN, GLN plus one. right? So M might, I act lambda of t on M and take the flat limit. So that might be some scheme. And then it turns out that one can associate a certain weight similar to in the Hilbert-Mumford criteria to this limit. And then you define the weight of this degeneration, that's called the Donaldson-Futaki invariant, as the weight as computed on this limiting quantity. So that's called the Donaldson-Futaki invariant for this degeneration. And now once you have a weight, you know how to define semi-stability. So M is called K semi-stable if for any Kodaira embedding and any one parameter subgroup, your weight has to be non-negative. And then it's called polystable if equality holds if and only if W is actually in the GLN orbit of M. Okay, and the conjecture is that ML admits a CSCK if it's K polystable. So heuristically, semi-stability is something like this, where the slope at infinity is 0, and polystability is where the slope at infinity is positive, unless you're in one of these sort of trivial directions. So I should say that this conjecture as stated, so by the way, this is called the Yau-Tian-Donaldson conjecture. As stated, it's almost certainly wrong. The crucial point is that sort of this trivial degeneration, to even define a trivial degeneration is a rather subtle concept, and maybe the way I've defined this trivial degeneration here is maybe too strong. So maybe one has to relax this a bit. Also, there are other relaxations. For instance, one can define what is called as uniform K stability, for which the conjecture is likely to be true. For K polystability, as I've defined, the conjecture probably is wrong. But then uniform K stability is again a hard condition to check. So the idea is one wants to get something in between, which will sort of be optimal. And also, in the end, maybe all of these are supposed to be essentially equivalent, but one wants to get a condition under which one can show existence, while it should also be sort of a good enough condition that one can actually check with by hand whether certain examples are K stable or not, which for instance geodesic stability is not. It's a hard condition to check. Okay, so I guess I'll just have 5 more minutes, so maybe I'll sort of quickly go over this section. So there is one important case where the conjecture is correct, and that was one of the major progress, major breakthroughs in the field in the last 10 years. Or maybe even in the last 20 years. So recall that the canonical line bundle, Km, is the line bundle that's locally generated by these top forms. So if L is either Km or the dual of Km, then it turns out omega is CSCK if and only if it is scalar Einstein, which means that the Ricci form is a multiple of omega. Sorry, so if L is actually the canonical line bundle and the canonical line bundle is ample, then by this work of Aubin and Yau, it's known that there always exists a Kähler-Einstein metric in C1 of Km. If Km is trivial, then in fact by Yau's work, which in part won him the Fields Medal, also shows that there is in fact a Ricci flat metric always, and hence a CSCK metric in any Kähler class. So then in the so-called Fano case, where the dual of Km is positive, this is the hard case. So notice that in this case, there is actually no requirement of K stability. You always have Kähler-Einstein metrics. But in the Fano case, you actually need K stability. But in dimension n equals 2, you actually don't, you need something simpler. So Tian proved in the late 80s and early 90s that there exists a Kähler-Einstein metric as long as the automorphism group is reductive. And then it was, he also formulated sort of the first precise version of K stability. And then very recently, Chen, Donaldson, and Sun proved that there, in fact, K-stability is sufficient for existence of Kähler-Einstein matrix when L is minus Km. And they used a continuity method through conical Kähler-Einstein matrix. So I think I'm running out of time, so I won't have time to say more about this. But I should maybe just mention that, as so often happens in math, once there is a big breakthrough, there are suddenly multiple proofs. So in fact, in 1 year, within 3 months, there were 3 new proofs. One done in collaboration with Gabor-Zaklidi, where we used a smooth continuity method, which is sort of a classical method that goes back to the method of Aubin and Yau. So historically, this was rather, I mean, nice that one could use the classical method to also get existence. But of course, we relied heavily on the work of Chen, Donaldson, and Sun. And the advantage here was that we were able to prove a G equivariant version, which helps in actually constructing examples of Kähler-Einstein manifolds. Soon enough, in 2 months, there was a proof by Chen, Wang, and Sun using Kähler-Ricci flow. And then the next month, there was another proof of completely different nature by a variational approach. This variational approach actually proved a slightly weaker theorem because it assumed uniform K-stability. But as I just mentioned, maybe in the CSCK problem, uniform K-stability is the right condition to actually use. Okay, so yeah, I'll maybe skip this slide on the overview of the CDS method. Maybe I'll also skip this slide on the moduli of Fano varieties, but I'll end with mentioning this dramatic recent development about 2 years back due to Jingryu Cheng and Chen, the same Chen who also worked on the Chen-Donaldson-Sun theorem. So if M is a Kähler manifold, then what they did was to get a priori estimates. So whenever you're solving any PDE, there's usually a continuity method involved. So remember, even Balaji talked about a sort of continuity method. Even for solving PDEs, there's a sort of continuity method that's involved. And the key is always to obtain a priori estimates. So what they showed was that if you have a CSCK metric, then the potential, all derivatives are bounded as soon as you know that the C0 norm is bounded. So all subsequent derivatives are bounded in terms of the C0 norm. Okay, and as a consequence of this, they were actually able to show that M admits a CSCK if and only if it is geodesic stable. So now the question that remains is how are geodesic stability and K-stability really related? And so of course, this seems like an algebraic problem. The other approach to actually solving the Yau-Tian-Donaldson conjecture is more in tune with the CDS method. You sort of set up a continuity argument and try to get some sort of geometric limits. But there you basically have to develop a structure theory for Riemannian geometric limits, which under Ricci curvature bounds, which is what you obtain when you are working with Kähler-Einstein matrix. This is rather rich and well developed by now due to the work of Cheeger, Polding, Tian, and so on. But in the scalar curvature side, I mean, if you only have constant scalar curvature and let's say an L2 bound on the curvature, on the full curvature tensor, then such a structure theory is not, I mean, is lacking and is in fact a hard problem in Riemannian geometry. So that is another possible approach where you might be able to more directly use K-stability rather than going via geodesic stability. All right, so I also wanted to end with this perturbation problem, but I think I'm out of time, so I'll just leave this slide as it is, and thank you for your attention.
Thank you, Dr. Datta.
Yeah.
So now I will open the session for questions.
Okay. Yes, I guess there are no.
It seems. Right. So here is a question.
There is a question in the chat box.
Okay. Oh, should I be able to see the chat box?
Yeah, sure.
Yeah, sorry. I should.
Yeah, Ved, just click on the chat, the icon at the bottom of the screen that says
Yeah,
chat.
that's what. But I think I'm in the full screen mode, so I'm not able to.
Doesn't it pop up? Oh, it's going to be behind your screen. Do you want me to read out the question?
Yeah, sure. That might save more.
Yeah.
That might save time.
Okay,
Yeah,
so this is a question I think that was posted on the YouTube channel and it's been relayed by Arpan.
Okay.
The question is, in general, when does the moment map exist given an action of a compact Lie group G on a symmetric manifold M, comma, with a Kähler form omega? I suppose by demand, the action has to be Hamiltonian.
Right. So, right. So the definition of a Hamiltonian action is that there exists a moment map. So that's a tautological statement. But one of the necessary conditions, or at least that's the definition I know. So, so one of the necessary conditions is, of course, you can assume that your manifold is simply connected because, so if your manifold is simply connected, one can check that there always exists a moment map. The other, so what happens in these settings is that your group action is not only an action on M, but it also lifts to an action of L. So there is sort of, this is called linearization in algebraic geometry, that there is an action on the total space of the line bundle. And in that case, you can actually show that there will be a Hamiltonian for any Lie algebra element. You'll have a corresponding Hamiltonian. So that is what happens in the setting of GIT. Because so remember, I already assumed that your G is sort of a subgroup of GLN, and we know that GLN not only acts on Pn, but it actually acts on the cone over Pn, right? On all of Cn plus 1. Right, so so that means, the total space of this line bundle will also be some sort of a cone inside Cn plus 1, and so your group will also act on that. So it acts on the total space of the line bundle, and then one can show that it will definitely be Hamiltonian. So I hope that answers the question. Okay, any other questions?
Yeah, probably a very naive question.
Okay.
Which is, in your talk throughout, since the question was about the existence of CSCK metrics, so we are really, the focus is on Kähler forms. And a lot of your definitions were stated as if one had a Kähler structure in the background.
Right.
Now, I don't know enough about this, and so I was probably not able to decode some of your definitions, but then the notion of a moment map is purely a real notion, right?
True. Yeah.
If I so what is sort of the best structure I need to endow a compact manifold with? If I have with a Riemannian structure.
No, just a symplectic structure.
Just a symplectic structure.
Yeah. So you can talk about Hamiltonian actions for symplectic manifolds. And in fact, this quotient that I looked at, mu inverse of 0 by G, that's in fact, it's defined in the symplectic setting. if you have a moment map, and that's called, I think, the Marston something symplectic reduction or something of that sort. But the point is that if your symplectic structure actually comes from a Kähler structure, then in fact this mu inverse of the symplectic quotient actually becomes a genuine Kähler manifold, as long as the group action is free and so on.
I see.
So,
Okay.
but yeah, you can do it for symplectic, and in fact, I don't know enough about these things, but these things like are also defined for symplectic manifolds. So you have this whole industry, right, which is essentially taking a complex line bundle of a symplectic manifold. So many of these things, I think, can be done in that generality, but you have to make contact with GIT, right? You need a Kähler structure.
Okay, I see. Right. Yeah, thanks.
Yeah, no problem.
So can I ask a question?
Yeah, sure.
So hi, Ved, a very nice talk.
Hi,
so,
I remember we met in Notre Dame a few years back, right?
exactly. Yeah.
Hi.
So my question was that, is there any like geometric flow proposal for like this Yaotian-Lorentzian conjecture of these sequences?
So there is a flow called as the Calabi flow. But I mean, generally the experience has been that it's much harder to understand flows than the corresponding elliptic problem. So
right.
for instance, I mean, even though the Kähler-Ritchie approach worked only a few months after we were able to make the Obayam method work, even then, I mean, sort of many of the PD techniques involved in the Obayam method were known for about 30 years, whereas Kähler-Ritchie flow, they had to sort of newly develop all these tools. So the experience is that flow is generally a harder thing to deal with. But having said that, I should also mention that so this a priori estimate of Cheng and Chen, in that same paper, they prove a rather remarkable condition. So nobody as of now knows whether the Calabi flow even exists for all time. Okay, so that's the first step, right? In any flow, you want to know if it exists for all time. But what these guys proved is that the flow exists as long as the scalar curvature doesn't blow up. And this is again quite remarkable because, I mean, a priori it was known that the flow doesn't blow up if the curvature doesn't blow up.
Right.
And even for Kähler-Ritchie flow, those are sort of standard Xi type estimates, right?
Right.
But what they were able to actually do is not even Ricci curvature being bounded, but they were actually able to reduce it to scalar curvature being bounded. So that is a pretty remarkable achievement. So, but I mean, yeah, it's conjectured that the Calabi flow exists for all time, but I don't think. I mean, there are examples where this is known, but I don't think anyone has any idea in general. Yeah.
So I guess then there are like no examples or of singularities of this Calabi flow yet. Then, if they are
not that I know of in finite time. Of course, at infinite time there would be most likely there would be singularities. There would also, in the unstable case, most likely there would also be collapsing because you have basically these. I mean, there are examples of projective manifolds where it basically breaks up into two complete pieces and so on, and you have collapsing at sort of each end of these complete manifolds. So the geometry is much more complex. So at infinity, of course, there are known examples of singularities, but as far as I know, for finite time, I don't think anyone knows because in this paper of Cheng and Chen, they actually put this as a conjecture, not only as a question, but as a conjecture that the Calabi flow exists for all time. So I think there are no known examples of finite time singularity.
Okay, thanks. Thank you.
Yeah.
If there are any other questions, okay. So then we should thank Professor Datta.
Thanks a lot for,
okay. For this nice talk.
Okay, thanks.
So now, thanks.
Okay, so do we reconvene in like 15 minutes or what is the?
So I think, so now there is, I think, next speaker.
Oh, right away. Okay, so I'll switch off the mic. Yeah. Anyway, thanks a lot.
Hi, Steve. How are you?
I am good.
Good to see you.
Here is Kaushik Sarkar.
Dr. Kaushik Sarkar, yeah, okay.
Hello. 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 Hello.
Hello. Now it is now
Yeah, we can start, right? Shubhaya?
Okay. Okay. Good evening, everyone. I am Kaushik Sarkar, and I am going to present my talk entitled Topological Warm-up of Partial Metric Spaces. Can you hear me, sir? Sir, can you hear me?
Yes.
Okay, okay. Let's.
Yeah, please wait. Please wait. Yeah.
Yes. So let's welcome Dr. Kaushik Sarkar from University of North Bengal. So he will speak on topological warm-up of partial metric spaces.
Okay. Good evening, everyone. I am Kaushik Sarkar, and I'm going to present my talk entitled Topological Warm-up of Partial Metric Spaces. So first, begin with an example which leads my interest to study partial metric space. Let x equal to s omega be the set of all sequences over a non-empty set S, and consider a mapping G from x cross x to x by dxy is equal to 2 to the power minus k, where k is the largest non-negative integer or infinity, such that xi yi is equal to yi for each I less than k. Then it is not hard to check that xt forms a metric space. In computer science, every sequence is approximated by a section of it, however long it may be, because it is not possible by writing a computer program to compute a sequence and print out its value in finite amount of time. Now, suppose our definition, or consider D, if we extend it to Y, the set of all finite sequence over S, then D fails to form a metric only for the reason dxx equals to 2 to the power minus k. That is for non-zero self-distance. So the natural question arises, is there any generalization of metric space axioms so that we can introduce the non-zero self-distances, and so that the familiar metric and its topological properties such as Cantor intersection theorem, Baire category theorem retained? Partial metric space appears as an affirmative answer to this question. In S.G. Matthews introduced this, and in last 3 decades, many mathematicians Altun, Badges, Turmach, Ultra Valero have studied master geometric space to some extent. In this article, we have considered a suitable definition of convergence of a sequence in a partial metric space. We have introduced star-closed sets in partial metric space and studied the relationship among star-closed sets in partial metric spaces and its induced metric spaces. Also, we have shown that Cantor intersection theorem and Baire category theorem can be achieved in partial metric space. And just preliminaries. So Matthews defined a mapping P from X cross X to R plus, where X is a non-empty set, is said to be partial metric if it satisfies the following conditions. This one is the equality implies indestency and symmetricity, self-distance property, and this is the modified triangular inequality. And then the XP is said to be partial metric space. And Matthews defined the convergence of a sequence in XP in such a way that Xn is converges to X if limit n tends to infinity, Pxn x will be Pxx. And a sequence Xn is a Cauchy sequence if limit n tends to infinity, Pxn xn exists. And if partial metric space XP is complete if the Cauchy sequence in X is convergent in such a way that limit n tends to infinity, Pxn x equals to Pxx is equal to limit n tends to Pxn xn. Okay. Now we consider an example. First, we once again, this is the definition for convergence according to Matthews. Limit n tends to infinity, Pxn x equal to Px. Now we consider an example, and we are taking x equal to r plus and Pxy is equal to maximum of xy. Then it is easy to check that this forms a partial metric. Now we consider this sequence Xn, this 1 2 1 2 1 2, this type of sequence. Then this sequence also convergent in X, which is absurd. So we consider the definition of convergence of a sequence in a partial metric space as in Badges. Badges, Cooperman, and Buckton they have done a paper in 2009 in American Mathematical Monthly, and they have considered this type of this definition of convergence, where they have extended this portion limit n tends to infinity Pxn x, Pxx equals to limit n tends to infinity Pxn xn. And accordingly, as the definition of convergence changes, we consider the definition of a complete partial metric space as if in this space every Cauchy sequence is convergent therein, and there is no change in the definition of Cauchy sequence. In partial metric space, if we define the functions dp and d omega in such a way, d omega xy to pxy minus pxx minus py, where p is a partial metric, then we can see that d omega is a d omega forms symmetric, and the same results hold for the dpxy, where we can define dpxy as pxy minus minimum of pxx and pyy. Then this forms a metric. We called it induced metric, induced by the partial metric P. In 2012, Altun and Durmach proved this following result, which will be very useful in proving so many results in partial metric space. They proved that the convergence of a sequence in a partial metric space is equivalent to the convergence of a sequence in its induced metric space. Throughout this paper, by a closure P we mean the closure of A in XP, and by simple A closure we mean the closure of A in its induced metric space. Now we define star closure. Once again, we consider an example. Let A equals to open interval 0 to 1, and the same partial metric on R plus P, where P is equal to maximum of xy, then A closure P is 0 to infinity. And if we take A, any point A from A closure P, then we cannot get any sequence xn in A such that xn converges to A. Xn converges to A in the sense of Badger's definition. So sequence lemma does not hold. So we now define star closure in such a way a star closure equals to A union L, where L is the limit of the convergent sequence in A. And A set A is said to be star closed sets if A equals to a star closure. Here is some similarities with star closure with metric spaces. We can see this also holds for metric space. Okay. And partial metric space generates a T0 topology. It's not even T1. There is a doubt about the uniqueness of the limit of convergent sequence therein. We remove this doubt by proving the following result. This is the proof. Just using the modified triangular uniquity, we can show that the limit of sequence is unique. Now, so this is also similar to metric space that is star closure is a closed set, and here is the proof. I will not go through the proof because time is very short. Okay, now. Okay, now. Here is some relationship between the closed walls. Any closed wall in XP is a star closed set in XP. And here is the proof. Just using the definition of star closure, we can prove this. But the converse of this theorem is not true. If we take R plus with P, where P is a function, P maximum of XY, and A is 1, 2, 3, 4 singleton, then A closure P is not equals to A, but A star closure is equals to A. So A star closed set may not be closed set in a partial metric space. Here is another theorem. It states that any star closed sets in XP is closed sets in XDP. And we can prove this theorem using this equivalency of convergence in XP and XDP. And this is the technique of this proof. And this is another example which shows that if a closed set in XDP may not be closed in XP. Now this is a theorem which states that if xn converges to x and yn converges to y, then limit n tends to infinity pxn yn is equal to pxy. Now we will prove Cantor intersection theorem. Before that, this lemma will be very useful. So this lemma tells that in a partial metric space XP, if xn is a Cauchy sequence in XP, then it will be Cauchy sequence in the XDP and vice versa. And if XP is complete, then also XDP will also be complete. And both this condition is equivalent. So proof part A is done by Altun, and we prove the part B, that is if XP is complete, then XDP is complete, and if XDP is complete, then XP is complete. Okay, and this is the sketch of the proof. Okay, now we define diameter of a set in a partial metric space. So we define diameter of a set in a partial metric space in such a way that P of A equals to supremum of Pxy minus Pxx for all xy in A. And like in metric space, we can show that diameter of A is equal to diameter of a star closure. And this is the proof. Finally, we are proving Cantor intersection theorem, which tells that a partial metric space XP is complete if and only for every sequence Fn of star closed sets satisfying Fn plus 1, that is nested sequence of star closed sets, and its diameter tends to 0 as n tends to infinity, then its infinite intersection is singleton. And here is the proof. This case of the proof is that just we take a Cauchy sequence, and using this we will consider this fn xn plus p minus 1, and we will show that this fn plus 1 is star closure satisfies this condition a and b, that is nested and its diameter tends to 0, and then its infinite intersection contains a non-empty, and so it contains an element x, and using this we can show that this is the proof. Now, Bayer category theorem. First, begin with some definitions. A set B in a partial metric space XP is said to be no higher dense in XP if every open set U in XP contains an open set V, so that P intersection V is equal to 5. And a partial metric space is said to be second category if it cannot be written as a countable union of no higher dense sets. Otherwise, it is of first category. Before proving this Bayer category theorem, we will prove this lemma, which will be very useful. It tells that a closed ball in a partial metric space is not a is a star closed set. A closed ball in a metric space is a closed set, but here is closed ball may not be closed sets. This is an example that a closed ball may fail to be closed set in partial metric space. If we take R plus P, the same P, then we can see that BP01, which is a closed wall, is not a closed set, and this closed wall is actually star closed set. And this is the proof that a closed wall is a star closed set. And here is the final theorem, which tells that every complete partial metric space is of second category. And we prove this, but this theorem actually can be proved without using Cantor intersection theorem. Here we prove this using Cantor intersection theorem only. So we proceed this theorem by contradiction method. We just take x can be written as a infinite union of no higher dense sets, and just using this no higher condition, dense condition, we have created a sequence of closed star closed sets, and then using Cantor intersection theorem for in partial metric space, we can show that XP is of second category. And these are the references I used to prepare this paper. And thank you all.
Thanks, Kaushik.
Thank you.
If there are any questions. Okay, I have one. Can you explain again how you generate the topology from a partial metric?
Please ask me again.
Right. Right. So how you generate the topology from a partial metric?
How did I
generate the topology for a partial metric?
It is not clear to me now also. Please ask one
so you have
more.
Right. So you have a partial metric space, right? Space with a partial metric. So how you generate the topology? Like how your open balls look like?
Okay. Its open balls look like pxy y in x such that pxy less than pxx plus epsilon. Here is the difference, because like metric space dxx is 0. Here for partial metric space dxx may not be 0. So we define here open balls pxy less than pxx plus epsilon.
Okay. if there are any more questions.
Yeah, I guess no questions.
Okay. Okay. Thank you, Kaushik, for a nice talk.
Thank you.
So,
Yeah, we can start the next talk maybe.
yes. So next we have Sharvari Nitin Tikekar from IISER Trivandrum. Can
Hello. Hello. Hello.
Yeah.
Hello. Yes.
Yeah.
So
Can you hear
please
me?
you can start.
Okay.
Please share your screen.
Yes.
Is it fine now?
Yes.
Maybe full screen.
Okay.
The left one. Yeah.
Yeah.
Presentation. Okay. Yeah.
Okay. So welcome Sharvari Nitin Tikekar from IISER Trivandrum. So she will speak on a Laplacian on the full space.
Thank you, sir. Good evening, all. I would like to first thank the organizers for giving me this opportunity to present our work here. Today, I'll be talking about a construction of Laplacian on the full shift space. So basically in class, this is a joint work with Srihari Sridharan. So basically in classical calculus, to define a Laplacian, it is necessary for the underlying space to be smooth. But after Mandelbrot's work on fractals, it was observed that these fractals are in fact abound in nature, and then it became necessary to study and analyze various physical phenomena on these kind of these rough surfaces. So towards that end, Goldstein, Kosoka, and few other mathematicians defined the Laplacian as a Brownian motion on Sierpinski casket. This was more of a probabilistic approach. In 1980s, a more direct and analytical approach was proposed by Kigami, where he constructed a Laplacian on Sierpinski casket as a renormalized limit of difference operators defined on finite sets, subsets of Sierpinski casket. And later, a Laplacian was constructed on many other fractals like self-similar structures and more hybrid fractals, non-self-similar structures as well. So we know that the shift spaces offer a symbolic coding of various fractal structures. So what we aim to do here is we want to construct a Laplacian on this abstract and disconnected setting of the shift space by similarly following the Kigami's method by constructing a sequence of subsets of shift space and defining a difference operator on those. So first I'll start with defining what a shift space. We have a symbol set S, which we have n symbols, at least 2, and a shift space is defined to be a sequence, a space of sequences with symbols coming from this S. A shift map sigma on sigma n plus takes a sequence from this sigma n plus and it deletes its first term and shifts the entire sequence one place to left. So this is also known as left shift map. We also have a metric on sigma n plus. So for 2 points x and y in sigma n plus, we look at the first place where x and y disagree. So that is rho of xy, with rho of xx is defined to be infinity. Then the distance between x and y is given by 1 over 2 power rho xy. A cylinder set of length m is a set of all such sequences in sigma n plus, which begin with this particular word of length m. In general, it's not required that the cylinder sets should fix the first positions in the beginning. We can have any places in the sequences fixed. But for our purpose, it's for convenience, we want the cylinder sets to fix the initial positions. The symbol set is having a discrete topology. So on sigma n plus, we have a corresponding product topology generated by this discrete topology. And we know that these cylinder sets in fact form a countable basis for this topology. And also this metric D generates the same topology on sigma n plus. Also in symbol set, we have a probability measure which where each symbol occurs with probability 1 by n. So we have an equidistributed Bernoulli measure mu on sigma n plus, which is specified on these Borel sets of length m as 1 over n power m. These are some standard properties of shift space. It is a compact metric space. The cylinder sets are both closed as well as open, and the shift space is totally disconnected and a perfect metric space. Now each point in sigma n plus has n pre-images where these are obtained by shifting the entire sequence one place to right, and the first place can be filled with any of the n symbols. So we have n inverse branches for the shift operator sigma. Further, sigma is onto and continuous transformation, and also the probability measure mu is sigma invariant. Now using those n inverse branches of sigma, we can obtain a self-similarity structure on this shift space. For instance, each inverse branch is defined by sigma L, where the first position is filled with the letter L. And then sigma n plus can be written as a disjoint union of images of sigma n plus under these inverse branches sigma L. A more general self-similarity can also be obtained by, instead of considering just one symbol, now we consider a word of finite length m. So for each such word, we can define a map sigma w, which concatenates a string of length m in the beginning of a sequence. And then sigma n plus can be written as this disjoint union. So now we'll construct an increasing sequence of subsets of sigma n plus. We start with the set V naught, which is the set of all fixed points of the shift map. So by 1 dot, I mean a constant sequence 1, 1, 1. By 2 dot, a constant sequence 2, 2, 2, and so on. Using this V naught inductively, we define each Vm for m greater than equal to 1, which is the inverse of Vm minus 1, and which can also be written as mth order pre-images of points in V naught. So any mth order pre-image of this has first m places filled with some word of length m, and then it is a constant sequence. For example, it precisely looks like x1, x2, xm, and then L dot. These VMs form an increasing sequence of subsets of sigma n plus. Since each point has n pre-images, the cardinality of each VM is n power m plus 1. The set V star given by union of Vm, which is the space of all eventually constant sequences, it is a countable dense subset of sigma n plus. Now to construct a difference operator on each of these VMs, we need to consider a set of all valued functions on VM, and we denote it by L of VM. And the standard inner product on L of VM is defined like this. Now any point P in VM it actually looks like this: P1, P2, PM, and PM plus 1 dot. By PM plus 1 dot, I mean it is a constant sequence after this. So the points in VM which are closest to P will have to look like they will be agreeing with P on the first m places, and they'll differ on the m plus first place. So all these points will be called as the neighbors of P, and this UPM is the deleted neighborhood of P in VM, which is the set of all these neighbors. So it, since this L can have only n-1 symbols, the cardinality of this set is n-1. For example, if we look at this point 21 dot in V1, its deleted neighborhood is given by this, where all these points agree with 21 dot in the first place, and the second place and so on is different. Now we will define a difference operator H0 on L of V0. So we take a point L dot in V0, and so there are n-1 points in V0 other than L dot, and all of these are at equal distance from L dot. So we look at this difference term U of K dot minus U of L dot, where K is coming from S. So since this sum, this entire sum then looks like this. Now using this H0, we define further difference operators HM on L of VM. So for that, we split this VM into its two subsets. One is VM minus 1, and the other is remaining VM minus VM minus 1. Now for points coming from VM minus VM minus 1, it has neighbors only in this set VM, and it has n-1 neighbors. So that difference term in fact looks like this. And for the points P coming from VM minus 1, it has HM minus 1 acting on it, and as well as it has neighbors in VM. So we have a difference term coming from there as well. Now for the purpose of this talk, we are mainly concerned with action of HM only on the points in VM minus VM minus 1. Now using these difference operators, we can define a Laplacian. So we'll take two continuous functions on sigma n plus, and we'll say delta u equal to f if the following limit is 0. So here we are looking at hm u of p divided by mu of this m long cylinder set, and we are taking maximum over all these points p in Vm minus Vm minus 1. So if you see, this actually looks like a discrete
फॉरवर्ड कर दिया, फीडबैक फॉर्म फॉरवर्ड कर दिया, फीडबैक फॉर्म किसी और को फॉरवर्ड मत करना.
This looks like a discrete version of the classical Laplacian. In this case, we'll call delta to be a Laplacian, and d mu will denote by d mu domain of delta. It is observed that d mu is a dense subset of continuous functions on sigma n plus. Now, if delta u is equal to f, this f can be formulated point-wise. For example, if x is a point in sigma n plus, we can consider any sequence of points Pm which converges to x, where each Pm is coming from Vm minus Vm minus 1. Then fx can be written as limit of n power m plus 1 hm u of Pm. Now I'll just give an easy example of a harmonic function whose Laplacian vanishes. So any point P in Vm can be completely determined by its first m plus 1 entries. So for this particular P, we'll consider a characteristic function of this m plus 1 long cylinder set. So whenever our PMs are coming from Vm minus Vm minus 1, for large enough m, all these points will either belong to this cylinder set or they will not. So for large enough m, hm u of Pm becomes 0. So Laplacian of these functions is actually 0. Now I'll briefly describe the Dirichlet boundary value problem on shift space. We'll start with constructing a Green's function on sigma n plus. It is defined as follows. So for xy in sigma n plus, if rho of xy is 1, that means if x and y disagree on the first place itself, then g of xy is defined to be 0. And if rho xy is greater than 1, then it is defined to be this finite sum. Here, these chi-sm and chi-rm are the characteristic functions of m+1 long cylinder sets particular to this point R and S. And GMRS is given by this, where so GMPQ is 2 by n if Q is equal to P, and if Q is a neighbor of P, then GMPQ is 1 by n and otherwise 0. So this is in fact obtained by the difference operators itself. So since the difference operators HMs are finite, they have a matrix representation. And when we consider HM only restricted to VM minus VM minus 1, we obtain a matrix that is invertible. And the negative of inverse of that matrix is precisely this GMPQ. So Green's function satisfies these properties. It is for any two distinct points xy, it is bounded by this term. So whenever one point P comes from V star and y in sigma n plus, g of Py is always finite. However, when x is coming from sigma n plus minus V star, g of xx is found to be infinite. And the Green's function is mu almost everywhere continuous. Using the Green's function, we define a Green's operator on space of mu integrable functions on sigma n plus, whose kernel is the Green's function that was just defined. So for an integrable function f, g mu f is also integrable. And for a continuous function f, g mu f is continuous. And moreover, g mu f restricted to V naught is 0. And a more important property that g mu f was observed to satisfy is this. So whenever f is continuous, we have g mu f belongs to the domain of Laplacian, and delta of g mu f was found to be minus f. Now this is the analogous Dirichlet boundary value problem for sigma n plus. So for any given continuous function f, and for any zeta given in L of V naught, we can find a continuous function u coming from d mu, which satisfies delta u equal to f, and u satisfies the boundary condition zeta. So since the sigma n plus has, it is a totally disconnected space, and it is of topological dimension 0, the topological boundary of sigma n plus is of very little significance for us. So we can define a boundary of sigma n plus to be V naught here. And finishing on the boundary V naught. So we will construct a function u like this. And here chi p naught is the characteristic function of a cylinder set of length 1 determined by this point P. Now delta of this is 0 because delta is linear, and delta of g mu f is minus f, so u satisfies this, and g mu f restricted to V naught is 0, so u restricted to V naught is this zeta, so u also satisfies the boundary value condition. The uniqueness up to harmonic functions is easy to see. So these are some of the references. This work can be found in this paper, which is on arXiv. We have also studied spectrum of the Laplacian, which can be found in this paper. Thank you.
Thank you, Sharvari. Now over to audience if there are any questions.
So I have a question.
Okay. Yes, please.
So can this work be done when S is countable? Like you have considered a finite, so this S is finite.
Yes.
The set S.
Yes.
Can you do it for countable alphabet?
I think it can be done.
Okay. So the Laplacian, what, like, would it, everything go through?
I think it will go through.
Okay. Thank you.
Yeah.
There is a paper by Sebastian Frenzy on countable substitutional dynamical systems. You should look it up, and I think, like, if you say that this work can go through, then it makes sense to do it for countable as.
Okay. Like,
Thank
as
you
of
for.
now, I'm not seeing if there will be any problem, at least as of now.
Okay.
Sure, I'll look into that. Which paper did you say?
Sebastian Frenzy. It's and the paper is Substitutional Dynamics on Countable Alphabets.
Okay. Okay, sure.
If there are no more questions, let's thank the speaker.
Okay, thank you.
Thanks, Sharvari, for your nice
Thank
talk.
you. Thank you.
So maybe you can stop sharing your screen now.
Yeah.
So the final speaker, we have Shubham Dwivedi from University of Waterloo.
Okay, so let me just share my screen. So I guess, so am I audible?
Yes.
Okay.
Welcome, Shubham.
Yeah, hi.
Yes, you can share your screen.
Okay. Okay, so is this visible?
Yes.
Okay, so just let me know whenever I should start.
Right. So it is in presentation mode, right?
Yes.
Yes. Okay. Yes. Okay. So welcome, Shubham Dwivedi from University of Waterloo. So he will be speaking on deformation theory of nearly G2 manifolds. Okay. I think you can
Okay,
start.
so, okay, yeah. So first of all, I would like to thank the organizers for this great initiative and for giving me an opportunity to speak here. So I'm going to speak about deformation theory of nearly G2 manifolds. So G2 manifolds are manifolds with exceptional holonomy, and I'll explain what they are in a bit. So this is based on a joint work with Ravini Singhal, who is also a PhD student at University of Waterloo, and it's based on the paper with this archive listing. So let's start with a brief introduction to G2 manifolds, or manifolds with a G2 structure. So suppose I have a 7-dimensional smooth manifold, and throughout this whole talk, the dimension of the manifold will be 7, because that's where G2 structures make sense. So suppose I have a 7-dimensional smooth manifold, then a G2 structure on M is just a 3 form. It's a differential 3 form denoted by phi, which is non-degenerate. So for the purposes of this talk, all you need to know about phi being not degenerate is that it induces a Riemannian metric and an orientation. So if I have a G2 structure on M, then this means that I have a non-degenerate 3 form phi, which means that it induces a Riemannian metric G phi and an orientation in a non-linear way. So that's an important part, that phi induces the metric and an orientation in a highly non-linear way. So once I have an orientation and a metric, I can define a Hodge star operator. So this is star, and I'm writing subscript phi to emphasize the fact that this star depends on what phi is. So once I have a Hodge star operator, I take the Hodge dual of phi. So I get a 4 form because I'm on a 7-dimensional manifold. And let's call this Hodge dual 4 form to be psi. So here is the definition of a nearly G2 manifold. So a manifold M with a G2 structure phi is a nearly G2 manifold if, first of all, phi is a G2 structure, and if you take the exterior derivative of phi, then you get 4 psi. So exterior derivative of phi is a 4 form, but it need not be a scalar multiple of the Hodge dual of phi itself. But I'm saying that if such is the case, then we call M as a nearly G2 manifold. And this 4 is, you can put any constant here. I'm just choosing 4 because that's what we do in the paper. And you can rescale the metric and then orientation to change this constant. So here's a remark. So the existence of a G2 structure on M is a purely topological phenomena. A G2 structure on M exists if and only if M is orientable and spinable, which is equivalent to the vanishing of the first and second Stiefel-Whitney classes. So W1M equal to 0 if and only if M is orientable, and W2M equal to 0 if and only if M is spinable. And by spinable, I mean that you can put a spin structure on the manifold. So here are 2 basic facts about nearly G2 manifolds. The first is that nearly G2 manifolds are always positive Einstein. So this means that the Ricci curvature of the underlying metric is a positive multiple of the metric itself. And since I mentioned on the last slide that a G2 structure or a nearly G2 structure on M exists if and only if M is orientable and spinable, this means you can put a spin structure. And once you have a spin structure, one can define what is known as a Dirac operator, which takes a spinner to a spinner. So Dirac operators are self-adjoint, elliptic, and so on and so forth. All right. So now suppose I have a 7-dimensional manifold with a G2 structure. So it's a common phenomena that whenever you have a G structure, where G is any Lie group, then the space of tensors, or in this case, space of differential forms, they always decompose further according to the irreducible G representation. So in this case, the Lie group is the exceptional Lie group G2, and on the manifold M, there is a further decomposition of the space of differential forms according to the irreducible G2 representation. So these are given by following. So the space of differential 2 forms, omega 2m, decompose as omega 2 7, direct sum omega 2 14. So this 7 and 14 are pointwise dimensions of these spaces. And by Hodge star, this is isomorphic to omega 5. And similarly, omega 3m decomposes as omega 3 1, direct sum omega 3 7, direct sum omega 3 27. So again, these are pointwise dimensions. And by Hodge star, it's isomorphic to omega 4m. So, and this decomposition is L2 or in fact, it's pointwise orthogonal. So it's L2 orthogonal. So suppose I have an arbitrary 3 form or an arbitrary 2 form. Then a priori, that 3 form is a combination of these 3 components. And similarly, a 2 form is a combination of these 2 components. But so that's where the importance of our first result comes into play. So what we proved is that suppose M phi psi, so remember psi is the Hodge dual of phi, is a complete nearly G2 manifold. So by complete, I mean that the underlying metric is complete. And suppose it's not isometric to the 7 sphere with the round metric, then every harmonic 3 form lies in omega 327. Equivalently, every harmonic 4 form lies in omega 427. And similarly, every harmonic 2 form lies in omega 214. Equivalently, every harmonic 5 form lies in omega 514. So if I have a harmonic 3 form, then from this decomposition, we see that a priori it can be a combination of any of these components. But what we proved is that if you have a nearly G2 manifold, then any harmonic 3 form must lie in the omega 327 component only. And similarly, every harmonic 2 form explicitly lies in omega 214. So this result completely characterizes the cohomology of any nearly G2 manifold, which is not isometric to S7, because omega 1 and omega 6, they are already known by Poincare duality. So all we needed to know was information about omega 2 and omega 3. And by Hodge theory, harmonic forms basically describe the cohomology of the manifold. And this not isometric to S7 is not even a condition, because cohomology of S7 is already known. So we have describing everything else. So that's the first result of our paper. So now let's come to the deformation theory part of the talk. So suppose I have a nearly G2 structure, phi comma psi on our manifold. And what we want to do is we would like to see whether we can deform this given nearly G2 structure to a nearby nearly G2 structure. Let's call it phi tilde and psi tilde. So the way to address these problems is that one would like to look at the space of all nearly G2 structures under certain equivalences. And usually the case with geometric structure is that you look for equivalences. So you mod out by diffeomorphisms isotopic to the identity. So I am going to denote the group of diffeomorphisms isotopic to the identity by diff naught M. So here is a schematic diagram of how to approach this problem. So suppose P denotes the space of all G2 structures on M, and this mathfrak P, which is a pair phi comma psi. So it's not actually a pair. It's if you have phi, you can always get psi, but I'm just writing it as a pair. Suppose it's a point in this space capital P, and suppose it's a nearly G2 structure on M. So everything inside this green curve is the set of all G2 structures, and I have a point mathfrak P, which is a nearly G2 structure. And so this group diff naught M, which is again diffeomorphisms isotopic to the identity, it acts on this space P, because this phi is always diffeomorphism invariance. So let us denote by OP the orbit of this point P under the action of diff naught M. So this in this picture, this orbit is denoted by this red curve. So usually, like the general strategy for studying a deformation theory is to first prove what is known as a slice theorem. So a slice theorem basically says that you can find what is known as a slice, which is actually a submanifold of this space P, such that at every point you can get a complement, which is denoted by this curve C, to the tangent space of the orbit. So what we would like to do is we would like to say that this tangent space to the space capital P at the point small p can be written as TPOP, where this is the tangent space to the orbit, plus a complement. So we proved a slice theorem by explicitly finding a complement to the tangent space of the orbit. And then the way we proved this slice theorem and the previous theorem on cohomology of nearly G2 manifold was to first define a Dirac type operator and then use mapping properties of that. So once we have a slice theorem, we can describe or we can characterize infinitesimal deformations of a given nearly G2 structure. So this result, which I'm going to state now, was already proved by Alexandrov and Simmelman in 2012, but we gave a different proof of this using our methods. So suppose K denotes the space of Killing vector fields on M. So these are vector fields such that when you take the Lie derivative of the metric, it's 0. So the theorem says that suppose I have a 7-dimensional manifold which is complete, and suppose there is a nearly G2 structure, then the infinitesimal deformations of this nearly G2 structure are in one-to-one correspondence with pair x comma psi C naught, where x is a Killing vector field and C naught is a 3 form which lies in the omega 327 component, such that this C naught, when you take the Hodge Laplacian of C naught, this is 16 times C naught, and when you take the Hodge Laplacian of x, you get 12x. So this theorem completely characterizes all the infinitesimal deformations space of a given nearly G2 structure. It says that they are in one-to-one correspondence with a pair of Killing vector field and a 3 form which explicitly lies in the omega 327 component, such that they both are eigenvectors of the Hodge Laplacian operator with eigenvalues 16 and 12 respectively. So as I say here, that this theorem characterizes the first order deformation of a given nearly G2 structure. Now, the goal of our paper was to see, can we describe higher order deformations by extending this further? So this is just infinitesimal deformation, and we wanted to see whether can we do second order or third order deformation. So to this end, let me make a definition to describe what second order deformations are. So suppose I have a given nearly G2 structure phi naught psi naught, then a second order deformation of phi naught psi naught in the direction of infinitesimal deformation C1 eta 1, C2 eta 2, where C2 is in omega 3 and eta 2 is in omega 4, such that when you look at the formal power series, phi is equal to phi naught plus epsilon C1 plus epsilon square by 2 C2, and psi equal to psi naught plus epsilon eta 1 plus epsilon square by 2 eta naught. So this is the formal power series in this parameter epsilon. Then this is a nearly G2 structure on the manifold up to order epsilon square. So what that means is that if I take d of phi, then it should be equal to 4 psi. So if that is the case, because a priori that might not be true, I'm just taking any arbitrary 3 form and 4 form. But if that is the case, then we say that phi naught psi naught has a second order deformation in this direction. So that does not always happen. In fact, the obstruction on a given first order deformation of the nearly G2 structure phi naught psi naught to be extended to second order is given by the following lemma. So if phi naught psi naught is a nearly G2 structure, and I have a pair C comma eta, which is in omega 3 cross omega 4 exact, which is a first order deformation of phi naught C naught, then a pair is star alpha comma alpha, which is in omega 3 cross omega 4 exact, is a second order deformation if and only if the L2 inner product of d star alpha plus 4 star alpha with chi is 0, where chi is any co-closed 327 form, which is an eigenvector of the Hodge Laplacian with eigenvalue 16. So this lemma puts a very strong condition for an infinitesimal deformation to be integrated to second order. Because if there is a second order deformation, then this L2 inner product must vanish, and this should happen for any chi which is in omega 327, which are co-closed and eigenvector of the Hodge Laplacian. So that led us to the final theorem of our paper. So the nearly G2 structures on homogeneous manifolds are completely classified. So Alexandrov Zimmerman, in the same paper in 2012, they proved that apart from this L-of-Wallach spaces, the nearly G2 structure on rest of the homogeneous spaces are rigid. And on this L-of-Wallach space, which is given by SU3 cross SU2 mod out by SU2 cross U1, there is an infinitesimal deformation space, which is 8-dimensional. In fact, it is isomorphic to the Lie algebra of SU3. So a natural question arises that do the infinitesimal deformation of this nearly G2 structure on the L-of-Wallach space can be integrated to the second order, because we already have a characterization for such a thing to happen. So this is the theorem which we proved that that is not possible. So precisely the infinitesimal deformations of the homogeneous nearly G2 structure on the L-of-Wallach space SU3 cross SU2 mod by SU2 cross U1 are all obstructed to second and higher order. And then the way we proved this result was again to use a special Dirac type operator, which is same as for the previous result, and to explicitly use the representation theoretic aspect of this space of the L-of-Wallach space. So that would be all, and thanks a lot for your attention.
Thanks, Shubham. If there are any questions.
So, I mean, these nearly G2 manifolds are much easier to, are they much easier to construct than G2 manifolds? I mean, where, so I guess G2 is where this P has to be parallel, right?
Right, right.
So are the nearly G2 ones much easier to construct?
No, I don't think so. In fact, so So like for torsion-free G2 manifolds, this is, so the equation is given by a non-linear elliptic PDE. For nearly G2, it's again a non-linear elliptic PDE, but I don't think so that they are like, if given a 7-dimensional manifold, one can describe criteria for like constructing those. For homogeneous, it's like easier because they have already been classified. But for arbitrary manifolds, I don't think it's that easy. In fact, there is a latest paper by Fabio Podesta, I guess, where he describes a one-parameter family of nearly G2 manifolds on R4 cross S3. So in the non-compact, so that's like sort of the first example, I guess, in this setting. But yeah, a priori, it's like not that easy.
I see, but I mean, are there conjecture? I mean, for instance, for G2, there's this Donaldson approach, right? Of
right,
you take a bundle over Calabi-Yau and then try to glue these things
right,
together to construct a G2, right?
Right,
So
right.
are there some conjectures for nearly G2?
Not that I know of. I mean, so like for example, in the torsion-free case, like the first construction was by Dominic Joyce, where he does the like Kummer construction. Then, as you said, like Donaldson gave this idea of having to asymptotically a cylindrical Calabi-Yau and then glue them in a nice way. So that is known as the twisted connected sum construction. But for nearly G2, I don't know like any conjecture or any approach like this. In fact, it would be very interesting to like see if to come up with such a construction.
I see, but at least heuristically, I mean, do you think this should, something like this should hold, or I mean, one should possibly?
Yes, like so while we were doing this project, so we had to like go through what Dominic Joyce did for his Kummer construction, and so as I said, this like existence of nearly G2 structure is also an elliptic problem. The only difference is that in torsion-free case, you have an elliptic operator acting on a tensor equal to 0, whereas in this case, you might get an eigenvector, but it's still elliptic. So like one expects that like things should go through with the modifications. I certainly expect that, but
maybe a nice problem for you to try.
Yeah, exactly. yeah. That's
all right.
correct.
Yeah, thanks.
Yeah, no problem. Yeah.
Yeah, any more questions?
There is a question in the chat from YouTube. No, was it already asked? I missed it.
Oh, okay, yeah.
I guess this one was asked.
This one's for the last talk.
Yeah.
Okay. Sorry,
Okay.
I missed that time.
Yeah, maybe Dr. Shiv, then we can close.
Yes, we can thank the speaker. Maybe.
Yeah. Thank you. Thanks.
Thank you.
Thanks, Shubham.
Yeah, thank you. Thanks a lot for attending.
And thanks to Dr. Shiv also for chairing this session.
Thanks, Soumya.
Thanks a lot. Okay, then we close today's session. We'll meet tomorrow at 10.
Okay,
Thank you
yeah.
all.
Yeah,
Thank
bye
you.
everyone.
Bye.